as the visual display gently fades away into soft, unbroken darkness. Take a quiet moment to settle into complete comfort, allowing your body to relax deeply and your breathing to find its slow, natural rhythm. Tonight, we begin a long, peaceful journey together through the history of astronomy, embarking on a continuous 40-part exploration of how human beings first looked up at the vast night sky and gradually uncovered the wondrous harmony of the cosmos, long before the bustle of modern cities illuminated our nocturnal landscapes, before books recorded the passing of centuries, and before optical glass was polished to gaze across light years. The dark sky above was humanity's most constant, comforting companion. Each evening, as the sun dipped gently beneath the western horizon and the lingering colors of twilight softened into deep indigo, the night sky unfolded its breathtaking, timeless tapestry of faint glowing bands, wandering planets, and uncountable stars. For early communities living close to the earth, the heavens were not merely a source of quiet wonder. They were a living, reliable clock and an eternal celestial calendar. The slow, graceful arc of the sun each day, the changing phases of the moon through the night, and the seasonal rotation of the constellations across the sky provided structure, meaning, and safety in a world that often felt unpredictable. By observing these predictable movements over countless generations, ancient observers learned when to plant their crops, when to gather the harvest, and when to prepare for the quiet cold of winter. In this opening part of our shared exploration, we turn our minds back over 5,000 years to the very dawn of human skywatching, where early cultures built enduring monuments of stone that merged the quiet beauty of the earth with the steady rhythms of the stars. Among all the astronomical cycles recorded by early humans, none carried greater weight or emotional resonance than the sun's annual journey across the sky. As autumn faded and the chill of winter settled over the land, ancient observers watched with quiet reverence as the days grew steadily shorter, the sun rising lower in the morning sky and setting earlier each afternoon. The world seemed to slow down. Shadows stretched long across the frost-touched fields, and nature sank into a deep, peaceful slumber. To live through the onset of winter in ancient times was to hold a quiet faith in the eventual return of warmth and light, eagerly waiting for the moment when the shortening of days would finally pause and reverse, the sacred turning point known as the winter solstice. In northern regions, where winter nights were long, dark, and biting cold, the solstice marked a moment of quiet hope, reassuring early peoples that the sun had not abandoned the earth, and that spring would surely return in due time. To track this critical moment, observers carefully marked the horizon points where the sun rose and set, using wooden posts or standing stones to trace its subtle northward and southward shifts over many years. To honor this fundamental cosmic event, ancient communities dedicated extraordinary effort, care, and architectural skill to build physical structures capable of marking the exact morning of the solstice. Across continents, from fertile river plains to forested hills. Megalithic builders quarried massive stones and moved great mounds of earth, aligning their structures with astonishing geometric precision to capture the rising or setting sun on key astronomical days. These monuments were far more than ceremonial gathering places. They were permanent, monumental instruments of observation, crafted through generations of patient stargazing and an intimate understanding of the heavens. One of the most remarkable and breathtaking examples of this ancient skywatching tradition can be found nestled within the quiet, rolling green countryside of eastern Ireland, near a gentle bend in the River Boyne. Here stands a grand circular mound of earth, white quartz stones, and dark river cobbles that has endured for more than 5 millennia. Around 3200 BCE, in the Boyne Valley of Ireland, megalithic builders engineered the stone passage tomb of Newgrange with a precise roof box aperture, allowing a single beam of morning sunlight to slip through the dark corridor and illuminate the inner chamber for 17 minutes on the winter solstice. To appreciate the true wonder of this creation, picture yourself standing inside the deep stone chamber of Newgrange in the still, cool darkness just before dawn on the morning of the winter solstice. The air is calm, cool, and peaceful, carrying the subtle, grounded scent of ancient stone and earth. Deep within the central chamber, surrounded by massive vertical stones decorated with intricate spiral carvings, you are enclosed in complete velvet darkness. Outside, as the eastern horizon slowly brightens from shadowy blue to soft shades of rose and gold, the rising sun reaches the exact position needed to align with the narrow, specially designed opening situated just above the main entrance. As the sun's upper rim crests the distant horizon, a brilliant shaft of warm golden light pierces the roof box opening. This narrow beam glides smoothly down the long 19-meter stone corridor, traveling across the stone floor like a ribbon of living light, until it reaches the inner chamber at the very heart of the mound. For 17 serene minutes, the once pitch-black chamber glows with a warm, radiant illumination, transforming the cold stone walls into a golden sanctuary before the sun continues its upward arc, and the light gently fades back into peaceful shadow. This extraordinary harmony between stone and starlight reveals just how deeply ancient people understood the sky and how central the movements of the cosmos were to their daily lives. Long before written mathematics, formal telescopes, or modern scientific equipment, the builders of Newgrange possessed a sophisticated, empirical knowledge of solar trajectories and horizon astronomy, meticulously passing their observations down from one generation to the next. The roof box was no simple window or fortunate coincidence. It was a purposefully engineered celestial aperture, designed with remarkable spatial accuracy to capture a brief, meaningful moment of light year after year without fail. The annual 17-minute illumination served as an enduring symbol of rebirth and continuity, offering a visual promise that even in the absolute darkest morning of the year, light would always return to warm the earth and awaken the sleeping land. As we rest quietly tonight, we can take deep comfort in knowing that this same timeless skyward gaze has united human hearts and minds across thousands of generations. The silent stone passage of Newgrange marks the very beginning of our long, soothing journey through the history of astronomy, a narrative that will take us from ancient stone monuments and early Babylonian star charts to the birth of mathematical models in ancient Greece, the brilliant astronomical traditions of medieval Islamic scholars, and the invention of the optical telescope. But for now, let the gentle memory of that golden solstice beam rest in your mind, bringing a deep sense of warmth, peace, and quiet stillness as you drift comfortably off into a restful, dreamless sleep under the watchful stars. Long ago, before cities glowed with artificial lights, and before mechanical clocks measured the steady progression of hours, the night sky served as the great shared canvas of human existence. When dusk softly settled over gentle hills, forest glades, and wide river valleys, people would step outside to behold an unblemished vault of stars, watching the familiar constellations slowly emerge from the deepening violet gloom. In those quiet moments, as cool night air brushed against the earth, the sky was not merely a distant, unreachable canopy of light, but an intricate, faithful, and living ledger of time. Each subtle seasonal shift, from the soft thaw of early spring to the crisp arrival of autumn frost, revealed itself first in the slow, graceful movement of luminous points overhead. Early communities learned to read these cosmic patterns with deep reverence and practical care, recognizing that their very survival depended upon understanding when to scatter seeds into fresh, fertile soil, when to guide herds across vast pastures, and when to gather and preserve harvests for the quiet stillness of winter. The stars offered a serene, unwavering rhythm, bringing harmony and order to the mysteries of human existence. Across continents and through generations, simple observation gradually transformed into carefully preserved knowledge. Skywatchers began to pay closer attention, observing not only the sun's broad daily arch, but also the delicate sliver of the waxing moon and the distinct groupings of stars that reappeared with comforting regularity year after year. In this peaceful dawn of observation, the desire to hold fast to the fleeting movements of the heavens led to the creation of the world's first physical star maps, enduring objects crafted to preserve the memory of the sky. Among the most extraordinary of these early creations is a remarkable relic discovered in the rolling hills of Central Europe, where ancient metalworkers sought to forge the cosmos into bronze. Beneath the tranquil canopy of an ancient landscape, skilled artisans carefully hammered copper and tin into a heavy, circular disc, imbuing the dark metal with the deep indigo hue of a night sky just after sunset. Upon this burnished surface, They laid delicate pieces of gold, mapping out the celestial bodies that guided their agricultural lives with quiet precision. Dating to around 1600 BCE in central Germany, the bronze Nebra sky disk was crafted with gold foil inlays depicting a slender crescent moon, 30 stars, and the cluster of the Pleiades to track the changing seasons. To hold this heavy artifact was to hold a miniature model of the universe, a sacred instrument designed to harmonize the lunar month with the solar year. The presence of the Pleiades, a tight cluster of shimmering stars, often known as the Seven Sisters, was particularly crucial for these early agrarian communities. When the Pleiades appeared alongside the slender crescent moon in the early spring twilight, farmers knew it was time to turn the earth and plant their crops. When the same arrangement returned in the chill of autumn, it signaled the arrival of the harvest and the coming rest of winter. The arcs along the edges of the disk marked the precise points where the sun rose and set during the summer and winter solstices, capturing the extreme boundaries of the solar journey across the horizon. Looking upon the smooth, cool metal of the Nebra sky disk, one can almost feel the quiet contemplation of its creators as they stood under the vast night sky, matching the golden shapes on the bronze to the real stars burning softly overhead. While metalworkers in Central Europe captured the stars in bronze and gold, scribes in the fertile river valleys of Mesopotamia were developing a different, yet equally profound, way to record the movements of the heavens. In the peaceful courtyards of temple complexes along the Euphrates and Tigris rivers, astronomers sat beneath clear, dry night skies, meticulously watching the shifting positions of planets and stars. Rather than working with metal, these dedicated observers used fine reed styluses and tablets of soft clay to preserve their detailed celestial logs. In ancient Babylon around 700 BCE, scribes carefully pressed cuneiform marks into damp clay tablets known as the mulapin, recording the quiet, predictable risings of bright stars like Sirius to track the steady passage of the seasons. Named after the very first constellation listed upon their surfaces, the Plough, these compendiums represented centuries of systematic stargazing, gathering generations of sky lore into an orderly, elegant system. The scribes divided the sky into 3 great paths, named for the principal deities Anu, Enlil, and E, mapping how stars moved through each domain over the course of the year. The tablet entries detailed the dates when prominent stars would first become visible in the morning twilight after being hidden by the sun's glare, a phenomenon known as heliacal rising. The predictable reappearance of Sirius, the brightest star in the night sky, was recorded with special reverence, as its rising heralded crucial seasonal transitions and guided agricultural planning across the region. As the soft clay tablets dried under the warm sun, the delicate, wedge-shaped impressions hardened into permanent libraries of astronomical wisdom. Together, artifacts like the Nebra sky disk and the written tablets of the MULAPIN reveal how early human societies, separated by great distances and distinct cultures, shared a common fascination with the nocturnal sky. Whether forged in shimmering gold upon bronze or etched into damp clay, these early works reflect a deep human desire to understand the celestial harmony that governs the natural world. The night sky was the first great clock, a quiet compass, and an infinite calendar whose hands were the moon, the sun, and the drifting stars. Through centuries of quiet observation, ancient stargazers realized that the universe operated not on randomness, but on smooth, predictable cycles that repeated with gentle perfection. As evening fell over ancient villages, farms, and stone temples, people could look up into the darkening expanse with a sense of wonder and reassuring comfort, knowing that the same stars that watched over their ancestors would continue to guide their children. As we rest beneath our own night sky today, looking up at the same constellation of the Pleiades or the bright radiance of Sirius, we share in that ancient, tranquil tradition. The quiet efforts of those early skywatchers established the very roots of astronomy, turning our gaze upward and setting humanity on an enduring journey of discovery, a journey that would slowly unfold over thousands of years, guided always by the quiet, steady light of the stars. As twilight fades over the floodplains between the Tigris and Euphrates rivers, the ancient brick towers and rooftops of Mesopotamia grow cool beneath an immense, dark sky. For centuries, quiet observers of the heavens had climbed to these raised platforms, turning their eyes upward into the evening air to watch the slow, predictable choreography of the stars. In the stillness of those ancient nights, when the sounds of daily life hushed into a gentle silence, the firmament was not merely an expanse of darkness, but a living tapestry of light, order, and rhythm. Every star maintained its fixed position relative to its neighbors, drifting together in a grand, unified sphere that turned softly above the sleeping world below. Yet among these steady constellations moved 5 distinct wanderers' planets, whose paths gently strayed from the background stars, weaving intricate and thoughtful routes across the band of the zodiac. To the skywatchers who sat in the cool night air of Babylonia, these wanderers were central to understanding the subtle harmony of the cosmos. Among them, the bright and majestic planet Jupiter moved with a particularly deliberate grace, taking 12 long Earth years to complete its full circuit around the heavens. Watching Jupiter required a practice of profound patience, observing night after night as the luminous sphere shifted by tiny, almost imperceptible increments against the familiar backdrop of distant stars. Over generations, these ancient astronomers realized that the sky was governed by rules that could be recorded, measured, and understood. What began as simple visual tracking evolved gradually into an exquisite tradition of systematic mathematical documentation. The scholars of the region created detailed diaries of celestial events, logging the precise moments when planets rose at dusk, when they changed direction in their apparent retrograde loops, and when they vanished into the bright glare of dawn. In doing so, they laid the quiet foundation for scientific astronomy, transforming the human relationship with the stars from passive wonder into a calm and orderly discipline of prediction, rooted in the unhurried observation of nature's deepest cycles. In this atmosphere of steady inquiry, the scribes of Babylon brought an extraordinary level of mathematical sophistication to their work, merging geometric reasoning with the gentle art of stargazing. Around 350 BCE in Babylon, scribes used fine reeds to press geometric trapezoids into soft clay tablets, calculating Jupiter's slow journey across the zodiac over 60-day intervals of the night sky. This remarkable technique was centuries ahead of its time, relying on the subtle relationship between time and apparent speed to determine how far the planet would travel along the celestial path. As a scribe held a stylus of dried reed, pressing tiny triangular wedge marks into the supple, unbaked clay, they were translating the physical motion of the cosmos into abstract geometric shapes. By plotting the changing velocity of Jupiter as a line that sloped gradually over a span of 60 days, the area underneath that line formed a trapezoid, a four-sided figure, whose total area represented the exact angular distance Jupiter traversed through the constellations. To visualize a planet's wanderings not merely as a list of numbers, but as a geometric area shaped by time and speed, reflected a profound and serene leap in human thought. These scribes worked in quiet rooms or upon flat rooftops illuminated by small oil lamps, their fingers moving with practiced care across small rectangular tablets of gray clay. Each tablet was compact enough to rest comfortably in the palm of a hand, yet contained within its pressed impressions a vast landscape of astronomical time and space. The 60-day intervals were chosen with intention, capturing a crucial segment of Jupiter's journey as it brightened, slowed, and moved through its arc before gradually fading into the sun's glare. The scribes were not seeking to hurry the sky or force it into rigid boxes. Rather, they sought to walk in step with its slow cadence, creating an enduring mirror of the cosmos on the surface of the earth, using nothing more than river clay, reed, and patient thought. In those quiet hours of calculation, the distant, silent path of Jupiter found a peaceful home upon the earth, bridging the infinite expanse above with the delicate craft of human hands below. As each clay tablet was completed, it was left to dry naturally in the warm Mesopotamian air, hardening into a permanent record of a single moment in the long story of the stars. Thousands of these clay tablets would eventually accumulate in ancient archives, preserving centuries of celestial observations like quiet leaves in a vast library of time. What makes the work of these Babylonian skywatchers so deeply moving is their quiet trust in the continuity of the universe. They understood that the sky they observed was was the very same sky watched by their ancestors, and that it would remain unchanged for those who came long after them. The 60-day geometric calculations for Jupiter were part of a continuous, multi-generational effort to map the subtle variations in planetary motion with mathematical elegance. Jupiter, moving through its 12-year cycle, served as a majestic cosmic clock, marking the passage of time with an unhurried, reassuring constancy. As the planet moved from one zodiacal constellation to the next, the scribes recorded its position with care, noting how its speed appeared to change as Earth and Jupiter moved along their respective paths around the Sun. Although they did not yet possess the concept of a heliocentric solar system, nor did they have optical telescopes to magnify the faint disk of the planet, their mathematical intuition allowed them to capture the underlying mechanics of planetary movement. The geometric trapezoids they pressed into soft clay represented an early form of integral calculus, calculating total displacement by finding the area under a curve of changing velocity. This brilliant insight would vanish from historical records for nearly 2,000 years, only to be rediscovered in medieval Europe. Yet here, in the quiet cities of ancient Mesopotamia, it flourished as a peaceful, practical tool for understanding the heavens. In the still hours of the night, as the stars drifted softly overhead, these scribes worked in quiet harmony with the cosmos, turning complex astronomical events into calm, beautiful geometry that demonstrated the power of patient human observation. Looking back across the centuries at those ancient Mesopotamian nights, we can feel a deep sense of stillness and connection with those early watchers of the dark. Their work reminds us that astronomy has always been, at its core, a quiet practice of listening to the universe and observing its gentle rhythms. Long before there were modern observatories, high-powered lenses, or digital sensors, there were simply human eyes, soft river clay, reed styluses, and the silent arc of Jupiter moving across the zodiac, the peace that settled over Babylon as the scribes laid down their tools at the end of a long night of calculation, is the same peace that awaits us whenever we look up at the night sky. The universe operates at its own measured pace, entirely unhurried, bound by natural laws of exquisite grace and mathematical balance. As Jupiter continues its quiet journey across the night sky tonight, taking 12 years to complete its broad orbit, just as it did millennia ago, it carries with it the quiet legacy of those ancient scribes. Their trapezoid calculations remain preserved in clay, silent witnesses to an age when humanity first learned to read the mathematical harmony written among the stars. And so, as the night deepens and the constellations turn softly in their ancient, timeless paths, we can let our thoughts rest in the calm, steady rhythm of the cosmos, a universe of quiet order, infinite depth, and enduring peace. As the cool night air settles gently across the coastal valleys of Peru, a profound stillness rests upon the dry desert earth, where the vast sky meets the low, rolling hills in a seamless, softly glowing expanse. Long before written records captured the story of the stars, in this part of the world, early human communities looked to the heavens with quiet curiosity, seeking order and comfort in the reliable, recurring rhythms of the celestial realm. In the peaceful solitude of the Casmasechan Basin, nestled between the Pacific coast and the towering, snow-capped slopes of the Andes, the night sky slowly yields to the delicate hues of early morning, transitioning from deep indigo and dusty violet into soft shades of rose and pale amber. Here, in an environment shaped by vast open spaces, dry breezes, and remarkably unclouded air, the celestial sphere reveals itself with exceptional clarity, inviting anyone who stands beneath it into a state of quiet contemplation. For the ancient peoples who inhabited these arid coastal strips, watching the sky was not merely a practical endeavor, but a meditative practice that connected their daily lives to the grand, silent geometry of the universe. The sun, rising each morning above the jagged ridgelines, was a steady and comforting companion whose journey across the sky marked the passage of seasons, the subtle shift of coastal currents, and the essential cycles of life, water, and harvest. As the last stars quietly dim in the fading darkness of the desert sky, the land stands silent and serene, illuminated by the gentle promise of a new day. In this tranquil environment, ancient skywatchers began to notice that the exact position where the sun first broke over the eastern horizon shifted slightly each morning, creeping north or south along the mountain crests in a slow, majestic dance that repeated with perfect fidelity year after year, offering a reliable pattern upon which they could build their understanding of time. High above the valley floor, set against the pale morning sky upon a barren desert ridge, stands one of the most remarkable and ancient astronomical monuments of the Americas. Constructed around 300 BCE along a desert ridge in Peru, the 13 towers of Chanquillo formed a precise horizon calendar, tracking the sun's steady movement as it rose through narrow stone gaps throughout the year. Arranged in a continuous, graceful line along the spine of the hill, these 13 rectangular stone towers stretch from north to south like a gentle crest against the open sky. Built from carefully chosen fieldstones and mortar, their weathered surfaces bear witness to more than 2 millennia of quiet solitude in the high desert air, preserved by the dry climate and the tranquil sanctuary of their remote setting. To an observer standing at specific, designated viewing points, placed precisely to the east and west of the ridge, the towers create a deliberate, tooth-like skyline with narrow, regular gaps spaced evenly between each structure. When the morning sun emerges from behind the ridge, its first rays pass through these narrow stone intervals, casting long, slender beams of light across the valley floor and signaling the exact time of year to those who watched below. The architectural symmetry of the towers was not merely decorative or ceremonial. It represented a deeply sophisticated integration of natural geography, practical geometry, and patient solar observation, effectively turning an entire hilltop into a living instrument for measuring the flow of time. As the morning light touches the ancient masonry, the stone structures warm slowly, glowing with a soft golden hue against the muted tones of the desert landscape. Every detail of their alignment reflects a profound patience and an intimate knowledge of the sun's annual path, offering a physical anchor for human thought in an ever-shifting world where the passage of days could be read directly from the earth itself. Throughout the course of the solar year, the sun's point of origin moves continuously back and forth along this manufactured horizon, creating a visual symphony of light and shadow that marked the peaceful rhythm of life for ancient observers. During the summer solstice, when the days were longest and the sun reached its northernmost extent, the dawn light would break precisely over the northernmost tower, crowning its stone edge in a brilliant, warm ring of morning gold. In the weeks and months that followed, as the earth continued its gentle, unhurried journey around the sun, the morning light would drift slowly southward day by day, passing through each successive gap between the stone towers like an illuminated pendulum, marking the steady passage of the season. By the time of the equinox, when day and night stood in perfect and tranquil balance, the sun would rise through the middle towers, casting symmetrical shadows across the desert floor and reassuring the watchers of the cosmos's unchanging order and balance. Eventually, at the winter solstice, the sun reached the southernmost tower, pausing briefly in its trajectory before beginning its slow, predictable journey back toward the north. This annual movement across the 13 towers provided the community with an extraordinarily accurate horizon calendar, precise to within a single day, allowing them to anticipate seasonal transitions, schedule agricultural tasks, and honor sacred communal moments without the need for written texts or complex mathematical tools. Observing this gradual shift required nothing more than a quiet morning stance, a clear view of the ridge, and a willingness to watch the light change with patient attention. In the serene atmosphere of Chankillo, time was not something to be rushed, controlled, or measured in fleeting seconds. It was a slow, majestic tide of light that washed gently over the stone towers, inviting quiet contemplation and instilling a deep, reassuring sense of harmony with the natural world. As evening returns to the Chasmosechen Desert and the sun begins its quiet descent behind the western horizon, the 13 towers of Chankillo cast long, peaceful shadows over the quiet ridge, returning once more to the still and serene embrace of the night. The warm desert breeze carries a cool softness as twilight deepens, blending the earth and sky into quiet, soothing tones of indigo, violet, and deep slate blue. One by one, the stars begin to appear in the darkening canopy above, pinpricks of soft, silver starlight that have shone down upon these stone towers for more than 2,000 years, unchanged by the passage of centuries or the quiet turning of the world. The ancient skywatchers who stood upon this desert ridge left behind no written books or formal treatises. Yet their legacy endures eloquently in the very stone of the landscape, demonstrating how deeply early cultures sought to understand their place within the cosmic order. Standing in silence under the vast Peruvian night sky, one can feel the timeless connection between human curiosity and the silent, comforting grandeur of the universe. The towers remain as a serene monument to human patience, optical clarity, and observational wisdom, a quiet invitation for us to slow our thoughts, release the cares of the day, look upward, and rest in the enduring harmony of the stars. As the night deepens and the desert grows still, the mind settles naturally into a calm and tranquil rhythm, carried along by the slow, eternal cycle of light and shadow that has guided skywatchers through the ages, offering deep rest, lasting peace, and quiet wonder beneath the ancient sky. On the serene island of Samos, cradled by the gentle tides of the Aegean Sea under a vast and unhurried night sky, ancient observers spent peaceful hours watching the slow, rhythmic turning of the heavens. In the 3rd century before the Common Era, the Mediterranean world was touched by a quiet intellectual awakening, where the ancient art of skywatching began to merge with the precise, elegant beauty of geometry. Samos had long been a sanctuary of thought, a place where early philosophers looked out upon the quiet sea and pondered the underlying order of nature. These early natural observers did not look up at the stars with anxiety or haste. Instead, they sat upon cool stone terraces as twilight gave way to deep indigo, allowing their eyes to adjust to the subtle gradations of celestial light. They noticed how the moon, floating like a pale silver shield against the darkness, changed its shape with predictable grace from evening to evening, sweeping through its familiar monthly cycle. This constant metamorphosis was not mysterious magic, but a gentle demonstration of shadow and sunlight interacting across the void. The scholars of Samos understood that the moon possessed no light of its own, but merely reflected the golden rays of the distant sun. As the evening sea breeze rustled softly through olive groves and carried the scent of wild thyme across silent courtyards, these patient thinkers realized that the geometry of lunar light held hidden clues about the grand scale of the cosmos. To gaze upon the moon was to look upon a celestial clock and a mirror of solar light, offering a calm invitation to measure the unseen distances that stretched between the Earth, its silver companion, and the brilliant star that illuminated them both. Among these dedicated seekers of truth was Aristarchus, a mathematician and astronomer whose quiet brilliance illuminated the ancient world. Settling into the calm rhythms of observation on his home island, he turned his mind toward a fundamental question that had long intrigued natural philosophers. How far away was the sun compared to the moon? around 270 BCE on the island of Samos. Astronomer Aristarchus measured the angle between the sun and moon during a half-moon phase, deriving the first geometric proof that the sun lies far beyond lunar orbit. His method was elegant in its simplicity and profound in its logical clarity. Aristarchus recognized that at the exact moment when the moon appears precisely half illuminated to an observer on Earth, a delicate celestial phase known as dichotomy, the lines connecting the Earth, the moon, and the sun form a perfect right-angled triangle, with the 90-degree right angle located precisely at the moon itself. By measuring the angle between the sun and the moon from the perspective of an observer on Earth at that fleeting instant, he could use the fundamental rules of geometry to calculate the relative proportions of the cosmic triangle. Under the clear Mediterranean sky, as the pale half-moon hung quietly beside the afternoon sun, Aristarchus observed the subtle angular separation between the two luminaries. Though the instruments of antiquity were elementary, relying on simple sightlines, shadow rods, and patient human vision, his geometric framework was impeccably sound. He determined that because the observed angle at Earth was extraordinarily close to a right angle, the sun had to be situated at a distance vastly greater than that of the moon, even though the precise measurements of his era were limited by human eyesight. His logical proof stood unshakable, establishing for the very first time in history that the lunar sphere was merely a close neighbor floating in the foreground of a much deeper ocean of space. This peaceful revelation gently opened the doors to a far grander cosmos than humanity had ever imagined. In his treatise on the sizes and distances of the sun and moon, Aristarchus built upon his initial geometric proof to explore the vast physical dimensions of the heavens. If the sun lay at such a staggering distance across space, and yet still appeared as a bright, warm disk in our daytime sky, it meant that the sun was not a modest glowing orb, but a colossal sphere of light, vastly larger than the Earth itself. By comparing the size of the Earth's shadow cast upon the moon during lunar eclipses with his solar distance calculations, he deduced that the sun's volume surpassed that of our planet many times over. This realization led Aristarchus to a quiet, revolutionary intuition. It seemed far more natural for our smaller Earth to glide softly around such an immense central beacon than for that giant furnace to circle our modest world. Long before modern telescopes would confirm his thoughts, Aristarchus contemplated a heliocentric order, imagining the Earth as a gentle wanderer moving in a slow, peaceful orbit around the sun, while rotating silently on its axis each day. Though his contemporaries found the concept difficult to embrace, preferring the familiar view of an unmoving Earth at the center of all things, the truth of his geometric reasoning remained an enduring testament to the power of quiet observation and human thought. The vastness of space far from being intimidating, offered a sense of profound stillness and cosmic harmony, reminding early stargazers that our world is a sheltered haven resting within an immense, luminous universe. As the night deepens and the silver half-moon drifts slowly toward the western horizon, the peaceful legacy of Aristarchus rests upon the sleeping earth like a quiet blanket. His ancient geometry demonstrated that even with simple tools and patient eyes, the human mind can reach across vast reaches of quiet emptiness to glimpse the underlying order of the heavens. Tonight, the same sunlight that Aristarchus studied continues to travel through the calm void, illuminating the cratered surface of the moon and casting a soft, gentle glow upon our world. The stars move in their silent, eternal paths overhead, untroubled by time, maintaining the peaceful rhythm that has guided navigators, dreamers, and scholars for thousands of years. As we listen to the soft cadence of the night, we can take comfort in the enduring harmony of the cosmos, where every planet, moon, and star moves with effortless grace. The vast distances of space enclose us in a quiet sanctuary of light and darkness, inviting the mind to let go of the day's concerns and surrender to the soothing rhythm of the universe, drifting peacefully into a deep, uninterrupted rest. As the golden warmth of the afternoon slowly fades across the ancient Mediterranean world, the mind can wander back over 2,000 years to the tranquil, sunlit halls of Alexandria. Here, beneath skies cleared by gentle desert breezes, the scholars of antiquity paused to observe the subtle, rhythmic interplay of light and shadow across the landscape. Among these quiet seekers of truth was Eratosthenes, a mathematician and chief librarian, whose curious intellect reached far beyond the cataloging of papyrus scrolls to contemplate the physical reality of the earth itself. In an era when travel was measured by the patient pace of walking or sailing along coastal waters, information traveled softly through stories told by merchants, travelers, and royal surveyors. Eratosthenes took great care to listen to these quiet reports, finding himself particularly intrigued by a description from the southern outpost of Sine, located near the first cataract of the Nile in modern-day Aswan. It was said that on the noon of the summer solstice, the longest day of the year, vertical obelisks and tall building pillars cast no shadow whatsoever upon the ground. Even more remarkably, direct sunlight reached all the way to the bottom of deep water wells, illuminating the calm water far below, without creating a single sliver of shadow along the stone walls. The sun hovered at the exact zenith of the sky, casting its golden beam straight down into the earth. Yet in Alexandria, situated several hundred miles to the north along the winding delta, a vertical post or gnomon planted in the earth at that precise same moment on the solstice cast a distinct and easily measurable shadow, where another observer might have dismissed this as a mere curiosity of geography. or local weather. Eratosthenes recognized a profound geometric revelation. He understood that if the sun was so unimaginably far away that its incoming light rays arrived at the Earth parallel to one another, then the difference in shadow angles between the two cities could only mean that the ground beneath them was gently curved. With methodical care and a calm, deliberate spirit, Eratosthenes set out to measure the precise angle subtended by the shadow in Alexandria. By comparing the height of the gnomon to the length of its shadow cast upon the smooth ground, he determined that the angle of the sun's rays was about 7 2/10 degrees, which represented exactly 1/50th of a full circle of 360 degrees. To complete his calculation, Eratosthenes needed to know the physical distance separating Alexandria from Scene. Relying on records kept by professional surveyors known as bamatists, who recorded distances by counting the steady, rhythmic steps of trained paces, or tracking the movement of camel caravans across the desert. He estimated the distance between the two cities to be roughly 5,000 stadia. By multiplying this distance by 50, Eratosthenes arrived at an estimate for the entire circumference of the planet, producing a figure remarkably close to modern satellite measurements. Around 240 BCE, Greek mathematician Eratosthenes compared the sun's shadow in Alexandria to the direct sunlight shining straight down a deep well in Scene, using the angle to calculate the Earth's circumference. This astonishing feat demonstrated that the human mind, using nothing more than a wooden stick, a deep well, and the fundamental laws of geometry, could embrace the vast scale of our home world. The realization that the Earth was a vast, unified sphere floating serenely in space brought a comforting sense of balance and order to the human imagination. As night slowly descended over the harbor of Alexandria, cooling the warm sands of Egypt and extinguishing the last fiery hues of twilight, the ancient world seemed to settle into a quiet, peaceful stillness, inviting stargazers to lift their eyes toward the pristine dark sky above. Drawn by the quiet beauty of the night, our thoughts drift across the calm waters of the Aegean Sea to the island of Rhodes, where another giant of early science spent his nights beneath an unclouded canopy of stars. More than a century after Eratosthenes mapped the curve of the Earth, the astronomer Hipparchus built a quiet observatory on the high ground of the island, far away from the distractions of daytime life. Surrounded by the gentle rustle of olive trees and the soft, rhythmic lap of waves against the rocky shore, he watched the celestial sphere turn above him night after night. Without the aid of modern telescopes or electronic sensors, Hipparchus depended entirely upon his unyielding patience, his clear vision, and simple mechanical sighting tools such as diopters and armillary spheres. He understood that to make sense of the heavens, one had to record them with absolute fidelity, transforming fleeting visual impressions into lasting numerical records. Patiently, he set about mapping the nighttime sky, measuring the coordinates of individual stars and cataloging their relative brightness with incredible care. He established a system that divided stars into 6 distinct categories of magnitude, designating the most luminous beacons of the twilight as stars of the first magnitude, while the faintest specks of light, barely discernible to the human eye, were placed into the 6th magnitude, creating a classification framework that astronomers still draw upon today. To verify his work, Hipparchus compared his own careful observations with older astronomical records compiled over a century earlier by Alexandrian astronomers Timacharis and Aristillus, as well as ancient Babylonian records preserved on clay tablets. In doing so, he discovered a tiny, unexpected shift in the position of key stars relative to the equinoxes, most notably the star Spica in the constellation Virgo. Around 127 BCE, on the island of Rhodes, astronomer Hipparchus catalogued 850 stars into 6 levels of brightness, noticing that the star Spica had drifted slightly from ancient records, and discovering the Earth's slow, gentle wobble of axial precession. This minute displacement of Spica was not the result of observational error or shifting stellar paths through space, but rather the quiet signature of an immense cosmic cycle operating behind the scenes of human history. Hipparchus realized that because the relative distances between neighboring stars remained completely fixed, it was not the stars themselves that were drifting, but rather the reference frame of the Earth itself that was slowly shifting. The Earth's rotational axis, he deduced, was undergoing a long, continuous wobble, tracing a slow circle against the background of the cosmos, like a spinning top coming to rest in slow motion. This motion, known as axial precession, causes the position of the celestial poles and the equinoxes to drift gradually through the zodiac over a vast cycle lasting approximately 26,000 years. It is a movement of such exquisite slowness that a person could live an entire lifetime without ever noticing a single change in the night sky. Only by bridging generations of careful observations could such a tranquil, grand truth be uncovered. Contemplating this silent wobble brings a soothing perspective to the human spirit, reminding us that we are part of an enduring cosmic tapestry that unfolds across unimaginable spans of time. As the centuries turn with soft and silent rhythm, Polaris yields its position to other stars, and the constellations tilt with endless, gentle poise across the heavens. Resting under this peaceful sky, we can feel anchored in the quiet vastness of the universe, wrapped in the comforting knowledge that the earth turns and sways in a timeless, protective lullaby, guiding all living things into deep, restorative rest. As night descends upon the tranquil waters of the Aegean, the darkness opens into a vast canopy of quiet stars, echoing the deep silence that has rested over the Mediterranean basin for thousands of years. Long before modern instruments brought the distant corners of the galaxy into sharp focus. Ancient observers walked along maritime shores and mountain terraces, resting their gaze upon the steady, predictable choreography of the night sky. In the gentle stillness of those evenings, when the warm sea breeze softened against coastal limestone, the moon rose in rhythmic phases, slender slivers of silver slowly swelling into luminous disks before waning back into soft shadow, while 5 bright wandering lights moved patiently against the backdrop of the fixed constellations. To the philosophers, mathematicians, and navigators of the Hellenistic world, these celestial movements were not random occurrences, but a grand, orderly harmony that invited deep study, reverence, and quiet contemplation. Across generations, scholars gathered in centers of learning, from Alexandria to the sunlit island of Rhodes, measuring angles with simple sighting rods, recording planetary retrogrades on papyrus, and drawing elaborate geometric models to explain the intricate machinery of the firmament. They perceived the sky as a series of nested, transparent spheres, smooth and eternal, turning with mathematical perfection above a quiet, resting earth. Yet beyond the parchment scrolls and geometric diagrams, there lived a profound desire among ancient craftspeople to make this hidden celestial harmony tangible, to build a physical bridge between the abstract geometry of the universe and the meticulous art of human hands. In quiet workshop spaces lit by flickering oil lamps, where the soothing murmur of the nearby sea provided a steady backdrop to long evening hours, early instrument makers began experimenting with metal plates, axles, and interlocking wheels, striving to condense the vastness of the heavens into portable mechanisms that could faithfully mirror the patient motion of the sun, moon, and planets across months, years, and decades. This union of philosophy and fine metalwork reached a breathtaking height of quiet mastery during the 1st century before the Common Era, when master craftsmen created what would become one of the most astonishing mechanical marvels of antiquity. Around 100 BCE, off the Mediterranean island of Antikythera, Greek artisans crafted a precise hand-cranked device with 30 interlocking bronze gear wheels, quietly tracking the smooth phases of the moon and the slow cycles of planetary orbits across a hand-engraved dial. Housed within a modest wooden casing no larger than a portable display box, this remarkable instrument held inside its bronze heart a miniature cosmos of extraordinary complexity and grace. By gently rotating a small side crank, an observer could move forward or backward through time, watching as multiple slender bronze pointers glided smoothly over concentric scales etched with fine Greek inscriptions, calendar months, and zodiacal symbols. The internal mechanism employed intricate gear trains of hand-cut triangular teeth, crafted with such extraordinary precision that they could calculate the variable speed of the moon as it traveled through its slightly irregular orbit, long before modern physics formulated the laws of planetary motion. A specialized pin and slot mechanism subtly shifted the rotational speed of the lunar gear, mirroring how the moon appears to accelerate and decelerate as it moves closer to or further from the Earth. Additional sets of interlocking gear wheels tracked the 19-year metonic cycle, which gracefully harmonizes the lunar months with the solar year, while lower spiral dials predicted the exact dates and times of solar and lunar eclipses according to the ancient Saros and Exeligmos cycles. Another dial even marked the 4-year cadence of the Panhellenic Games, weaving human cultural life directly into the fabric of cosmic time. To turn the crank of such a device was to hold a living mirror of the night sky in one's hands, a quiet testament to the belief that the seemingly infinite heavens operated according to principles of harmony, proportion, and quiet regularity that human intelligence could comprehend, capture, and preserve in bronze. Eventually, the merchant vessel carrying this delicate mechanical universe sank during a storm, coming to rest undisturbed in the cold, dark silence of the seabed off the coast of Antikythera for more than 2,000 years. As centuries unfolded above the waves, as empires rose, shifted, and faded into history, and as the specialized knowledge required to craft such complex clockwork vanished from memory, the bronze gears lay quietly submerged in deep turquoise waters, slowly cradled by marine sediment and encrusted with protective mineral layers, while the stars above continued their unhurried dance unchanged. When sponge divers unexpectedly rediscovered the fragile, corroded fragments in the early years of the 20th century, modern scholars were initially astonished, finding it difficult to believe that ancient Greek astronomers had achieved a level of mechanical design and mathematical integration that would not reappear in Western history for another millennium. Decades later, using advanced X-ray imaging and three-dimensional digital tomography, researchers were able to peer inside the calcified bronze blocks without disturbing their delicate structure, revealing the hidden teeth of 30 distinct gear wheels, the elegant differential assemblies, and thousands of tiny engraved letters that served as an instruction manual for reading the sky. This extraordinary artifact remains a quiet, enduring symbol of how deeply connected humanity has always been to the celestial realm. Long before glass lenses opened the distant depths of outer space to human vision, ancient minds used geometry, patient observation, and exquisite craftsmanship to bring order to their night sky, finding profound comfort in the discovery that the universe moves in steady, dependable cycles. As you rest in the calm of the present evening, the very same constellations that watched over those ancient craftsmen continue their slow, peaceful turn across the dark expanse of space. The moon completes its familiar journey through the quiet night, casting its soft, silver glow across land and sea, just as it did when bronze pointers tracked its path across hand-engraved dials thousands of years ago. The steady machinery of the cosmos moves without sound, friction, or haste, drawing the planets along their ancient, well-worn paths through the quiet dark. There is a deep, reassuring peace in knowing that behind the shifting details of our daily lives lies a timeless structure of order, rhythm, and light, inviting us to lay aside the burdens of the day, to quiet our thoughts, and to settle gently into the comforting, eternal rhythm of the night. As the soft, amber light of sunset gently recedes over the harbor of Alexandria, the ancient city settles into a peaceful, cooling twilight. Long shadows stretch across the wide stone avenues and marble porticos, while the gentle murmur of the Mediterranean Sea provides a steady, soothing rhythm against the shore. In the 4th century, this grand center of learning served as a quiet sanctuary where scholars dedicated their lives to unraveling the calm mysteries of the natural world, reading the movements of the earth and the sky like pages in a timeless manuscript. As the dusk deepens from warm gold to soft violet, the first evening stars begin to emerge, puncturing the darkening canopy with precise points of light. Within the quiet courtyards of the academy, surrounded by open archways that catch the night breeze, the atmosphere is filled with a profound sense of stillness and contemplation. Here, the pursuit of knowledge was not a hurried endeavor, but a slow, meditative practice of observing, measuring, and reflecting upon the underlying order of the universe. The scholar Hypatia walked these serene terraces, her thoughts attuned to the geometric elegance of the cosmos and the subtle harmony that governed the movement of every celestial body. She recognized that the night sky was far more than an inspiring spectacle. It was a grand, reliable clock whose unseen gears turned with perfect mathematical precision. Under her thoughtful guidance, the study of geometry, arithmetic, and astronomy merged into a single, cohesive vision of cosmic order, offering comfort and clarity to all who looked up into the vast, dark expanse. As the last remnants of daylight vanish entirely beyond the western horizon, the sky over Alexandria transforms into a deep, velvety canvas, illuminated by countless distant worlds, whose steady glow has watched over humanity since the beginning of time. In this tranquil environment, the ancient Skywatchers found a deep sense of stillness, knowing that the celestial cycles would continue their gentle, unhurried rotation night after night, bringing reassurance to a world below preparing for rest. To translate this abstract mathematical beauty into something tangible that could be held in the human hand, Hypatia turned her expertise toward the design and refinement of complex observational instruments. Primary among these was the astrolabe, a marvelous brass microcosm of the heavens that condensed the three-dimensional vault of the night sky into a portable disk of geometric perfection. Crafting such a tool required immense skill and patience, blending rigorous spherical trigonometry with delicate metallurgical artistry. The body of the instrument consisted of heavy, polished brass, carefully weighted, so that when suspended from a small silk ring, it hung completely plumb against the force of gravity. Upon its smooth, cool surface were etched concentric circles, altitude arcs, and coordinate grids corresponding precisely to the latitude of the observer, creating an enduring framework upon which the stars could be mapped. Over this base plate rested a pierced, decorative lattice known as the reedy, a delicate metal web whose slender pointers marked the exact positions of the brightest navigational stars. In 4th century Alexandria, the scholar Hypatia crafted precise brass astrolabes engraved with silver star maps, allowing night travelers to determine the exact hour simply by aligning a rotating ruler with the position of Vega. Each silver inlay gleamed softly in the faint lantern light, representing prominent celestial markers with exquisite accuracy and timeless beauty. On the reverse side of the instrument sat a straight, rotatable sight bar known as the alidade, fitted with tiny pinhole sights, through which a scholar or traveler could line up a target star against the night sky. By lifting the astrolabe by its suspension ring, sighting a bright star through the tiny apertures, and noting where the alidade crossed the finely graduated scales along the outer rim, one could instantly bridge the immense distance between human perception and cosmic time. The instrument felt heavy and substantial, a comforting piece of brass that transformed the overwhelming scale of the night sky into a manageable, elegant harmony. For the traveler resting beneath the vast desert skies of North Africa, or navigating the dark, calm waters of the Mediterranean, holding such an astrolabe brought a profound sense of security and quiet connection. Imagine standing upon a silent dunescape at midnight, surrounded by the cool, crisp air of the desert and the soft, motionless expanse of the wilderness. The world below is asleep, shrouded in gentle darkness, but high above, the celestial vault glows with brilliant, crystalline clarity. The constellation Lyra hangs gracefully near the zenith, its brightest beacon, Vega, shining with a cool, sapphire light that pierces the quiet dark like a solitary lantern. A weary merchant or sea captain, pausing along their journey, pulls the brass disc from a protective leather pouch. Holding the instrument steady by its top silk cord, they allow it to settle gently in the still air, letting gravity find its true vertical line. Peering through the small, aligned sights of the alidade, they slowly rotate the ruler until the bright, silver point of Vega aligns perfectly through the tiny pinholes. With a smooth turn of the reedy, the silver-mapped stars on the brass disc mirror the living sky overhead with flawless mathematical symmetry, reading the tiny, hand-engraved numerals where the ruler intersects the outer altitude ring. The traveler determines not only their exact location upon the curved surface of the earth, but the precise hour of the night. There is no urgency in this measurement, only a peaceful ritual of observation that confirms the traveler's place within the vast, orderly cosmos. The silver star maps, cool brass, and distant starlight meet in a quiet moment of absolute balance, offering comforting reassurance that even in the deepest, most isolated darkness, the heavens provide a trustworthy, beautiful guide to steer the way home. As the night continues its slow, majestic arc across the sky, instruments like Hypatia's astrolabe remind us of the enduring human desire to find harmony, structure, and peace within the cosmos. Long before the invention of glass lenses or automated clocks, these brass discs transformed the mysterious, swirling heavens into an accessible map of quiet beauty. They allowed early skywatchers to feel anchored in time and space, knowing that every rising star and setting constellation followed an unvarying, predictable path crafted by natural law. The bright star Vega, having served as a steady beacon for the traveler's astrolabe, slowly glides across the dark zenith, descending toward the western horizon in a motion so smooth and gradual it is imperceptible to a fleeting glance. To reflect upon such an instrument is to cross a quiet bridge over 16 centuries, connecting our present stillness with the thoughtful scholars of ancient Alexandria who sat under these very same constellations. The brass plates may grow cool in the evening air, and the silver star points may reflect only the softest gleam of starlight. But the fundamental relationship between human curiosity and the nocturnal sky remains entirely unchanged. As you rest now in the warm comfort of your surroundings, you can picture the dark Mediterranean waters lapping softly against the ancient stone quay of Alexandria, the gentle desert wind whispering through the palm fronds, and the steady, rotating sky cradling the sleeping world below in absolute peace. The stars continue their silent, eternal dance, unhurried and serene, inviting your thoughts to soften, your breathing to slow, and your mind to sink deeply into the calm, restorative expanse of sleep. As dusk settles softly over the ancient city of Ujjain in central India, the warm daytime air of the subcontinent gently yields to a deep, velvety stillness, inviting all eyes upward toward an expansive canopy of timeless stars. In this historic center of learning and trade, positioned along the prime astronomical meridian of ancient India, the night sky was understood not as a collection of distant mysteries, but as an intricate, living clockwork whose smooth, rhythmic motions brought a comforting sense of order and harmony to the world below. Long before glass lenses could reach into the deep ocean of space, skywatchers sat upon open stone terraces and along the quiet banks of the Kashipur River, patiently tracing the steady arcs of bright, wandering planets and watching the slow, majestic waxing and waning of the glowing moon. Amidst the gentle rustle of evening breezes and the quiet flicker of oil lamps illuminating parchment leaves, scholars sought to capture the hidden mathematical order governing the cosmos. It was within this atmosphere of quiet, meditative scholarship, around 628 CE in Ujjain, that the astronomer Brahmagupta compiled the Brahmasfuta Siddhanta, establishing precise sign tables and mathematical formulas to compute the nocturnal paths of planets and the exact timing of lunar eclipses by translating the curved trajectories of the celestial spheres into exact numerical relationships. His work revealed a profound and reassuring truth. The wandering lights of the night moved according to constant, elegant mathematical laws. To hold these mathematical tools was to realize that the darkness above was governed by an enduring geometry, where every star and planet traversed its appointed track across the heavens without haste or deviation. Through his meticulous tables, an astronomer sitting in the quiet of midnight could map the subtle drift of Jupiter through the constellations, or calculate days in advance the precise moment when the Earth's soft shadow would touch the face of the moon during a lunar eclipse. There was a deep and restful peace in this certainty, a quiet reassurance that the passage of the night was part of a perfectly balanced, predictable universe. The formulas recorded in Ujjain did not merely serve practical agricultural calendars or navigational needs. They deepened humanity's spiritual and intellectual connection to the cosmos, allowing the human mind to mirror the calm, unhurried precision of the heavens above. As the night deepened over the peaceful rooftops, these mathematical principles began their long journey outward across trade routes and oceans, carrying with them the understanding that the cosmos was a vast canvas of timeless mathematical grace, moving farther eastward across the ancient continent, along the peaceful trade routes and misty mountain passes that connected distant cultures. Another great tradition of skywatching flourished in the kingdom of Silla, situated on the southern expanse of the Korean peninsula. Here, nestled among gentle hills and fertile river valleys, lay the royal capital of Jeonju, a city where the observation of the heavens was woven into the very fabric of governance and daily life. Night after night, as a cool breeze whispered through the surrounding pine forests and bamboo groves, royal astronomers gathered to observe the celestial vault, seeking to harmonize earthly affairs with the serene rhythms of the stars. To facilitate this solemn and peaceful duty, master builders crafted an enduring monument of stone, designed specifically to capture the quiet beauty and mathematical order of the night sky. Built in 647 CE in Jeonju, Korea, the bottle-shaped stone observatory of Cheomseongdi was constructed from 362 granite blocks, one for each day of the lunar year, allowing royal skywatchers to quietly monitor nocturnal stars through an open central window. Standing gracefully against the dark horizon, the structure's smooth, elegant curves mirrored the soft contours of the celestial dome, while its carefully counted granite stones symbolized the complete cycle of time as measured by the moon's monthly journeys. Inside the central chamber, or resting upon its flat upper platform, observers sat in tranquil focus, watching as familiar constellations drifted slowly past the frame of the open window. The dense granite, cooled by the evening air, provided a stable, unchanging foundation from which to trace the subtle seasonal shifts of the stars. From the first delicate rising of spring constellations to the crisp, brilliant fields of midwinter stars. Through this open portal to the heavens, the Skywatchers noted the subtle wanderings of the planets, the gentle changing shades of the lunar surface, and the sudden, silent passage of meteors, standardizing their records over years of patient care. The observatory was not a place of noise or busy ambition, but a sanctuary of quiet reflection, where the simple act of looking upward became a shared ritual, connecting the royal court to the vast, silent expanse of space. The 362 granite blocks, laid layer upon layer with meticulous craft, stood as a physical testament to humanity's desire to anchor the fluid flow of time in stone, creating a timeless bridge between the earthly landscape and the infinite skies above. When we look back across the centuries at these early eras of astronomical discovery, from the sun-warmed plains of India to the cool stone valleys of Korea, we see a profound and shared human devotion to the quiet beauty of the night. In both Ujjain and Jeonju, early astronomers worked without the complex mechanical telescopes of the modern era, relying instead upon patient human eyes, deep mathematical insight, and stone structures built to endure through generations. These ancient observers understood that to watch the stars was to enter into a state of quiet contemplation, where the restless noise of daily life naturally faded away, replaced by the slow, majestic progression of the universe. The precise sign tables composed by Brahmagupta and the carefully stacked granite blocks of Cheomseongdi were different expressions of the exact same fundamental human impulse to seek meaning, structure, and peace within a cosmos defined by balance and eternal rhythm. Through their quiet, dedicated efforts, the night sky ceased to be an intimidating or mysterious void, becoming instead a familiar and trusted companion that guided farmers in their fields, navigators on the seas, and scholars in their studies. As time unfolded, the knowledge gathered in these ancient observatories softly rippled across continents, refining humanity's understanding of time and motion, and laying the quiet groundwork for future generations, who would build even sharper instruments to gaze deeper into space. Yet even as our tools have changed, the core experience of standing under the night sky remains entirely unchanged, a solitary, soothing practice of looking up at the stars and feeling a deep sense of stillness and wonder. The realization that men and women centuries ago stood under these very same constellations, calculating their paths with parchment and watching them through stone windows, brings a gentle warmth to our own night, reminding us that we are all part of an unbroken lineage of Skywatchers. As the hours drift gently onward and the stars continue their silent, unhurried passage across the dark, we can draw profound comfort from knowing that the cosmos moves with the same quiet grace it has possessed for ages, surrounding us with its soft, peaceful light and inviting us to sink into restful sleep. As twilight gently settles across the vast, rolling sands of Central Asia, the ancient oasis of Dunhuang softens into the quiet hues of evening, where the heat of the day yields to a cool, restorative breeze. Here, along the winding routes of the Silk Road, where travelers, merchants, and scholars have rested for generations beneath the quiet expanse of the heavens, the night sky opens like a vast and familiar canopy. Long before the invention of glass lenses or modern brass instruments, the human eye watched the stars with patient reverence, tracking their steady, rhythmic journeys across the velvet darkness. In the stillness of the desert, away from the clutter of city lights, the sky revealed itself in astonishing clarity, a shimmering tapestry of light that offered both practical guidance for travelers crossing uncharted terrain and profound solace to those contemplating the vast harmonies of the cosmos. Night after night, skywatchers observed how the constellations drifted overhead in predictable, elegant arcs, their fixed positions offering a sense of permanence amidst the ever-changing landscapes of Earth. The desert night possessed a unique stillness, a sanctuary where the rustle of wind through dry grasses and the soft sighing of resting camels framed the silent, majestic movement of the heavens. In this atmosphere of quiet contemplation, astronomers and scribes gathered their thoughts, seeking not only to understand the laws of the celestial spheres, but also to record them with painstaking beauty, ensuring that the fleeting brilliance of the night could be preserved on delicate parchment for generations yet to come. The cosmos was understood not as a distant or alien realm, but as an intimate companion to earthly life, governing the rhythm of agricultural cycles, the timing of seasonal migrations, and the quiet hours of evening rest. As darkness deepened, each prominent star became a beacon of calm regularity, inviting the watcher to slow their breath and sync their thoughts with the eternal cadence of the universe. Within the quiet libraries and scriptoriums of Tang Dynasty China, skywatching was both an art form and a sacred discipline, carried out with remarkable technical precision and artistic elegance. Scholars understood that to chart the stars was to map the very breadth of heaven, organizing the infinite celestial sphere into structured mansions, enclosures, and asterisms that mirrored the order of earthly society. Around 705 CE, along the Silk Road in Dunhuang, scholars painted a fine paper scroll featuring over 1,300 stars across 12 monthly charts, using red, black, and white ink dots to mark each celestial coordinate. This extraordinary document, crafted on fine mulberry paper with delicate brushstrokes, represented one of the most complete and accurate star maps of the ancient world. The deliberate choice of colored dots was not merely aesthetic. It reflected a deep historical awareness, using distinct colors to differentiate the stellar catalogs compiled by earlier master astronomers such as Shishen, Ganda, and Wu Xian. thereby unifying centuries of astronomical wisdom into a single, cohesive visual narrative. Each dot was positioned with exceptional care relative to polar coordinates and equatorial divisions, creating a reliable visual guide to the night sky as it shifted month by month throughout the solar year. The 12 monthly panels displayed the equatorial region of the sky in rectangular projections, capturing the gradual seasonal shift of the constellations above the horizon, while a final circular chart depicted the circumpolar stars that never set, remaining perpetually visible around the celestial pole. The ink dried slowly in the dry desert air, setting each star in its proper place with serene accuracy. To behold the scroll was to see the entire visible universe rendered in miniature, a testament to human curiosity and peaceful dedication. The quiet diligence required to produce such a work, dipping a fine brush into prepared inks, calculating positions by the light of a flickering oil lamp, and carefully placing over 1,000 individual marks, evokes a meditative rhythm, a serene communion between the scholar's hand and the distant fires of the cosmos. The practical and spiritual value of such sky maps reached far beyond the quiet walls of the Dunhuang scriptorium, offering a gentle map of time and space for all who looked upward, for the caravans preparing to journey across the silent dunes under the safety of night, knowing which constellations would rise and set provided a reliable compass and a comforting clock, assuring travelers that their path across the dark wilderness was aligned with the steady order of the cosmos. The celestial sphere was divided into 28 lunar mansions, small segments of the sky through which the moon made its monthly passage, creating a gentle lunar calendar that tracked the subtle passage of time day by day. Each night, as a new mansion rose into view, watchers could measure the progression of the season, sensing the subtle transition from the crisp skies of autumn to the deep, clear nights of winter. The Dunhuang map captured this dynamic celestial motion with subtle artistry, portraying the sky not as a static ceiling, but as a living, breathing harmony that rotated gently around the northern pivot star. The northern star sat motionless at the center of the circumpolar chart, a point of absolute stillness around which all other stars performed their slow, eternal dance. This central point of stability served as a comforting anchor for both astronomical study and philosophical reflection, reminding observers that amidst all movement and change, there exists an enduring axis of peace. The precision of the map allowed astronomers to predict celestial phenomena, track planetary movements, and align civil calendars with the movements of the sun and moon, ensuring that human activities remained in peaceful resonance with the grander cycles of nature. The soft texture of the paper scroll, designed to be unrolled section by section as the months unfolded, encouraged a contemplative, unhurried engagement with astronomical knowledge, inviting the reader to experience the night sky as an unfolding story told in ink and light. Eventually, this magnificent scroll was carefully rolled, bound, and placed within the dark, dry sanctuary of the Mago Caves, where it remained protected from light, moisture, and time for over 1,000 years. Sealed inside a hidden chamber among thousands of sacred texts, historical documents, and exquisite artwork, the star map lay in peaceful rest, preserving its vibrant red, black, and white ink dots untouched, while empires rose and fell across the surrounding lands. Its long slumber in the desert cave mirrors the timeless quiet of the stars themselves, which continue to shine above Dunhuang with the same calm, unhurried brilliance as they did when the unknown scribe first touched brush to paper. Looking up at the night sky today, one feels a profound connection across the centuries to those ancient skywatchers who sat beneath the same celestial dome, finding wonder and quiet reassurance in the orderly dance of the cosmos. The stars they charted so lovingly, the bright beacons of Vega and Altair, the sweeping arc of the Big Dipper, and the faint clusters scattered along the Milky Way, remain unchanged, continuing their nightly journey with effortless grace. As the night deepens and the world grows quiet, the memory of that ancient scroll reminds us of the enduring human desire to observe, to understand, and to find peace in the vastness of the universe. The gentle rhythm of the night carries on, a slow and rhythmic lullaby written in starlight, inviting the mind to rest, to let go of the day's concerns, and to drift peacefully into sleep under the watchful, eternal care of the starry heavens. As the night deepens over the quiet curves of the Euphrates River, the ancient landscape of Syria settles into a restful and meditative stillness. In the historic city of Raqqa, during the flourishing height of the Islamic Golden Age, the night air carries a cool, gentle breeze that rises from the slow-moving waters, softening the heat left behind by the desert day. Above the flat rooftop terraces, tall minarets, and whitewashed stone arches, the heavens open into a vast, unblemished canopy of velvet dark, untouched by modern artificial light, and brilliant with the steady, familiar geometries of distant suns. Here, scholars of the medieval Islamic world gathered under the silent cosmos, carrying forward an enduring legacy of scientific inquiry that gracefully bridged the traditions of ancient Greece, Babylonia, Persia, and India. In this golden era, astronomy was viewed not merely as an abstract science of calculation, but as a peaceful contemplation of cosmic order, a tranquil mapping of celestial time and rhythm that allowed desert travelers to navigate trade routes across vast, shifting sands, farmers to mark the quiet turning of planting and harvest seasons, and communities to align their daily lives with the silent motion of the sun. The night sky served as an eternal, soothing clock, ticking with the slow, predictable wheeling of stars across the curved horizon. As twilight faded into deep indigo, observers would step out onto elevated observation platforms, surrounded by finely calibrated brass instruments that glinted faintly in the soft glow of oil lamps. The atmosphere in these early skywatching sanctuaries was defined by patience, quiet discipline, and a profound reverence for the steady, unhurried patterns of the natural world. Far removed from the clamor of busy marketplaces, astronomers spent long hours in gentle solitude, observing how each star rose and set with absolute consistency, tracing the golden arc of the ecliptic and cataloging the subtle shifts that occurred across months, years, and decades. In this serene refuge along the riverbank, astronomical observation became a quiet, meditative practice, linking the immediate ground beneath one's feet to the infinite reaches of the celestial sphere, encouraging a peaceful state of wonder that invited the human mind to rest in the grandeur of a harmonious and orderly universe. Among the most dedicated and influential skywatchers of Raqqa was the Syrian astronomer Abu Abdullah Muhammad ibn Jabir ibn Sinan al-Raqi al-Harani al-Sabai, known to history simply as Al-Battani or Al-Battanius to the scholars of medieval Europe. Night after night, season after season, he ascended to his rooftop terrace, overlooking the calm, dark ribbon of the Euphrates, to study the delicate mechanics of the heavens. Equipped with large armillary spheres, intricate astrolabes, mural quadrants, and tall wooden sighting tubes, Al-Battani brought an unprecedented level of care to measuring the precise coordinates of fixed stars and the subtle tilt of the sun's path across the sky. He understood with quiet clarity that determining the true length of a solar year required far more than a few brief seasons of measurement. It demanded a lifetime of disciplined patience, comparing the sun's elevation at solstices and equinoxes across decades to eliminate minor errors caused by atmospheric refraction or subtle instrument variations. Through long, peaceful nights filled only with the soft rustling of palm fronds and the low, rhythmic murmur of the river below, he carefully recorded the exact moments when celestial bodies crossed the meridian, painstakingly cross-referencing his empirical findings with the classical manuscripts inherited from Ptolemy's Almagest asterisk. Over the course of many quiet years, Al-Battani recognized that several fundamental astronomical constants accepted by earlier Greek observers were slightly inaccurate, having drifted out of alignment over time, or having been measured with less refined instruments. With unwavering focus and meticulous mathematical precision, he set out to recalculate the fundamental rhythms of celestial motion, establishing a far more reliable foundation for understanding our planet's journey around the sun. Around 900 CE, along the Euphrates River in Raqqa, Syrian astronomer Al-Battani calculated the length of the solar year as 365 days, 5 hours, 46 minutes, and 24 seconds, refining ancient star charts across 40 steady seasons. His calculation was extraordinarily accurate, differing from modern atomic measurements by only a tiny handful of minutes. A remarkable achievement accomplished entirely through non-telescopic sightlines and handcrafted tools. This extraordinary milestone was not achieved through sudden, dramatic revelations, but through the calm, steady accumulation of 40 years of nightly observation, demonstrating how true understanding unfolds slowly and peacefully from a lifetime of quiet dedication. Beyond determining the precise length of the solar year with such extraordinary accuracy, Al-Battani's long years of patient observation along the Euphrates yielded several other profound insights that reshaped humanity's understanding of cosmic geometry. By comparing his own carefully recorded solar measurements with those preserved by ancient astronomers who had lived centuries before him, he discovered that the solar apogee, the point in the sun's apparent orbital path where it reaches its greatest distance from Earth, was not fixed permanently in space as Ptolemy had assumed, but was instead shifting slowly and continuously forward through the zodiacal constellations over great spans of time. To describe these delicate and complex motions with absolute mathematical clarity, Al-Battani introduced groundbreaking trigonometric methods to replace the cumbersome geometric chord calculations that had been used since antiquity. He was among the first mathematicians to systematically develop and apply sine, cosine, tangent, and cotangent functions to astronomical problems, creating elegant mathematical tools that allowed complex three-dimensional movements of celestial spheres to be calculated with remarkable smoothness, simplicity, and grace. These mathematical innovations elevated astronomy into a highly refined, predictive science, enabling future skywatchers to forecast planetary positions and eclipses with unmatched confidence. In the quiet warmth of his study, surrounded by manuscripts written in fine Arabic calligraphy and charts drawn with delicate precision, Al-Battani cataloged over 400 stars, updating their celestial positions to account for the slow, silent precession of the equinoxes. Every line of numbers in his masterwork, the astronomical handbook known as the Asterisk Zij al-Sabi Asterisk, reflected a profound alignment between human intellect and the natural cosmos, demonstrating that beneath the apparent complexity of the night sky lay an enduring, beautiful simplicity that brought clarity and calm to all who studied it. The quiet, enduring legacy of Al-Battani's work rippled gently across centuries and continents, traveling far beyond the banks of the Euphrates to illuminate the future of global science. Long after his passing in 929 CE, his astronomical tables and theoretical writings were translated into Latin as Asterisk de Motu Stellarum, becoming foundational texts in European universities and monastic centers of learning throughout the Middle Ages and the Renaissance. Centuries later, when Nicolaus Copernicus began formulating his heliocentric model of the solar system, he drew extensively upon Al-Battani's precise calculations of the solar year and the motion of the solar apogee to verify his own groundbreaking theories. Citing the Syrian astronomer with deep admiration and gratitude, later figures such as Tycho Brahe, Johannes Kepler, and Galileo Galilei similarly relied upon Al-Battani's refined observations as they constructed the modern laws of planetary motion and prepared humanity for the invention of the telescope. Today, as we look up into the tranquil night sky, we are connected across time to those peaceful evenings in Raqqa, where a solitary scholar watched the stars drift across the Syrian dark. The same constellations that guided Al-Battani over 11 centuries ago continue their silent, majestic rotation above us, offering a soothing reminder of the permanence, beauty, and quiet order of our universe. As the world grows quiet and twilight turns to peaceful sleep, the story of Al-Battani invites us to breathe slowly, let go of the day's concerns, and rest peacefully under the gentle, eternal harmony of the cosmos. As dusk settles softly across the ancient landscapes of the earth, the evening sky gradually shifts from soft shades of rose and gold into a deep, comforting indigo, inviting the restless mind to settle into a quiet, restful stillness. Long before the invention of glass lenses or modern optical instruments, early astronomers across the globe gazed up into the night with a calm, patient wonder, seeking to map the silent order of the heavens. In the 10th century, within the tranquil oasis city of Isfahan in Persia, the desert air was cool, dry, and exceptionally clear, offering an unobstructed window into the vast expanse of space. Here, amidst the quiet courtyard bowers and high flat roofs of the city, the distinguished Persian scholar Abd al-Rahman al-Sufi spent countless peaceful hours examining the stars. With a deep reverence for the cosmos, he set out to update and refine the ancient astronomical catalogs left behind by earlier generations, meticulously measuring the brightness, color, and precise position of every star visible to the naked eye. In the serene stillness of midnight, while the city below lay asleep, al-Sufi turned his attention to the constellation of Andromeda, high in the northern sky. As his eyes adjusted to the deep darkness, he noticed something extraordinary hovering near one of the constellation's key stars, a delicate, hazy patch of light that did not twinkle like the surrounding stars, but instead glowed with a faint, ghostly luminescence. He observed this subtle phenomenon again and again over many clear nights, taking care to describe its delicate appearance and precise location in his masterwork, the Asterisk Book of Fixed Stars Asterisk. Around 964 CE in Isfahan, Persian astronomer Abd al-Rahman al-Sufi recorded the earliest known observation of the Andromeda galaxy in his Book of Fixed Stars. describing it as a soft, faint cloud hovering near the star New Andromedy. This gentle, unpretentious recording was the very first time in human history that our neighboring galaxy was documented, a colossal island of hundreds of billions of stars, lying over 2 million light-years away, yet perceived by a patient astronomer in Persia as nothing more than a quiet cloud floating softly in the night sky. The beauty of Al-Sufi's discovery lay not in complex technology, but in the quiet art of attentive watching, a practice shared by skywatchers across every corner of the ancient world. While scholars in Isfahan catalogued the night sky with ink and parchment, communities half a world away were carving their own deep understanding of celestial rhythms directly into the living rock of the earth. Far across the Atlantic Ocean, on the expansive desert plateaus of the North American Southwest, the ancestral Puebloan people lived in profound harmony with the cycles of the sun, moon, and stars. In the remote valley of Chaco Canyon, surrounded by dramatic red sandstone cliffs, flat-topped mesas, and open desert skies, the cosmos felt intimately connected to daily life. The high desert air carried the clean, grounding scents of sagebrush, juniper, and dry earth, growing stillness as the heat of the afternoon yielded to the cool calm of twilight. For the ancestral Puebloans, observing the sky was essential for guiding their agricultural seasonal cycles, marking the times for planting corn, harvesting, and gathering for communal gatherings. They watched the sun's path shift along the horizon day by day, noting how shadows lengthened and shortened across the canyon walls as the seasons turned. To mark the pivotal turns of the solar year with absolute precision, they sought out high, sacred places where the relationship between sunlight and shadow could be captured in stone. Their gaze turned toward Fajada Butte, a striking, solitary rock formation that rises hundreds of feet above the flat canyon floor, standing like a silent sentinel watching over the desert below. On the windswept summit of this isolated butte, early skywatchers set about creating one of the most subtle and awe-inspiring solar calendars ever devised by human hands. Near the very top of Fajada Butte, nature had left 3 massive sandstone slabs leaning upright against a smooth cliff face, separated by narrow, vertical gaps that allowed thin slivers of sunlight to pass through. Recognizing the unique potential of this natural formation, ancestral Puebloan astronomers worked with profound reverence for the land, carefully arranging and refining the position of these immense stones to create a precise instrument for measuring the celestial year. Behind the giant slabs, hidden in the soft, protective shadow of the cliff overhang, they carved a beautiful spiral petroglyph directly into the smooth rock wall. A delicate, 9-ringed concentric design that mirrored the unfolding journey of time, the movement of the heavens, and the cyclical return of the seasons. Throughout the changing year, as the sun traversed the sky at varying angles, The 3 sandstone slabs acted as natural light shapers, filtering the intense desert sun and projecting narrow, changing ribbons of brightness onto the shaded petroglyph behind them. During the winter solstice, 2 shafts of light would frame the outer edges of the spiral, while at the equinoxes, a smaller light beam would pass through a secondary carving. But the most breathtaking moment of this celestial dialogue occurred at the exact height of summer, when the sun reached its absolute zenith in the sky. Around 1000 CE, at Fajada Butte in Chaco Canyon, ancestral Puebloan skywatchers positioned 3 massive sandstone slabs to cast a single, silent dagger of midday sunlight directly through the center of a spiral petroglyph on the summer solstice. For a few brief, tranquil minutes at solar noon, this slender shaft of light pierced the exact center of the spiral like a beam of liquid gold, marking the longest day of the year with quiet perfection before slowly drifting away and dissolving back into the cool, peaceful shadows of the cliff face. These 2 ancient stories, one originating under the quiet, starlit domes of 10th century Isfahan, and the other carved into the sun-warmed sandstone of Chaco Canyon around the turn of the 1st millennium, illustrate a fundamental human desire to connect with the quiet rhythm of the universe. Though separated by vast oceans, differing cultures, and thousands of miles of terrain, Abd al-Rahman al-Sufi and the ancestral Puebloan astronomers shared a profound capacity for still, patient observation. Neither required complex machinery or intrusive instruments to perceive the subtle harmonies of the cosmos. Instead, they relied upon keen human vision, deep patience, and an enduring reverence for the sky above. In Persia, a scholar's steady hand recorded a faint, soft cloud of starlight that had traveled across millions of light years to reach his eyes, preserving for posterity our first glimpse of the Andromeda Galaxy. In the high desert of New Mexico, indigenous skywatchers harnessed the light of the sun itself, allowing a single beam of midsummer light to mark the turning of the seasons upon a stone spiral. Both achievements invite us to slow down, to breathe deeply, and to remember that we are part of the very same cosmos that guided ancient eyes so long ago. As the night deepens and the world draws its quiet curtains shut, we can find comfort in knowing that the same stars Al-Sufi cataloged still shine softly in the dark above, and the same sun still rises with gentle reliability each morning. The vast heavens continue their silent, eternal dance, cradling the sleeping earth in a timeless blanket of peace, light, and enduring calm. In the quiet expanse of the 11th century, across the vast lands of Central and South Asia, a serene culture of inquiry flourished under open skies, preserving the celestial wisdom of the ancient world while quietly charting new pathways toward understanding. Astronomers of this golden era viewed the heavens not as a realm of chaos or distant mystery, but as a magnificent, orderly clockwork, whose silent mechanisms could be comprehended through patient observation, and the pure language of geometry. Centuries earlier, scholars in ancient Alexandria had estimated the circumference of the globe by comparing the sun's shadow at two widely separated locations at high noon, a heroic effort that required measuring long, exhausting distances across desert sands between distant cities. Yet, as the generations passed, thinkers pondered whether there might exist a more elegant way to measure the curve of our world without traversing hundreds of miles of terrain. Among these contemplative minds was Abu Rayhan al-Biruni, a scholar of extraordinary breadth and quiet dedication, whose life was defined by an unhurried, systematic search for truth. Al-Biruni recognized that the geometry of the earth was reflected not only in the distant shadows of midday, but also in the very way the landscape fell away into the horizon when viewed from a great height. He understood that if one stood upon a high mountain overlooking a flat plain, the line where the earth met the sky would not lie at a true right angle to a plumb line, but would instead drop slightly below it. A minute, delicate dip caused by the gentle curvature of the planet's surface. To capture this elusive angle required an intellect of profound patience and an instrument of exquisite craftsmanship, as well as a setting where the natural landscape provided a clear, uninterrupted view across vast stretches of low-lying land. In the calm stillness of the mountains, far from the noise of city markets, Al-Biruni spent long seasons studying the light of the stars and the mathematical relationships that bound the terrestrial realm to the celestial vault above. He saw mathematics not as an abstract burden, but as a soothing bridge connecting human perception to the hidden harmonies of nature, allowing the mind to measure the immense contours of the world while standing still upon a single quiet summit. As night descended over the mountain ranges, bringing a cool air that cleared the atmosphere, he would gaze up at the slow, majestic rotation of the constellations, knowing that every star held its place within a grand, unified structure that invited quiet contemplation. The ideal opportunity to test his revolutionary geometric vision arrived in the early decades of the 11th century. Among the rugged, weathered heights of the Salt range near the historic stronghold of Fort Nandana. Perched high upon these quiet mountain cliffs, overlooking the vast, sun-softened expanse of the Punjab plains that stretched out like an emerald ocean toward the distant horizon, the landscape offered an unparalleled vantage point for measuring the world. The air at this elevated altitude was remarkably still and clear, free from the thick haze of the river valleys below, providing an unobstructed view of the infinite space where the curving earth dissolved into the blue haze of the sky. Stepping out onto the stony promontory in the quiet chill of early morning, Al-Biruni held in his hands a brass astrolabe, a beautifully crafted instrument of bronze and brass, etched with fine, delicate gradations, celestial coordinates, and sighting vanes that gleamed softly in the rising light. His method unfolded in 2 peaceful, deliberate steps, each requiring rigorous precision, yet executed with a meditative calm. First, using the principles of triangulation, he determined the precise vertical height of the mountain peak above the flat plain below. By taking sight lines from 2 different positions along the base of the mountain and measuring the angle of elevation to the summit. Once the height of his mountain sanctuary was established with absolute mathematical certainty, Al-Battani turned his attention to the most delicate measurement of all: the tiny, almost imperceptible angle between the true horizontal line perpendicular to his plumb line and the visible edge of the distant horizon around 1021 CE near Fort Nandana. Scholar Al-Battani measured the subtle dip of the horizon from a quiet mountain peak, using a brass astrolabe to calculate the Earth's radius within 15 miles of its true measure. Through a single, masterfully designed trigonometric equation relating the mountain's elevation and the cosine of that minute horizon dip, he derived the dimensions of the entire sphere of the Earth without ever needing to step foot across the vast plains spreading out beneath him. The extraordinary accuracy of his calculation stood as a testament to what could be achieved through pure reason, elegant geometry, and meticulous observation, where earlier methods required teams of surveyors walking thousands of paces through difficult terrain. Al-Battani's method transformed the mountain peak itself into a giant mathematical instrument, using the natural contours of the Earth to reveal its own hidden scale. The significance of Al-Battani's quiet breakthrough extended far beyond the physical boundaries of Fort Nandana, casting a soothing, illuminating light across the whole field of astronomy and geography. By establishing a remarkably precise measure for the Earth's radius, astronomers were empowered to calculate the true physical scale of celestial phenomena with unprecedented confidence, grounding their models of the cosmos upon a reliable terrestrial foundation. When the size of our home planet is known with exactness, the apparent movements of the moon, the sun, and the wandering planets can be translated into actual physical distances, revealing a cosmos that is vast, orderly, and deeply harmonious. For Al-Battani, completing these calculations was not an occasion for grand display, but a moment of quiet gratitude and deep intellectual contentment. In the quiet hours after his measurements were recorded, as the golden light of dusk faded into the deep indigo of twilight, he would remain upon the mountain peak, watching the first evening stars emerge one by one in the darkening sky. The brass of his astrolabe, resting gently in its protective leather case, retained the faint warmth of his hands, while the cool mountain breeze whispered softly through the ancient pines and stone outcrops of the fortress. Looking down at the peaceful plains far below, where small village fires began to twinkle like fallen stars in the growing darkness, the scholar felt a profound sense of unity between human existence and the grand, spherical majesty of the Earth resting beneath the heavens. The planet beneath his feet was no longer a flat, mysterious plain lost in mist, but a magnificent, perfectly measured sphere suspended gracefully in the cosmic void, turning silently through space on its endless journey. As we reflect upon that calm morning near Fort Nandana so many centuries ago, there is a deep, comforting stillness in realizing how much of our understanding of the universe was built through such quiet, patient moments of observation. Long before the invention of electric lights or modern machinery, human beings sat beneath the very same stars that grace our night sky today, using simple brass instruments, clear minds, and an abiding sense of wonder to unlock the fundamental truths of our existence. Al-Biruni's work reminds us that true discovery does not always require loud commotion. Often, it requires only a quiet height, a clear view of the horizon, and the willingness to look closely at the gentle curves of the natural world. The legacy of his measurement drifted softly down through the centuries, inspiring generations of later skywatchers who would eventually turn their eyes toward the deeper secrets of the nighttime sky. But on this night, we can let our minds linger on the tranquility of that ancient mountain peak, where the air is cool, the wind is gentle, and the world stretches out in a smooth, continuous sphere of peace beneath the quiet canopy of heaven. The stars continue their slow, reassuring drift across the velvet dark, constant and calm, watching over the earth just as they did when Al-Biruni rested his astrolabe and gazed into the infinite night. The geometry of the earth and sky remains whole, balanced, and serene, inviting us to rest beneath the timeless, gentle harmony of the cosmos. As night settled across the fertile floodplains of the Nile, the city of Cairo rested beneath a vast canopy of clear, dustless air, where the ancient stars shone with an unhurried, steady luminescence. Throughout the vibrant centuries of the Islamic Golden Age, generations of patient scholars had turned their eyes toward this dark expanse, preserving the mathematical legacies of antiquity while charting the gentle, predictable paths of planets and constellations across the sky. In grand observatories, quiet courtyards, and rooftop terraces across the Islamic world, astronomers adjusted delicate bronze astrolabes and calibrated grand armillary spheres, tracing the nocturnal arc of fixed stars with meticulous care. Yet, to truly understand the underlying mechanics of the cosmos, one needed to understand not merely where the celestial bodies moved, but how their delicate light traveled across the vast emptiness to meet the human eye. In the peaceful solitude of private libraries and scholarly retreats, study was conducted with a serene, methodical devotion, free of haste, where geometry, mathematics, and natural philosophy merged into a quiet pursuit of cosmic truth. Scholars recognized that the rays of light flowing from the sun, the soft glow of the moon, and the subtle glimmers of distant wandering worlds held hidden physical laws waiting to be uncovered through quiet reflection and precise experiment. The night air was cool, carrying the gentle scent of river water, jasmine, and dried reed paper, as thinkers pondered the true nature of visual perception and the paths that illumination took through air and shadow. Rather than relying solely on abstract theory or ancient texts, this era nurtured a deep reverence for direct, carefully constructed observation, setting the stage for a profound transformation in how humanity would come to examine the heavens. Every shadow cast across a marble sundial, every soft beam filtering through an arched stone window, offered a whisper of physical principles that governed both the earthly realm and the celestial spheres above. It was a golden age of quiet inquiry, when the study of the heavens became intrinsically intertwined with the study of light itself, laying a tranquil foundation for all the optical wonders that were yet to come in the long, unfolding story of astronomy. Among these dedicated seekers of knowledge was a thoughtful scholar whose patient inquiries would forever alter humanity's relationship with light and space. Working in the stillness of his study, removed from the noise and distraction of the bustling metropolis outside, he sought to untangle the long-standing mystery of how vision occurs and how light behaves when passing through narrow openings. In 1028 CE in Cairo, scholar Ibn al-Haytham darkened a quiet room and carved a tiny pinhole in the shutter, projecting a soft, inverted image of a solar eclipse onto a clean white sheet of paper. In that tranquil moment, as the moon slowly traced its path across the solar disk, outside in the bright afternoon sky, the scholar watched the cosmic event unfold safely within the cool, muted shadows of his chamber, completely removed from the blinding brilliance of the open sky. The delicate crescent of sun, flipped upside down by the natural geometry of light traveling in straight paths through the tiny aperture, revealed the fundamental mechanics of what would come to be known as the camera obscura. This simple yet profound demonstration proved beyond doubt that rays of illumination move continuously from external objects, crossing through small openings without losing their inherent spatial order, to form a clear and faithful representation upon a waiting surface. By observing this silent projection, Ibn al-Haytham did not merely protect his vision from the sun's intense glare. He established an empirical method for capturing the subtle movements of the heavens without distorting their pristine form. He observed how the softness of the image depended on the size of the hole, balancing clarity with luminescence in a way that felt almost magical, yet was entirely grounded in the mathematical nature of light. The quiet room became a haven of peaceful inquiry, where the enormous scale of a solar eclipse was gently miniaturized and brought down to rest upon a humble page of paper, bridging the immense distance between celestial mechanics and human perception in a single, quiet beam of light. This gentle experiment was only one of many detailed within Ibn al-Haytham's masterwork on optics, a multi-volume text that would wander across languages, cultures, and continents over the subsequent centuries, quietly reshaping how natural philosophers understood the act of seeing. He demonstrated with mathematical elegance that starlight and sunlight refract when passing through media of varying density, explaining why celestial bodies appear slightly displaced near the horizon as their rays journey through the Earth's soft blanket of atmosphere. His meticulous studies of curved glass surfaces, water-filled glass spheres, and the subtle bending of light laid the essential theoretical groundwork that would later inspire natural philosophers to fashion lenses and combine them into instruments of magnification. Long before Western glassmakers polished the first spyglass, the principles governing how light converges, expands, and forms focused images were recorded in these calm, analytical treatises. Scholars across Europe and the East began to realize that the human eye itself functioned much like a darkened chamber, collecting the delicate beams emitted by distant fires and focusing them into meaningful form upon a sensitive backdrop. This realization transformed astronomy from a passive recording of visible points into an active exploration of optical physics, encouraging future generations to think of light as a measurable, bendable medium that could be gathered, concentrated, and directed. The idea that a simple aperture or shaped glass could reveal details invisible to the naked eye began to take root in the collective consciousness of skywatchers across the world, growing softly over time like a seed planted in rich, quiet soil. Through these patient demonstrations, the gap between the observer and the observed grew narrower, suggesting that the vast mysteries of the cosmos could be drawn down, examined, and understood within the tranquil space of a scholar's room. As the centuries drifted onward, the memory of those peaceful Cairo afternoons remained woven into the fabric of astronomical progress, a quiet reminder that the greatest discoveries often begin in moments of silent, undisturbed attention. The soft projection on that sheet of paper served as a gentle harbinger of the optical revolution that would eventually place glass lenses between human eyes and the night sky, opening vast new depths of space to human wonder. Yet even as instruments grew more complex and telescopes grew larger, the core experience of the astronomer remained rooted in that same serene stillness, sitting quietly in the dark, allowing light from distant worlds to travel across millions of miles to reach a quiet focal point. Starlight continues its unhurried journey through the void, moving in straight, perfect lines until it encounters a lens, a mirror, or simply an open window high above a resting world. The ancient skywatchers understood that to observe the universe is to participate in a timeless, restful dialogue with illumination itself, receiving the faint messages sent by stars that burned long ago. The quiet discipline of observing light in a darkened chamber taught humanity that nature reveals her deepest secrets not to those who rush, but to those who wait in patient silence. As night deepens over mountains, valleys, and quiet cities, the sky remains a vast, open chamber of light, holding its secrets with a gentle patience, waiting for those who pause, darken their surroundings, and listen to the quiet harmony of the cosmos. As dusk settled gently over the sprawling imperial capital of Kaifeng during the middle of the 11th century, the vibrant energy of the Song dynasty softened into a quiet, meditative twilight. High above the darkened rooftops, courtyard gardens, and serene waterways of the city, the imperial observatory rose toward the heavens, offering a tranquil sanctuary for those who sought to trace the eternal choreography of the stars. In this place of stillness and careful reflection, the renowned scholar and polymath Shen Qiu dedicated himself to studying the silent mechanisms of the night sky. For centuries, skywatchers had held a deep-seated belief that the bright star sitting near the northern zenith was entirely fixed in place, serving as the true, motionless axis around which the whole celestial sphere rotated. Yet Shen Qiu, guided by a spirit of patient empirical inquiry, suspected that the relationship between the physical star and the true mathematical pole was somewhat more complex. To investigate this subtle question, he designed an elegant observational instrument, a long wooden aiming tube with a slightly widened interior bore, mounted carefully to allow smooth, repeatable alignments night after night. Standing on the observatory platform amidst the cool evening air, with water clocks measuring the slow drip of time beside him, he systematically traced the tiny path of the star across the velvet dark. Over many consecutive weeks, as summer faded into the crisp chill of autumn, he logged the exact positions of the light relative to his wooden sight, carefully plotting its minuscule nightly arc. In 1074 CE in Kaifeng, Song dynasty scholar Shen Qiu used a widened wooden aiming tube over 3 months of quiet night observations, discovering that the North Star was positioned 3 degrees away from the true celestial pole. This profound discovery revealed that the celestial pivot was not a visible point of light, but an unseen geometric center around which the star drifted in a tight, harmonious circle. Shen Qiu recorded his findings with characteristic calm and clarity, enriching the astronomical traditions of East Asia with a new layer of precision. His work served as a peaceful reminder that the universe unfolds through quiet subtlety, rewarding those who watch the night with patience, humility, and enduring wonder. Moving across continents to the western expanse of the Islamic world, a parallel spirit of astronomical inquiry flourished in the vibrant cultural crossroads of Al-Andalus. Nestled high above a dramatic bend in the Tagus River, the ancient city of Toledo rested under clear, indigo skies, its stone arcades and peaceful courtyards bathed in the soft glow of moonlight. In this famous seat of medieval learning, scholars of diverse backgrounds worked side by side, translating ancient texts, refining mathematical tables, and constructing exquisite instruments designed to measure the movements of the sun, moon, and planets. Astronomy in Toledo was treated as both a rigorous science and a contemplative art, a gentle pursuit that connected the terrestrial realm to the orderly geometry of the cosmos. As night fell over the city's quiet streets, astronomers ascended to their rooftop terraces, holding brass instruments up to the stars to measure their altitudes above the horizon. The traditional astrolabe had long been the primary tool for such work, acting as a portable model of the heavens that could tell time, predict the rising of constellations, and assist in navigation. However, standard astrolabes suffered from a practical limitation. Their internal plates, or tympans, were engraved for specific geographic latitudes, requiring observers to manually swap out engraved metal discs whenever they traveled to a new location. In the quiet workshops of Toledo, where master craftspeople blended metalwork with advanced geometry, astronomers sought a more elegant and unified solution. They envisioned a single instrument that could encapsulate the entire sphere of the heavens without the need for interchangeable parts, allowing a traveler or skywatcher to read the positions of the stars effortlessly, regardless of where on Earth they stood. The air in these workshop courtyards was filled with the gentle scrape of copper tools against brass plates, as scholars spent long evenings calculating the intricate stereographic projections required to compress the three-dimensional celestial vault onto a flat, two-dimensional surface. It was an era when scientific progress unfolded not in rapid leaps, but through the quiet, devoted craftsmanship of individuals who found solace in the steady harmony of geometry and the nocturnal sky. At the center of this golden age of Andalusian astronomy was the brilliant instrument maker and mathematician Abu Ishaq Ibrahim al-Zarqali, known to later European traditions as Arzashel. Working with extraordinary artistic sensitivity and mathematical rigor, al-Zarqali set out to solve the long-standing limitation of multi-plated astrolabes by inventing a truly universal instrument, rather than relying on separate plates customized for specific northern or southern latitudes. He developed a groundbreaking design that used a single, highly sophisticated stereographic projection centered on the equinoxes. This monumental achievement required engraving intricate networks of intersecting arcs, latitude circles, and celestial grids directly onto a single plate of polished brass. The resulting device was a masterpiece of precision and beauty, holding within its gleaming surface the capacity to calculate celestial coordinates for any location on Earth. Around 1080 CE in Toledo, Andalusian astronomer al-Zarqali crafted the Azafia, an advanced universal brass astrolabe engraved with delicate stereographic grids that enabled night skywatchers to compute celestial coordinates at any latitude without swapping instrument plates. The Azafia represented a profound leap forward in instrument design, combining portability with unprecedented versatility. When held up against the dark canopy of the night, fine brass reticle caught the pale light of the stars, allowing skywatchers to measure planetary positions, track the drift of constellations, and calculate exact time with smooth, effortless grace. The elegance of the instrument lay not only in its technical perfection, but in the peaceful clarity it offered to those who studied the heavens. A traveler resting under the open sky in North Africa, Syria, or Southern Europe could hold the same brass disc, look up at the familiar stars, and feel immediately connected to the unified order of the universe. In the centuries that followed, the Asaphia was copied, translated, and praised across both the Islamic world and medieval Europe, leaving a quiet, lasting mark on the evolution of navigational and observational tools. Through the patient efforts of scholars like Shen Kuo in the East and Al-Zarqali in the West, the 11th century became a quiet golden bridge in human understanding, a time when wooden tubes and brass plates revealed the hidden precision of the cosmos, guiding the human spirit into a calm, restive appreciation of the infinite night. As twilight fell softly across the ancient city of Kaifeng, the administrative heart of the Northern Song dynasty gradually hushed its daytime bustle, settling into the tranquil quiet of the evening. High above the courtyard roofs and tiled eaves, the night sky began to reveal its vast and timeless expanse, unfolding a velvet blanket of stars that had guided travelers, farmers, and scholars for generations. In imperial China, astronomy was far more than an academic pursuit. It was viewed as a sacred responsibility to maintain harmony between the earth below and the heavens above. The emperors commissioned dedicated institutions of skywatchers who spent their lives observing the night sky with unwavering patience and quiet reverence. They mapped the stars into intricate constellations and lunar mansions, noting every subtle shift in planetary positions, every gentle passage of comets, and every rare, luminous guest star that appeared temporarily in the darkness. To these ancient observers, the sky was a seamless, living organism, moving with a predictable grace that mirrored the ideal order of society. Time itself was measured by the turn of the cosmos, tracked by shadow paths across sundials during the day, and by the rising and setting of prominent stars throughout the night. Yet, as dark hours lengthened and seasons shifted, astronomers sought increasingly refined methods to mirror this celestial motion continuously, dreaming of a mechanism that could capture the silent, eternal revolution of the stars and bring it down into a physical form that never rested. In the quiet atmosphere of the observatory courtyards, surrounded by the cool night air and the soft whisper of wind through ancient trees, scholars contemplated how to bridge the realm of mortal craftsmanship with the infinite rhythm of the firmament. This dream of uniting time, water, and starry motion achieved its most celebrated realization through the brilliance of a remarkable statesman and scholar whose work marked a golden age of medieval innovation. In 1092 CE in Kaifeng, polymath Su Song constructed a 35-foot wooden clockwork tower driven by dripping water, inside which a heavy bronze armillary sphere turned steadily throughout the night to track the stars. Rising majestically into the night sky, this pagoda-like structure housed an intricate interior world of hand-carved gears, wooden axles, counterweights, and water vessels, all engineered with breathtaking precision. At the heart of the apparatus was a pioneering escapement system that regulated the force of gravity and liquid flow, allowing energy to be released not in a continuous rush, but in tiny, perfectly measured intervals. Water was fed into a reservoir at a controlled rate, trickling down into small scoops attached to the rim of a large wooden water wheel. As each scoop filled to its exact capacity, its weight tripped a delicate balance lever, allowing the wheel to rotate forward by a single spoke before a wooden latch caught it once again with a subtle, rhythmic click. This continuous, hypnotic dripping and releasing provided the steady heartbeat of the entire tower, turning complex gear trains that drove astronomical displays on multiple levels. Within the upper chamber of the tower sat the massive armillary sphere, crafted from polished bronze and intricately engraved with celestial coordinates, ecliptic rings, and equatorial markers. Because the clockwork rotated the heavy bronze instrument at the exact speed of the Earth's rotation, the sphere's sight tube remained aligned with target stars continuously, turning alongside the night sky in seamless, automated unison. Stepping inside the lower chambers of Su Song's clockwork tower at midnight offered a sensory experience of deep stillness and mechanical harmony. The ambient darkness was illuminated only by the faint glow of oil lamps, casting long, gentle shadows across the wooden beams and polished metal surfaces. The primary sound filling the space was the soft, soothing murmur of water flowing continuously through hidden channels and bronze spouts, creating a meditative rhythm akin to a gentle rainfall in a quiet forest. At regular intervals, the quiet was punctuated by the soft, resonant chime of a bell or the low strike of a gong, sounded by small mechanical wooden mannequins that emerged from miniature doors on the tower facade to announce the passage of each hour and watch period. Higher up within the tower, astronomers could work with unprecedented ease, observing the cosmos through the rotating armillary sphere without needing to manually adjust its massive weight against the night air. The heavy bronze rings, gleaming faintly in the lamplight, turned so smoothly that their motion was almost imperceptible to the human eye, mirroring the subtle, silent drift of the constellations across the open sky above. This remarkable synthesis of hydraulics and observational astronomy demonstrated a profound understanding of natural forces, harnessing the steady downward flow of water to reflect the endless circular motion of the heavens. Scholars could rest assured that even when clouds obscured the night sky, the bronze sphere within the tower continued its patient rotation, keeping faithful time and preserving the cosmic map until the clouds parted to reveal the stars once more. As the long night wore on and the stars began their slow descent toward the western horizon, Song's clock tower remained an enduring symbol of peaceful contemplation and human ingenuity. It represented a moment in history when skywatchers did not merely watch the heavens from afar, but sought to understand their underlying mechanics so deeply that they could build a microcosm of the universe on Earth. The legacy of this water-driven monument resonated far beyond the walls of Kaifeng, inspiring future generations of instrument makers, mathematicians, and astronomers across Asia and Europe to explore the possibilities of mechanical clockwork. The idea that time, distance, and planetary movement could be captured through gearwork laid early conceptual foundations for the mechanical clocks and automated astronomical models that would emerge centuries later. Yet, in its own time, the tower served a purpose that was as aesthetic and spiritual as it was scientific. It offered a tangible manifestation of cosmic order, inviting observers to pause, breathe slowly, and feel connected to the grand, unhurried movements of the universe. Sitting beneath the quiet canopy of the night, listening to the gentle drip of water and the steady turn of bronze against wood, one could feel a sense of profound calm, knowing that the great wheel of the heavens was turning as it always had, guided by laws of timeless grace. As the first soft light of dawn began to touch the eastern sky, the stars slowly faded into the morning blue. But inside the tower, the water kept dripping, the gears kept turning, and the quiet harmony between humanity and the stars endured unbroken. In the quiet warmth of the Mesoamerican evening, where the dense tropical canopy softens into silhouetted leaves against a darkening sky, the ancient universe revealed itself in moments of profound stillness. Long before optical instruments were fashioned to magnify distant worlds, the skywatchers of the Yucatan Peninsula looked upward with an unhurried, patient gaze, discovering in the nocturnal vault a world of absolute order and serene mathematical harmony. High atop limestone platforms and elevated observatories designed to align with distant horizon points, these ancient astronomers watched the slow, graceful drift of constellations, listening to the night breeze as it stirred the leaves of the surrounding jungle. To them, the night sky was neither mysterious nor chaotic, but a living, glowing clockwork whose intricate cycles mirrored the rhythms of agriculture, architecture, and daily life. As twilight ebbed into the deep indigo of full night, the air cooled, and the first bright wanderers of the solar system began their silent procession across the dark expanse. Among all the celestial bodies that crossed the heavens, none commanded greater devotion or held a more breathtaking presence than Venus, shining with a luminous, steady radiance that pierced the gathering dusk just above the treetops. Night after night, season after season, generation after generation, observers stood in quiet recording the exact positions where this brilliant star first appeared above the eastern horizon at dawn, or lingered above the western horizon at dusk. In this serene atmosphere of quiet study, astronomy was not a hurried search for rapid answers, but a gentle, lifelong meditation on the passage of time, a peaceful dialogue between the grounded earth and the eternal light of the distant cosmos. Around 1200 CE, in the Yucatan Peninsula, Maya scribes painted the delicate bark paper pages of the Dresden Codex with natural indigo and red mineral pigments, meticulously recording the 584-day cycle of Venus as it rose as a morning and evening star over 40 quiet synodic periods. To create this extraordinary manuscript, master artisans first harvested the inner bark of wild fig trees, soaking and beating the fibers into long, flexible sheets of paper known as ammetal, which were then folded like a delicate accordion and coated with a thin layer of white lime plaster to provide a smooth, resilient surface. Sitting in quiet, airy scriptoriums illuminated by gentle daylight, the scribes prepared their natural pigments with painstaking care, grinding hematite and cinnabar to produce deep, vibrant reds, and blending leaf extracts of the indigo plant with palygorskite clay to yield a brilliant, luminous blue that would resist the fading touch of time for centuries. With fine brushes fashioned from animal hair, they rendered precise rows of dot and bar numerals, glyphic annotations, and sacred deity figures, carefully mapping out the complex mechanics of the night sky. Each section of the Venus table in the Codex detailed the exact progression of the planet through its 4 distinct phases. Its dramatic emergence as the morning star after disappearing behind the glare of the sun, its quiet passage through superior conjunction, its return as the glowing evening star in the western sky, and its brief disappearance during inferior conjunction before beginning the cycle anew. By compiling these calculations across 40 complete synodic cycles, the scribes created an astronomical document of stunning precision, bridging the gap between direct observational experience and abstract mathematical prediction. The manuscript remains a testament to a culture that viewed the sky with both artistic reverence and scientific rigor, recording the movements of distant worlds on delicate bark paper with pigments derived directly from the earth beneath their feet. The tracking of 40 synodic cycles was not merely a brief calculation, but a grand endeavor spanning more than 2 centuries of dedicated skywatching, reflecting a profound commitment to long-term observation passed down through lineages of scholars. A single synodic period of Venus lasts approximately 584 days, during which the planet completes its entire sequence of appearances, disappearances, and reversals against the background of the stars. To track 40 of these extended cycles required, counting 23,360 individual days with unbroken accuracy, a colossal span of time that allowed Maya astronomers to discover incredible mathematical harmonies hidden within the cosmos. Through their meticulous records, they realized that 5 synodic cycles of Venus, totaling 2,920 days, aligned almost perfectly with 8 solar years of 365 days each, creating a recurring pattern where Venus returned to nearly the same spot in the sky on the exact same date every 8 years. Expanding this vision across 40 synodic periods allowed them to harmonize 3 distinct calendars: their 260-day sacred almanac, their 365-day solar year, and the long, wandering journey of Venus itself. Every calculation written on the bark paper pages served to fine-tune their understanding of these celestial gearings, enabling them to predict solar and lunar eclipses, adjust seasonal calendars, and anticipate the precise moment when Venus would once again pierce the dawn sky as a morning star. This deep numerical harmony brought a sense of profound peace and predictability to their world, confirming that behind the shifting appearance of the sky lay an unwavering law of balance. Sitting under the vast, quiet canopy of the tropical night, the astronomers could rest secure in the knowledge that every planetary motion had been measured, understood, and woven into the grand tapestry of human thought. As the deep quiet of night settles fully over the land, the story of these ancient Mesoamerican skywatchers invites us to pause and reflect on our own connection to the cosmos. Long before glass lenses and electronic sensors expanded human vision into the far reaches of deep space, the human eye and a quiet, patient mind were sufficient to uncover the deepest secrets of planetary motion. The Dresden Codex remains a gentle reminder of what can be accomplished when human curiosity is paired with quiet stillness and an enduring reverence for nature's subtle rhythms. Across the centuries, the same Venus that guided the brushes of Maya scribes still rises quietly in the twilight, casting its soft, silver light across calm oceans, whispering forests, and sleeping cities around the globe. Its steady glow reminds us that the universe moves in slow, graceful loops, unhurried by the frantic pace of modern life, offering an eternal backdrop of calm and continuity to all who look up into the dark. As the stars continue their silent rotation across the night, there is a deep comfort in knowing that generation after generation of human beings have looked upon this very same sky, finding peace, inspiration, and rest beneath its luminous expanse. In the soothing quiet of the night, as thoughts grow soft and heavy, we can let our minds wander back to those peaceful scriptoriums on the Yucatan Peninsula, where the gentle touch of a brush on bark paper captured the music of the spheres, leaving behind a timeless legacy of wonder to accompany our quietest dreams. In the middle of the 13th century, where the river Tagus loops softly around the high, sun-baked promontory of Toledo, a profound and restful quiet settled over the ancient city each evening. Toledo had long served as a remarkable crossroads of thought and gentle exchange, a sanctuary where Jewish, Christian, and Muslim scholars met in mutual respect to study philosophy, medicine, and the sacred architecture of the night sky under the dark Iberian canopy, while the cobblestone streets below lay silent beneath terracotta tiles and stone arches. Astronomers climbed to high alcoves and tower rooftops to gaze upward at the unchanged constellations. For untold generations, watching the subtle movement of the wandering stars, the planets that drifted with slow, elegant paths across the backdrop of fixed stars, had required both boundless patience and intricate mathematical imagination. The accumulated astronomical insights of ancient Greece, Persia, and the Islamic world had flowed steadily into the scriptoriums of Spain, bringing with them sophisticated astrolabes, armillary spheres, and complex geometric treatises. When King Alfonso X of Castile, known to history as Alfonso the Wise, looked out across the quiet hills surrounding his capital, he envisioned a single, comprehensive work, a complete set of planetary tables that would refine existing knowledge and bring reliable clarity to the nocturnal heavens. It was an undertaking conceived not out of urgency or ambition, but from a deep, peaceful reverence for the hidden order of the cosmos. The stars, gleaming with quiet consistency, seemed to offer an invitation to human curiosity, prompting the king to gather the finest minds of his realm to translate the delicate geometry of the heavens into rows of numbers that could be read by the warm light of oil lamps. The quiet chambers of Toledo, surrounded by parchment sheets, iron gall ink, and fine brass instruments, a monumental labor began, one that would bridge ancient celestial lore with the future of navigation and planetary study, weaving a calming tapestry of numbers across the deep indigo night. To carry out this massive undertaking, scholars of varied backgrounds pooled their knowledge, creating an atmosphere of shared dedication, where personal differences dissolved into the quiet study of the cosmos. 1252 in Toledo, a council of scholars compiled the Alphonsine tables, hand calculating hundreds of pages of mathematical grids to predict planetary movements across the nocturnal sky for 3 centuries. Working hour after hour through the peaceful stillness of the night, these astronomers painstakingly calculated the complex geometric interactions of Ptolemaic orbits, epicycles, and deferents, converting abstract circles into neat, ordered columns of numerical values. Each single entry demanded complete concentration and unwavering care, as quills carefully recorded the longitudes, latitudes, and expected velocities of the Sun, the Moon, and the 5 visible planets Mercury, Venus, Mars, Jupiter, and Saturn, for every day and hour across hundreds of years. The process was slow, rhythmic, and deeply serene, echoing the silent, measured drift of the stars outside their tall stone windows. Because a single error in addition or sign calculation could compromise an entire sequence of future predictions. Every line of numbers was calculated independently reviewed, and cross-checked against fresh observational data gathered from Toledo's high watchtowers. Through this harmonious collaboration, the scholars succeeded in refining older Islamic tables, harmonizing discrepancies, and providing an updated numerical model tailored to the geography of Western Europe. The resulting grids were far more than mere historical records of past positions. They represented a quiet promise, a map of time that foretold where each wandering light would appear in the sky long after the scholars themselves had laid down their pens. Bound into heavy volumes, these grids transformed the wild, terrifying vastness of the midnight sky into an accessible and reassuring harmony for all who sought to understand the stars. The compilation of these mathematical grids marked a quiet revolution in medieval science, laying down a stable foundation that would guide astronomers, mariners, and scholars across Europe for generations. Prior to the completion of the Alphonsine tables, predicting the precise date of a celestial alignment, a planetary conjunction, or the gentle darkening of a lunar eclipse was an uncertain task, often dependent on fragmented or outdated manuscripts passed down through centuries of copying. With these new tables available, a scholar preparing lectures at the University of Paris, a doctor calculating auspicious moments in Italy, or a sea captain planning a journey across open waters could open a manuscript and trace the future path of any planet with unprecedented accuracy and peace of mind. The tables provided a universal language of numbers, turning what once seemed like unpredictable celestial movements into a steady, reliable rhythm. As seasons turned from autumn gold to winter snow, and decades washed over the towns and fields of Europe, the cosmos inside the pages of Toledo's masterwork moved with silent, perfect regularity. The manuscripts themselves were masterpieces of medieval scriptorium art, arranged in immaculate rows of red and dark brown ink, complete with delicate column headers and explanatory margins written in Latin and Spanish. Preserved within cathedral archives, monastery scriptoriums, and royal libraries, they quickly became the authoritative standard across the continent. Copyists worked methodically to duplicate the grids by hand, spreading Toledo's quiet intellectual triumph to every center of learning. In a world often marked by uncertainty and change, the tables provided a comforting sense of order, proving that behind the mystery of the dark sky lay a profound, beautiful mathematical harmony that humans could discover through patience, study, and quiet devotion. Even as centuries passed, and the scholars who labored in Toledo dissolved into history, the Alphonsine tables continued to shine as a beacon of astronomical knowledge, silently shaping the dawn of modern science. For nearly 300 years, virtually every major astronomical calculation, navigational chart, and almanac created in Western Europe drew directly upon or referred back to these meticulously hand-calculated grids. When early Renaissance astronomers began to re-examine the fundamental structure of the cosmos, it was the numbers of the Alphonsine tables that sat open on their wooden desks. Nicolaus Copernicus studied these very figures as he developed his heliocentric model, relying on the long-term observational predictions compiled in Toledo to test and refine his revolutionary idea that the Earth and planets orbited the Sun. Thus, the quiet, persistent work accomplished in 1252 served as an enduring bridge, carrying the wisdom of ancient skywatchers through the Middle Ages and into the birth of modern astronomy. The ultimate legacy of Toledo was not merely a collection of numerical data, but a testament to the soothing power of human curiosity and peaceful inquiry. Today, as night settles softly over the world and the first bright planets emerge in the twilight, one can look up with the same sense of wonder that filled the hearts of those medieval scholars. The planets move along their accustomed paths across the zodiac, just as predicted by the soft scratch of quills against parchment so long ago. The quiet memory of their labor offers a lingering comfort that across ages and cultures, humanity's gentle search for order in the stars brings a timeless sense of peace, connecting us all beneath the vast and quiet night. As night descended across the quiet high plateau of northwestern Iran, the air grew still and cool, inviting the eyes upward toward the unhurried arc of the constellations. Here, far above the rustling valleys and sleeping towns, human curiosity turned toward the ancient puzzle of how celestial bodies trace their paths across the midnight sky. For centuries, astronomers across many cultures had wrestled with complex mathematical constructs to explain why planets seemed to slow, stop, and gently loop backward against the backdrop of distant stars, moving in patterns that defied simple circles. In 1259, at the Marikeh Observatory in northwestern Iran, astronomer Nasir al-Din al-Tusi devised the Tusi couple, a mathematical mechanism of nested rotating circles that modeled planetary motion with smooth geometric precision. This elegant invention allowed a smaller circle to roll smoothly inside another of twice its diameter, transforming pure rotational movement into a steady, linear back and forth oscillation without relying on clumsy mechanical levers or artificial constructs. Within the quiet stone walls of the hilltop observatory, lit only by soft oil lamps and the faint, silvery glow of the cosmos, Al-Tusi and his fellow scholars recorded these geometric harmonies onto parchment, finding a profound sense of quiet order in the universe. The mechanism was more than just a clever geometric proof. It was a peaceful reimagining of celestial mechanics that eliminated many of the awkward assumptions of earlier Ptolemaic models, allowing future generations of astronomers to view the wandering stars with newfound clarity and mathematical grace. In the deep hush of those mountain evenings, the slow turn of brass astrolabes and the gentle scratch of reed pens against paper mirrored the eternal, silent dance of the heavens above. The observatory served as a peaceful sanctuary where scholars from distant lands gathered to translate, measure, and contemplate, weaving together threads of knowledge from ancient Greece, Persia, and India into a coherent, beautiful vision of cosmic harmony. As the stars drifted softly across the meridian, the quiet work at Marigay demonstrated how human thought, patient and meticulous, could untangle the subtle rhythms of the cosmos and offer a restful sense of predictability to the surrounding night. Thousands of miles to the east, under that very same vault of midnight dark, another great tradition of skywatching was observing the subtle passage of the seasons with equal reverence and meticulous care. Across the expansive, quiet plains of China, where the heavens were viewed as a vast, serene mirror reflecting earthly balance, generations of imperial astronomers spent their lives charting the sun's breath and the slow movements of the lunar mansions. Stargazing in the east was not merely a matter of practical utility. It was an act of deep contemplation, a calm attunement to the natural laws that govern time, agriculture, and the rhythmic pulse of the earth itself. The night skies over the ancient administrative centers were clear and unpolluted, revealing thousands of faint, shimmering stars that served as delicate markers along the ecliptic path. Astronomers worked in hushed silence atop elevated stone platforms, using intricate armillary spheres, water-driven globes, and shadow-casting rods to track the slow drift of the solar declination day by day, night by night. Every shadow cast at noon, every stellar alignment recorded in the deep tranquility of midnight, contributed to a grand, continuous ledger of cosmic order that stretched back over millennia. There was a restful dignity in this daily and nightly routine, a shared understanding that human life was gently bound to the steady, unhurried cadence of the celestial sphere. As seasonal breezes shifted from the warm moisture of summer to the crisp, clear stillness of autumn, these devoted observers watched the stars of the azure dragon give way to the calm, starlit contours of the black tortoise, tracking the passage of time not with urgency or fanfare, but with a quiet, meditative gratitude for the enduring constancy of the sky. This long heritage of Eastern observational science reached a monumental peak of precision in the late 13th century, set against the peaceful backdrop of the Henan countryside. In 1279 CE, at the Geocentric Observatory in Henan, Yuan dynasty astronomer Gu Shaojing constructed a 40-foot brick gnomon tower paired with a fine bronze shadow definer, measuring the length of the solar year to within 26 seconds of modern satellite data. Standing tall and proud against the open horizon, the great brick tower acted as a massive instrument of shadow and light, catching the high noon sun and projecting its long, subtle shadow across a low stone measuring channel that stretched along the ground like a quiet river of stone. To overcome the natural blurriness of shadows, cast over such vast distances. Guo Xiaojing's ingenious bronze pinhole device, the shadow definer, focused the sunlight into a remarkably sharp, clear point of light, allowing measurements of extraordinary exactness that surpassed anything previously achieved. Day after day, season after season, as the long shadows of winter gradually shortened into the fleeting shadows of the summer solstice, the observatory stood as a timeless monument to patience, focus, and quiet craftsmanship. The calendar produced from these observations, known as the Shaoxi calendar, guided millions of agricultural lives with unprecedented accuracy, aligning human activity perfectly with the natural rhythm of the Earth's orbit around the sun. In the cool stillness of twilight, when the shadow on the stone channel faded into the gentle dimming of the sky, the tower seemed to merge with the landscape itself, a silent monument bridging the earth beneath with the starry expanse above. Through the quiet genius of observers like Al-Tusi in Iran and Guo Xiaojing in China, humanity took steady, confident steps forward in understanding the architecture of space and time, laying a peaceful foundation of knowledge that would drift softly across centuries, inspiring all who look up into the tranquil expanse of the night. As the 14th century unfolded across the landscape of southern Europe, the rhythms of human life remained deeply tied to the natural movements of the heavens, where celestial bodies traced their silent, eternal arcs across untouched dark skies, far removed from the intrusive glow of modern cities. The nocturnal firmament offered a breathtakingly clear view of constellations drifting overhead, inspiring astronomers and scholars to seek ever more refined ways of listening to the geometry of the cosmos. In the historic town of Avignon, situated along the tranquil banks of the Rhone, the cool evening air was frequently filled with the quiet contemplation of scholars who gathered under the vast European sky to chart the wanderings of planets and fixed stars. For generations, astronomical observations had depended primarily upon grand, stationary installations, massive stone quadrants, brass astrolabes, and heavy armillary spheres anchored to courtyard floors or hilltop platforms. While these classic instruments possessed a majestic permanence, they were inherently cumbersome and limited by their immobility, leaving observers reliant upon fixed positions that could not easily adapt to changing vantage points or swift field measurements. As trade routes expanded and intellectual exchanges deepened across the Mediterranean world, there arose a gentle yet persistent longing among natural philosophers for portable, elegant tools that could bridge the gap between abstract mathematical theory and direct stellar observation. Skywatchers envisioned an instrument light enough to be held comfortably in a scholar's hands, simple enough to craft from seasoned timber, yet precise enough to reveal the subtle angular separations between celestial lights. Beneath the peaceful canopy of the medieval night, where the soft rustling of leaves and the distant murmur of river currents provided a calming backdrop. The quest for a new kind of astronomical instrument began to take shape, guided by a spirit of patient inquiry and profound reverent wonder at the order governing the cosmos. Among the most remarkable figures of this intellectual era was the distinguished scholar, mathematician, and philosopher Levi ben Gershon, often known to history as Gersonides, whose wide-ranging intellect sought to bring unprecedented mathematical clarity to the study of the heavens, working within the vibrant cultural crosscurrents of Provence. Gersonides dedicated countless quiet hours to refining astronomical calculations, revising planetary models, and crafting innovative instruments designed to improve the accuracy of human sight. In 1342, in Avignon, Jewish polymath Levi ben Gershon described the Jacob staff, a calibrated wooden rod with sliding crosspieces that allowed skywatchers to measure the exact angular distance between quiet night stars. This ingenious device, known in Latin treatises as the asterisk baculus Jacob asterisk, consisted of a main, long wooden shaft, carefully inscribed with precise mathematical graduations along its length, paired with one or more perpendicular cross veins, engineered to slide smoothly back and forth along the central axis. To operate the staff, a skywatcher would raise one end of the main rod gently to the eye, sighting along its polished length toward a chosen region of the night sky, and then carefully adjust the position of the sliding crosspiece until its opposite outer tips aligned perfectly with two selected stars. By observing where the sliding vein intersected the numerical markings on the main rod, the user could easily calculate the angular separation between the 2 points of light using the fundamental rules of trigonometry. What made this instrument so extraordinary was not merely its mathematical elegance, but its remarkable accessibility and physical simplicity, transforming complex geometric principles into a direct, tactile experience. Instead of requiring complex gearwork or fragile glass optics, the Jacob staff relied entirely upon the harmony of sight, straight lines, and proportional ratios, giving astronomers an unprecedented ability to measure the expanse of the firmament with quiet confidence and remarkable accuracy during the long, tranquil hours of the night. The physical experience of using the Jacob staff under a clear, unpolluted sky was one of deep focus, meditative stillness, and restful engagement with the nocturnal world. Holding the polished wooden shaft steadily against the cheekbone, an observer had to slow their breathing, matching the quiet rhythm of the midnight environment as they aligned the edges of the cross vein with the faint shimmer of distant suns. The subtle sound of wood sliding smoothly over wood echoed softly in the quiet night, serving as a gentle tactile reminder of the human craft dedicated to understanding the universe. as the observer shifted the crosspiece by mere fractions of an inch. The proportions of the right triangle formed between the eye, the center of the rod, and the outer edges of the vane changed in perfect mathematical harmony, allowing even subtle planetary movements or the angular spans of comets to be recorded with newfound precision. Before Gersonide's thorough treatise, earlier versions of sighting rods had existed in rudimentary forms, but his rigorous mathematical calibrations elevated the concept into a standardized, scientific instrument that could be reliably replicated by instrument makers across Europe. Furthermore, the Jacob staff possessed a unique dual nature, proving equally valuable for terrestrial surveying and maritime navigation as it was for celestial mapping. In the decades and centuries that followed, sailors navigating vast and uncharted oceans under dark, starlit skies would embrace modified versions of the staff, often referred to as cross staffs, to measure the altitude of Polaris above the horizon, using the calm light of the North Star to determine their vessel's latitude. Thus, a device born from the peaceful study of a medieval scholar in Avignon grew to become an essential companion for explorers venturing across the globe, linking the quiet solitude of astronomical study with the grand, sweeping journeys of human discovery. Long before the invention of the telescope revealed the hidden depths of deep space, the Jacob staff provided humanity with a profound tool for measuring the silent architecture of the night. It reminded skywatchers that the heavens were not an chaotic or incomprehensible void, but a masterwork of mathematical order whose secrets could be unlocked through patience, clear sight, and humble craftsmanship. The calibrated wooden rod transformed the sky into a vast canvas of measurable relationships, where every star maintained its appointed distance from its neighbors, moving in steady, dependable harmonies across the dark blue dome of night. As Gersonides rested his eyes after hours of painstaking observations, recording his geometric derivations into illuminated manuscripts, he contributed a crucial chapter to the long story of astronomical progress, a story built step by step through human ingenuity, careful observation, and an enduring love for the nocturnal sky. The legacy of his work endured through generations of skywatchers, serving as a bridge between the qualitative observations of antiquity and the quantitative precision of modern science. Tonight, as we look up at the same timeless stars that illuminated the rooftops of Avignon so many centuries ago, we can appreciate the quiet beauty of those early instruments that brought clarity to human vision. The steady, calm presence of the stars continues to offer a sense of peaceful permanence, inviting us to rest beneath their gentle glow, comforted by the knowledge that the universe unfolds in quiet, orderly rhythm, holding its timeless patterns in safekeeping until the dawn. As twilight gently settles over the fertile valley of the Zarafshan River, the ancient city of Samarkand softly transitions into the quietude of evening. The vibrant hues of cobalt, lapis, and turquoise tiles that adorn the city's majestic domes begin to mute under a darkening sky, gradually yielding their brilliant luster to the cool, restful shadows of dusk. In the early 15th century, this bustling crossroads of the Silk Road became a sanctuary not only for merchants and artisans, but for those who sought a deeper, more peaceful understanding of the heavens above. Among them was the astronomer Prince Ulugh Beg, a figure whose deep passion for mathematics and the steady paths of the stars far exceeded any desire for political ambition or courtly noise. Upon the gentle rise of the Kuhak Hill, situated just beyond the city's perimeter, he envisioned a place where the subtle movements of the sun, moon, and distant constellations could be recorded with unprecedented stillness, scale, and clarity. As the evening air cools and the soft desert breeze whispers through the surrounding gardens and orchards, the observatory stands as a silent monument to human patience, inviting the mind to leave behind the busy distractions of the day and enter a realm of quiet, predictable harmony. Here, high above the sleeping rooftops, the night sky opens like a vast velvet canopy, clear and unburdened by dust, offering an expanse of steady celestial light that has fascinated skywatchers across countless generations. The slow, rhythmic passage of time is felt in every breath of evening air as the first bright points of light emerge in the zenith, calm and reassuring in their eternal cycles. To step into this sanctuary of science is to enter a space where time naturally slows down, where the noisy demands of everyday life fade into the calm, measured cadence of cosmic geometry, and where looking upward becomes a soothing meditation on order, beauty, and peace, to achieve a level of observational accuracy that had never before been realized in human history. Ulugh Beg recognized that the instruments of astronomy needed to transcend the small, handheld astrolabes and portable quadrants of earlier generations. He understood that to measure the subtlest shifts in the heavens, one required extraordinary scale, absolute stability, and an immovable foundation rooted deep within the bedrock of the earth itself. In 1420, near Samarkand, astronomer Ulugh Beg constructed a subterranean stone meridian arc with a radius of 40 meters carved into a sandstone hill, using its gentle shadows to measure the night sky and catalog 1,018 stars. This monumental arc, aligned with perfect exactness along the north-south meridian line, was sunken deeply into the cool, protective trench of the hill to shield the delicate measuring surfaces from thermal expansion, wind, and the subtle vibrations of the ground. Twin parallel tracks of finely dressed limestone and smooth, polished marble were embedded into the carved stone arc, inscribed with precise degree marks and fractional divisions that allowed observers to read the positions of celestial bodies with unprecedented exactness. During the brightest hours of the day, A small opening at the top of the observatory building allowed a single, focused beam of sunlight to fall onto the subterranean scale, casting a soft, luminous spot that glided effortlessly across the numbered stones as solar noon approached. As daylight slowly softened into dusk, this same vertical plane became a calm transit corridor for the moon and stars, whose gentle passages across the meridian line were recorded by quiet observers seated along the stepped curve of the trench. Descending into the cool, quiet depths of the sandstone hill offered a profound sense of peaceful isolation, as if stepping out of time itself into a sacred space dedicated entirely to the quiet dialogue between light and stone. Night after night, in the serene stillness of the Central Asian sky, Ulugh Beg and his dedicated circle of scholars gathered along the great stone arc to perform their quiet work. There were no sudden rushes or dramatic displays in their labors. Instead, their pursuit was defined by a soothing, repetitive routine of patient waiting, fine alignment, and gentle record-keeping. As each star drifted quietly across the narrow vertical window of the meridian, an observer positioned within the dark subterranean trench would carefully sight its altitude against the polished marble graduations, recording the exact moment of its highest point with a calm and steady hand. The thick stone walls and natural earth surrounding the observatory absorbed the residual heat of the day, creating a microclimate of stable, unruffled air that minimized atmospheric shimmering, allowing the stars to appear as clear, steady points of pure illumination. Through this tranquil, methodical process, the astronomers recorded the precise coordinates of the planets, measured the subtle tilt of the Earth's axis with astonishing accuracy, and calculated the length of the solar year to within seconds of modern values. The work proceeded with the gentle rhythm of a nighttime lullaby, where each entry in the observational ledger represented hours of quiet contemplation beneath the vast, silent vault of heaven. The scholars moved with soft steps across the stone platforms, speaking only in whispered tones so as not to disturb the profound quiet of the night, bound together by a shared reverence for the mathematical elegance of the cosmos. In this atmosphere of deep focus and quiet wonder, the vast distance of the stars did not feel cold or overwhelming. Rather, it offered a sense of comforting permanence, reminding those who watched that above all human cares, the celestial sphere moves with unhurried grace and timeless stability. The ultimate fruit of these long, peaceful nights was a masterwork of astronomical knowledge that would quietly enrich scientific understanding across the world for centuries to come. The star catalogue, created within the cool sandstone depths of the Samarkand Observatory, provided an extraordinarily accurate mapping of the firmament, refining measurements that had remained unchanged since the ancient observations of Ptolemy over a millennium before. Bound into elegant manuscripts decorated with fine calligraphy and copied by hand in scriptoria across Asia the Middle East, and eventually Europe. These star tables carried the peaceful legacy of Ulugh Beg's observatory across oceans and generations, connecting scholars of different eras through a shared wonder at the night sky. Today, though the grand upper structure that once stood atop the sandstone hill has long since weathered away, the lower arc of the great stone sextant remains resting peacefully within its subterranean trench, preserved in the cool earth just outside Samarkand. Visiting the quiet site today evokes a deep sense of restfulness, as the smooth, sweeping curve of stone still marks the place where light and shadow once met in quiet precision. It stands as a timeless reminder of what human patience and gentle curiosity can achieve when focused not on conflict or speed, but on listening to the quiet rhythms of the natural world. As we gaze up at the very same stars that glided over the meridian of Samarkand 6 centuries ago, their steady, soft light invites us to slow our thoughts, let go of the day's burdens, and drift into a peaceful sleep beneath the eternal harmony of the night sky. As the 15th century unfolded across the vast expanses of Eurasia, the night sky offered a sanctuary of absolute stillness, inviting scholars and observers to contemplate the subtle, orderly rhythms of the universe. High along the Silk Road in Central Asia rested the historic city of Samarkand, surrounded by fertile valleys and framed by the distant, snow-capped peaks of the Pamir Mountains. In those quiet evening hours, a cool desert breeze settled over turquoise-tiled domes and peaceful courtyards, creating atmospheric conditions of exceptional transparency and stillness. At the center of this cultural and scientific flourish was the Timurid ruler Ulugh Beg, a sovereign whose deepest devotion lay not in territorial expansion, but in the quiet realm of mathematics and observational astronomy, drawing upon centuries of Islamic astronomical tradition. Ulugh Beg recognized that earlier instruments, such as handheld astrolabes or portable brass quadrants, were limited by their small size and prone to minor flexure or temperature expansion. To achieve true precision in mapping the celestial sphere, astronomers needed a measuring device of monumental scale, anchored immovably into the very bedrock of the earth itself. On the gentle crest of the Chupanada Hill, just outside the city walls, he planned an observatory of unprecedented grandiosity, a massive circular structure built to house a measuring instrument larger than any the world had ever seen. In 1428, at his observatory in Samarkand, the astronomer Ulugh Beg constructed a stone meridian arc with a 40-meter radius built directly into a hillside, measuring the length of the tropical year to within 25 seconds. This colossal instrument, constructed as a double meridian quadrant, was set into a deep trench carved out of solid rock and lined with finely polished limestone blocks, inscribed with meticulous degree markings and fractions of minutes. Deep within the subterranean chamber of the ark, shielded from wind, thermal shift, and ambient light, the air remained soothingly cool and silent. As solar noon approached each day, a narrow beam of golden sunlight entered through an aperture at the top of the observatory and slid smoothly along the dark, curved marble track below. By measuring the solar beam's position across successive solstices and equinoxes over many peaceful years, Ulugh Beg and his scholars calculated the length of the tropical year with an error of less than half a minute, producing the famed Zijai Sultani star catalogue that catalogued over 1,000 stars and brought a profound, comforting order to the measurement of time. Far to the east, across thousands of leagues of high plateaus, quiet forests, and winding rivers, a parallel pursuit of celestial harmony was unfolding in the Korean peninsula. During the mid-15th century, the capital city of Seoul, then known as Hanyang, slumbered peacefully beneath clear, star-dusted skies under the wise reign of King Sejong, the Great of the Joseon dynasty. King Sejong held a deep, compassionate belief that the well-being of his kingdom depended on living in gentle alignment with the natural order of the heavens and the rhythms of the seasons. While daytime hours across the palace grounds were marked by elegant stone sundials, measuring the deep, silent hours of the night presented a unique practical challenge for court scholars and civil guardians. The traditional water clocks housed within central palace towers provided reliable time, but night watchmen patrolling the quiet perimeters of the city walls and distant wooden gates required a light, independent way to verify the midnight hours directly under the open sky. To solve this, King Sejong turned to the extraordinary talent of Jang Yong-sil, a master artisan who had risen from humble beginnings to become the kingdom's chief engineer through his extraordinary mechanical intuition and inventiveness. In 1437 in Seoul, Joseon artisan Jang Yong-sil crafted the Ilseonjeongshini, a portable bronze star clock that allowed night watchmen to tell the exact hour after dark by aligning calibrated rings with the North Star. The name of this remarkable device translated to the instrument for determining time by the sun, moon, and stars, integrating both solar timekeeping by day and stellar timekeeping by night. Cast in heavy, polished bronze and engraved with delicate precision, the star clock featured 3 concentric, independently rotating rings representing the celestial equator, the sun's annual path, and the positions of key reference stars, all held together by a central handle and sighting mechanism. As a night watchman walked his quiet rounds through the slumbering city, past tiled roofs and dark garden courtyards, he could pause under the open sky and raise the instrument toward the heavens, sighting the steadfast, unmoving light of Polaris through the central aperture, and rotating the outer bronze rings to align with the prominent circumpolar constellations, such as the stars of the Great Bear as they pivoted around the pole. The watchman could instantly read the precise night watch hour from the intersecting scale. The cool glint of moonlight on calibrated bronze brought a gentle certainty to the dark, reassuring the city's inhabitants that the night was unfolding in perfect harmony with the sky. Although separated by vast mountain ranges, cultural traditions, and geographic distances, the monumental stone arc of Samarkand and the delicate bronze star clock of Seoul shared a deeply tranquil and unifying human impulse. Both masterworks emerged from a golden age of pre-telescopic astronomy, when measuring time was understood not as a restless drive for speed, but as a meditative practice of observing nature's grand design. Samarkand, the earth itself was opened and lined with polished marble to receive the slow, silent transit of the sun across a 40-meter arc. In Seoul, the light of distant circumpolar stars was framed within handheld bronze circles, allowing a lonely guardian in the midnight silence to connect his daily duties with the axis of the spinning earth. In both instances, the North Star and the celestial meridian served as quiet anchors, grounding human life in the eternal stability of the celestial pole. Neither instrument relied on ticking gears, coiled springs, or artificial force. Rather, both devices adapted human vision to the quiet, immutable mechanics of the heavens, inviting mankind to attune its life to the gentle rotation of the cosmos. In these 15th century innovations, scientific accuracy was sought as a path to clarity, quiet order, and peaceful contemplation. As the centuries have passed, the constellations that guided Ulugh Beg in his hillside observatory and illuminated Jang Yongsil's bronze rings continue to trace their silent, unbroken paths across the night sky. Remembering their devotion reminds us that time is a vast, calm ocean, carrying the earth smoothly through space in an eternal lullaby of starlight and shadow. Underneath this same vast, quiet canopy that has comforted skywatchers for centuries, the mind is invited to release its daily cares, drifting softly into the peaceful stillness of a restful night. Along the serene banks of the Vistula Lagoon, where the quiet northern winds touch the Baltic coast, night settles gently over the historic grounds of Fromberg Cathedral. In the early decades of the 16th century, this sheltered sanctuary offered an atmosphere of absolute calm, far removed from the clamor of bustling trade cities and noisy markets. Here, amid the cool brick architecture and the rhythmic murmur of coastal breezes, the evening mist rises slowly over the damp grass, wrapping the ancient stone structures in a soft, silver veil high above the cobblestone courtyards. Set within the sturdy warmth of a medieval fortified wall stands a modest tower that served as both a refuge and an observatory. Within this dimly lit, unadorned chamber, the air carries the subtle scent of old parchment, beeswax candles, and damp timber, creating an environment of deep concentration and timeless stillness. The passage of hours in such a place is marked not by the striking of bell towers or the footsteps of passing travelers, but by the gradual, deliberate rotation of the night sky overhead. As as the sun sinks below the flat horizon, bathing the northern skies in deep indigo and violet hues, the stars emerge one by one, shimmering like quiet lanterns across the vast expanse of the cosmos. For a dedicated scholar seeking to understand the true harmony of the heavens, this quiet tower provided an ideal perch from which to trace the delicate trajectories of light that cross the celestial dome. Night after night, as the rest of the world slumbered beneath warm down blankets, the tower remained a solitary beacon of patient curiosity, suspended between the steady earth below and the infinite mystery of the stars above. To read the vast book of the heavens without the aid of modern lenses required extraordinary patience, meticulous calculation, and simple instruments crafted with precise intent. In an era before glass optics revealed the cratered surfaces of distant worlds, astronomers relied on sightlines, physical scales, and geometric ratios to map the movements of celestial bodies. Working in a quiet brick tower at Fromberg Cathedral around 1520, Polish scholar Nicolaus Copernicus used a handmade wooden triquetrum carved from fir to measure the subtle nightly altitude of the moon. This classical three-staff instrument, constructed from local softwood, consisted of 3 joined rulers hinged together to form an adjustable triangle, allowing the observer to measure the angular distance of an object above the horizon with remarkable consistency. Sighting along the grain of the pale fir wood, Copernicus would carefully align the wooden scales with the silver disk of the moon as it drifted through the constellations of the zodiac. Each night, as the moon cast long, delicate shadows through the narrow lancet windows of the tower, he noted its exact position relative to the horizon, recording the subtle variations in its height and path with meticulous care. The triquetrum, though humble in its construction when compared to the grand metal armillary spheres of later centuries, was perfectly suited for the quiet work of observational astronomy. The wood itself, smoothed by hand and marked with fine ink graduations, felt cool and solid to the touch, grounding the astronomer in the tactile reality of physical measurement, while his thoughts ranged far out into the heavens. Through hundreds of such deliberate, soft-spoken observations, recorded in the margins of his handwritten charts and ledgers, he sought to untangle the complex mathematical knots that had bound astronomical thought for over 1,000 years. Listening closely to what the quiet moonlight might reveal about the geometry of the solar system. As the hours slipped softly toward dawn, the rhythmic movement of the moon across the stars provided more than just numbers on a page. It offered a key to reimagining the fundamental architecture of the cosmos. For centuries, the prevailing view of the universe had placed a stationary Earth at the absolute center of all motion, with the moon, sun, and planets revolving around it in complex, interlocking crystalline spheres. Yet, as Copernicus compared his nightly measurements of lunar altitude with the historical records of ancient Greek and Islamic astronomers, subtle discrepancies began to emerge, small, persistent incongruities that suggested the traditional model was far too convoluted to represent nature's elegant design. In the quiet solitude of his Fromberg sanctuary, surrounded by stacked folios and geometric diagrams drawn in iron gall ink, his mind gently pivoted toward a radically simpler idea. What if the apparent motions of the heavens were not entirely the work of the stars themselves, but were instead mirrored reflections of our own motion? What if the earth, far from being the fixed anchor of existence, was itself a sphere in gentle, continuous motion, drifting peacefully along a circular path around the sun alongside the other wandering planets? This profound realization did not arrive as a sudden, dramatic awakening, but rather settled over him like the soft twilight of a summer evening, nurtured by years of calm reflection and steady mathematical proof. The moon, in this newly envisioned cosmic order, remained our constant companion, moving quietly around the earth as the earth spun upon its axis and journeyed around the sun. By allowing the earth to move, the complex loops and retrogrades of the outer planets dissolved into simple, beautiful geometry, restoring a sense of pristine harmony and divine simplicity to the nighttime skies. In the deep quiet of the Baltic night, the tower at Fromberg stood as a bridge between the ancient tradition of skywatching and the dawn of modern scientific inquiry. Outside the tower window, the constellation of Cygnus drifted lazily through the Milky Way, its stellar pattern reflected in the calm, dark surface of the nearby sea. Copernicus understood that his revolutionary work required no haste, no grand announcements, and no contentious debates. It was a truth to be assembled slowly, layer by layer, with the quiet grace of a craftsman building a cathedral. The wooden triquetrum, resting gently against the brick wall between observations, was a testament to how human intellect could reach out into the vast emptiness of space, using only wood, string, ink, and vision. As the first faint traces of morning light began to soften the eastern horizon, painting the clouds in pale shades of rose and silver, the scholar would carefully store his instruments, blot the fresh ink on his parchment notebooks, and close his heavy wooden shutters against the rising sun. The world below would soon awaken to its daily routines of farming, fishing, and trade, blissfully unaware that within that quiet brick tower, the true place of our planet among the stars had been forever transformed. And as the morning breeze carried the sweet sound of cathedral chimes across the sleeping countryside, the quiet harmony of a sun-centered universe remained safely recorded in the silent pages of his manuscript, waiting patiently for future generations to look up at the night sky with renewed wonder and understanding. As the quiet twilight of the 16th century settled over the ancient university towns of Flanders, the human relationship with the night sky began to take on a remarkably intimate, handcrafted scale. For centuries, the measurement of celestial movement had belonged to vast stone observatories, heavy astrolabes, and immovable sundials that anchored human time to fixed places upon the earth. Yet, as scholars and artisans began to refine their understanding of geometry and metallurgy, the vast mechanics of the heavens were slowly brought down into the quiet palm of a traveler's hand. In quiet study rooms lit by gentle candlelight, mathematicians began to realize that the grand celestial sphere, with its tilted axis, its invisible equator, and its steady rotation, could be mirrored in small, portable arrangements of polished metal. This period marked a subtle transition in the history of astronomy, moving from grand public monuments to personal, meditative tools that allowed an individual, standing alone beneath the silent canopy of stars, to find their place in both space and time. The evening air in these northern towns carried a stillness that invited contemplation, where the slow movement of the constellations was no longer merely a distant, cosmic spectacle, but a dependable clock ticking gently in the dark. The crafts of the brass smith and the astronomer merged into a single art form, dedicated to translating the subtle angles of starlight into readable human hours. As travelers walked along dark country paths or rested beside quiet rivers, they carried with them tiny models of the cosmos, forged with precision and care. These instruments required no fire, no ticking gears, and no sound, relying entirely upon the silent, eternal geometry of the cosmos and the patient eye of the observer. In this peaceful union of human craft and stellar motion, the night ceased to be a dark void of uncertainty, becoming instead a structured and reassuring realm where every star had its defined place, and every hour could be gently unlocked by understanding the subtle tilt of the world. It was within this calm environment of scholarly reflection that Flemish astronomer and mathematician Gemma Frisius made a profound contribution to the art of nocturnal navigation and timekeeping. Working in the quiet academic haven of Louvain in the year 1534, Frisius published a detailed design for a remarkable instrument known as the astronomical ring, an elegant arrangement consisting of 3 delicate interlocking brass hoops that allowed night travelers to determine their precise local time simply by aligning the rings with starlight and the rotational axis of the Earth. Unlike traditional astrolabes, which often required flat plates tailored to specific latitudes, this self-adjusting armillary sphere in miniature was universal in its application, carrying within its nested circles the geometry of the entire globe. Each hoop had its own quiet purpose. One represented the meridian, set to match the latitude of the traveler. Another formed the equator, marked with the 24 hours of the day. And a third served as the declination ring, carrying a small sighting aperture or pointer to capture the gentle light of the sun or stars. When held suspended by a fine thread, the instrument allowed gravity itself to establish a true vertical line, leaving the traveler to gently rotate the nested hoops until the distant light aligned with the engraved scales. In the hands of a weary traveler pausing on a darkened road, the astronomical ring was both a practical guide and a quiet work of art, shining faintly under the soft moonlight as its polished brass captured the cool, ambient glow of the night. By bringing together the axis of the Earth and the distant light of fixed stars, Frisius had created a physical manifestation of astronomical theory that was as light as a pocket watch and as accurate as the sky itself. The publication of this design in Louvain resonated throughout Europe, offering merchants, mariners, and astronomers a serene sense of self-reliance, knowing that wherever they wandered across the sleeping continent, the sky above could always be read with clarity and ease. To understand the quiet grace of using an astronomical ring during a midsummer night is to appreciate the gentle rhythm of early modern astronomy. Imagine standing on a grassy hilltop outside a quiet village, long after the noise of the day has faded into silence. The air is cool and still, filled only with the soft rustle of evening leaves and the distant murmur of a meadow stream. You draw the small brass instrument from a velvet pouch, feeling the cool, polished metal against your fingers. The three hoops, resting flat against one another for easy travel, slide smoothly into position, unfolding into a delicate three-dimensional sphere. Hanging the ring from its slender silk cord, you allow it to settle into stillness, untroubled by wind or haste. To align the instrument, you find the familiar steady point of Polaris High in the northern sky, tilting the outer meridian hoop until it mirrors the exact angle of your location on Earth. Next, you gently pivot the hour circle until it catches the soft beam of a known star or the faint glow of the setting sun through its tiny pinhole. As the light aligns precisely through the apertures, the shadow falls across the engraved Roman numerals of the hour hoop, silently revealing the exact time of night. There is no ticking sound, no mechanical friction, only the silent, instantaneous agreement between your small brass sphere and the vast rotation of the planet beneath your feet. In this quiet moment of observation, time does not feel like something rushing forward or slipping away. Rather, it feels like a patient, continuous breath shared between the earth and the heavens. The simplicity of the technique meant that anyone with a basic understanding of the stars could navigate the dark hours with confidence, holding in their hand a true model of the celestial equator. The rings did not force the cosmos to yield its secrets through complicated computation, but invited the observer into a peaceful conversation with the night sky, turning the act of telling time into a tranquil ritual of astronomical wonder. As the decades passed, the astronomical ring of Gemma Frisius inspired generations of instrument makers, astronomers, and philosophical thinkers across Europe. It represented a pivotal moment when complex mathematical concepts became accessible, tangible objects of everyday beauty. The instrument required no complex power source, only the enduring stability of the Earth's rotational axis. and the clear visibility of the night sky, making it a timeless testament to human curiosity and harmony with nature. Long before the invention of the telescope or the precision pendulum clock, these interlocking hoops demonstrated that human beings could find clarity and peace amid the vastness of the universe, simply by observing its natural geometry. The delicate brass rings transformed the daunting infinity of space into something comforting, familiar, and deeply peaceful. As you lie back and picture those early skywatchers standing under the clear, star-filled skies of the 16th century, holding up their brass hoops to catch the quiet starlight, you can feel the same timeless calm that guided them. The stars continue their slow, silent drift across the dark dome of the night, constant and serene, just as they did centuries ago. The Earth turns gently on its axis, carrying the sleeping world smoothly toward the coming morning, wrapped in a blanket of quiet space, while the timeless geometry of the heavens offers a soothing rhythm to rest your mind upon. As the 16th century unfolded across the quiet landscapes of Europe, the study of the stars retained a deeply reflective, almost meditative rhythm that comforted the human spirit. Night after night, skywatchers stepped out under clear, unlit skies, gazing upward into the vast velvet blue, where stars glittered like soft embers across an unbroken dark expanse, long before glass lenses were ground and polished to capture distant rays of celestial light. Astronomers relied upon geometric imagination, artistic skill, and the tactile beauty of parchment to map the movements of the cosmos in the quiet sanctuaries of scholars' towers, monastery scriptoriums, and early university libraries. The heavens were not merely observed with the naked eye. They were translated into intricate geometric figures, carefully calculated tables, and tangible paper mechanisms. The night sky, with its orderly progression of seasonal constellations and wandering planets, presented an eternal puzzle of serene harmony, inviting patient minds to untangle its subtle motions. Scholars spent long, peaceful hours by candlelight, tracing circles within circles, seeking to capture the subtle variations of planetary speed and the rhythmic dance of lunar phases. There was a profound quietude in this work, a gentle communion between human curiosity and the vast, unhurried expanse of space above. The instruments of the era reflected this delicate balance of art and science, blending fine typography, woodcut printing, and vivid hand-applied pigments to transform abstract mathematical theories into objects of luminous grace. Books were no longer silent repositories of static text. They were becoming dynamic, interactive portals through which a reader could gently step into the celestial order, turning paper discs that mirrored the very turning of the celestial spheres. In this contemplative atmosphere, the art of bookmaking aligned seamlessly with the science of astronomy, creating physical works that spoke as much to the aesthetic soul as to the inquiring mind. softly bridging the distance between the earthbound observer and the timeless universe above. Among the most extraordinary creations of this golden age of paper instruments was the work of a master mathematician, cartographer, and printer working along the peaceful banks of the Danube River. In 1540, in Ingolstadt, court astronomer Petrus Apianus published the Astronomicum Caesarum, featuring hand-colored rotating paper volvels that allowed skywatchers to quietly compute planetary positions by turning fine silk threads across paper discs. Dedicated to the Holy Roman Emperor Charles V and his brother Ferdinand, this monumental volume represented the pinnacle of Renaissance printing and scientific illustration. At its heart were complex, layered paper wheels known as volvels, intricate analog computing devices, fashioned entirely from paper, thread, ink, and brass pivots. Each page of the massive folio was a masterwork of visual design, where nested paper discs of varying sizes could be manually rotated across calibrated background scales. By carefully aligning the edges of these paper circles and pulling a delicate thread of colored silk across the face of the instrument, an astronomer, court scholar, or noble patron could determine the exact longitude of a planet, trace the nodes of the moon, or predict the occurrence of an eclipse without performing hours of tedious hand calculation. The rich pigments applied to these pages, lapis blues, deep cinnabar reds, soft saffron yellows, and earthy forest greens, were painted by hand in the print shop, giving every single copy of the book its own unique, luminous character. To turn these wheels was to engage in a silent, tactile dialogue with the cosmos, holding in one's hands a working paper model of Ptolemaic astronomy. Apianus designed these instruments so that even complex orbital irregularities, such as planetary retrogression and epicyclic motion, could be visually demonstrated and measured with simple elegance. The soft rustling of parchment, the smooth sliding of paper upon paper, and the subtle tension of a fine thread resting across a painted constellation transformed the formidable complexity of mathematical astronomy into an inviting, soothing act of discovery. The ingenuity of Apianus lay not only in his mathematical precision, but also in his deep understanding of how human hands and eyes interact with the physical book. Each volvel within the volume served a specialized purpose, functioning as a quiet, interactive guide through different realms of the night sky. One page might feature a paper instrument designed to trace the subtle movement of Mercury or Venus, with intricate scales indicating dragon lines and nodal crossings, while another offered a quiet method for calculating the exact hour of night. By observing the position of the stars relative to the horizon, the use of fine silk threads was a brilliant touch of practical craft, thin enough to cross minute-degree marks without obscuring the fine lettering beneath, yet strong enough to be pulled taut across the disc. The thread acted as an adjustable ray of light, linking the central pivot of observation to the outer scales of time and position. Through these paper mechanisms, the grand, sweeping mechanics of the universe were rendered intimate, accessible, and manageable. A scholar sitting alone in a quiet room at midnight could align the paper sun with the current month, trace the lunar phase wheel, and softly determine the position of the planets, feeling a direct connection to the cosmic clockwork overhead. The craftsmanship required to align multiple rotating paper layers with sub-millimeter accuracy was astounding, demanding seamless cooperation between the astronomer who drew the master diagrams, the woodcut engraver who carved the wood blocks, and the pressmen and colorists who assembled each page. In an era before mechanical clocks could maintain consistent time across long intervals, these paper computers provided an elegant, quiet standard of temporal and astronomical truth, allowing human minds to follow the rhythm of the cosmos through a medium as gentle as paper and string. Looking back at these masterworks from the vantage point of history, we see how the era of paper instruments created a serene bridge between ancient skywatching traditions and the transformative optical discoveries that lay just ahead. Before glass lenses would open up the depths of space to reveal the craters of the moons of Jupiter, and the subtle rings of Saturn, human beings achieved a profound closeness with the heavens through geometric devotion and artistic mastery. The paper volvels of the Renaissance remind us that understanding the cosmos has always been a quiet, patient journey, one that honors precision, beauty, and peaceful contemplation. As the evening hours deepen and the stars continue their silent, unhurried trek across the dark dome of the night, the memory of these ancient paper celestial globes brings a gentle sense of quiet grace. The universe, vast and mysterious as it is, unfolds in orderly, predictable rhythms that can be traced by a steady hand, a thoughtful mind, and the soft movement of silk across painted parchment. The quiet dedication of early skywatchers, who coaxed clarity from the night sky using only paper, thread, and candlelight, offers a soothing reminder of humanity's enduring desire to find harmony within the quiet expanse of the stars, inviting quiet rest as the night settles softly over the world. As the 16th century moved gently forward through the historic towns and tranquil countrysides of Europe, the ancient human quest to comprehend the subtle, rhythmic dance of the sun, moon, and stars began to find new expression within places of quiet sanctuary and extraordinary craftsmanship. For countless generations, skywatchers had relied upon portable instruments like astrolabes, handheld quadrants, and simple wooden staffs held aloft beneath the open sky. But as the need for greater temporal precision grew, natural philosophers came to understand that true observational accuracy required instruments of immense physical scale that could remain completely stationary against the ceaseless passage of time. Within the cool, echoing naves of grand Renaissance churches, an unexpected and fruitful harmony emerged between sacred architecture and observational science. As the massive stone walls, thick masonry pillars, and lofty, shaded vaults provided an environment perfectly sheltered from the wavering heat, gusting winds, and thermal turbulence of the outdoor world. By placing a tiny, meticulously crafted aperture high upon a south-facing facade, astronomers could transform an entire monumental building into a vast camera obscura, allowing a single, focused ray of golden sunlight to travel unimpeded across the quiet interior and fall upon the smooth marble floor below. In 1575, inside the quiet nave of Santa Maria Novella in Florence, astronomer Ignazio Danti pierced a tiny marble hole high in the south facade, projecting a solitary beam of sunlit gold across a calibrated brass line on the floor to track the exact moment of the equinox. As the Earth continued its steady, silent journey along its orbital path, this luminous golden oval glided slowly across the cool marble tiles each day precisely at solar noon, gradually shifting its path by delicate increments as the sun climbed higher toward the summer solstice or descended into the soft, long shadows of winter. The profound stillness within the church offered a restful refuge where the observer could sit in patient, silent contemplation, watching the gentle movement of light trace the true length of the solar year with a mathematical purity that felt both humbled and elevated by the surrounding architectural grace. There were no jarring sounds, no ticking mechanical gears, nor any artificial hands to mark the passing hours. Only the silent, unhurried progression of sunlit gold moving across the inlaid brass meridian, reminding all who watched that the cosmos operated according to a deeply orderly and comforting rhythm. Far to the north, amid the crisp, sea-washed air and gentle tides of the Baltic, a parallel pursuit of celestial clarity was taking shape beneath the wide, open Scandinavian skies, far removed from the bustling noise of continental cities. On a serene island rising quietly from the blue waters between Denmark and Sweden, the natural world offered a landscape of peaceful horizons, where the night sky unfolded in all its unclouded magnificence over rolling pastures, whispering waters, and quiet coastal shores. Here, a monumental effort was undertaken to construct a dedicated sanctuary for skywatching that would elevate the ancient art of visual, unassisted observation to its absolute physical limits, blending fine architectural symmetry, mechanical precision, and unwavering observational discipline, recognizing that even the sturdiest wooden structures could flex or vibrate under the force of heavy sea winds, and that subtle shifts in temperature could alter the alignment of fine sighting mechanisms. The observatory's design incorporated subterranean crypts and chambers dug deep into the firm, insulating earth, where the surrounding soil maintained a constant cool temperature and protected the delicate instruments from every external disturbance. On the peaceful Danish island of Hvin in 1576, astronomer Tycho Brahe built the subterranean observatory of Uraniborg, using massive ivory-inlaid brass quadrants to measure star positions within 2 arc minutes without any optical lenses. Within these sunken, stone-walled rooms, sheltered from the damp evening breezes, observers sat quietly beneath opening roof panels, carefully aligning their sightlines along the burnished edges of giant instruments, whose arcs had been painstakingly engraved and inlaid with fine ivory scales to allow measurements of breathtaking subtlety. Night after night, as the distant constellations drifted overhead in their slow, silent pageantry, the astronomers recorded the precise altitudes and meridian crossings of planets and fixed stars, assembling a vast catalog of celestial positions that far surpassed any collection of data compiled since the classical era of antiquity. The astonishing degree of precision achieved within these quiet, underground vaults demonstrated how deeply the secrets of the cosmos could be understood through human patience, fine engineering, and sustained visual focus, long before a single glass lens had ever been turned toward the evening stars. Together, these 2 remarkable achievements, the golden solar beam tracing its silent path across the cathedral floor in Florence, and the subterranean star chambers cradled by the calm earth of Hvin, represented the glorious, quiet summit of classical observational astronomy. They demonstrated that before the advent of optical magnification, humanity had already learned to listen to the silent, harmonious language of the universe with profound care, utilizing stone, brass, sunlight, and shadow to map the vast expanse of the sky. In both the warm, filtered light of the Italian nave and the cool, nocturnal peace of the northern island crypts, the study of the heavens was experienced not as a hurried search for sudden revelation, but as a deeply restful practice of quiet attention, where the observer became fully attuned to the slow, eternal turning of the cosmic sphere. The extraordinary wealth of precise data gathered during these calm, watchful years would soon serve as the indispensable foundation for future astronomers who sought to uncover the true geometric laws governing planetary motion, seamlessly bridging the ancient era of unassisted skywatching and the approaching epoch of telescopic exploration. As night settled gently over the silent fields of Hvin and the dark, vaulted aisles of Santa Maria Novella, the stars continued their timeless, peaceful journey across the deep blue night, leaving behind a lasting legacy of order, clarity, and quiet wonder to lull the resting world into a deep and soothing sleep. As the golden twilight of late summer slowly faded into deep indigo over the Baltic Sea during the final decades of the 16th century. An extraordinary quietude settled over the small island of Hven, resting peacefully in the waters of the Øresund Sound between Denmark and Sweden. Here, far removed from the clamor of bustling European cities and the restless courtly life of mainland castles, the night sky revealed itself in immaculate, velvety clarity, unmarred by smog or artificial light, upon this secluded island, gifted to him by King Frederick II. The Danish astronomer Tycho Brahe established a grand sanctuary dedicated entirely to the patient, unhurried study of the heavens. He constructed high-walled medicinal gardens, intricate water-powered paper mills, and the magnificent palace observatory of Uraniborg, whose spires and open-air terraces reached upward toward the celestial vault. In this era long before the invention of the glass telescope, skywatching was a deeply tactile, visually demanding, and reverent human endeavor. Astronomers relied entirely on their own keen vision, aided by massive instruments built of seasoned wood, heavy iron, and burnished brass. Great quadrants, sextants, and armillary spheres designed to divide the circle of the heavens into minute fractions of a degree. Night after night, as cool mists rolled off the gentle waves and carpeted the island's coastal pastures, Tycho and his devoted team of young scholars wrapped themselves in thick wool capes and climbed to the upper balconies of Uraniborg. There, under the quiet gaze of the constellations, they tracked the slow, steady wanderings of Mars, Jupiter, and Saturn, charting the moon's subtle variations and cataloging the positions of fixed stars with an accuracy never before imagined in human history. Yet as the years passed, Tycho began to notice how even the gentlest ocean winds sweeping across the open terraces could cause subtle, almost imperceptible tremors in the long wooden sighting arms of his instruments, prompting him to dream of an even quieter refuge where the air itself would remain completely still. Recognizing that true precision required an environment entirely isolated from the shifting elements, Tycho conceived an ingenious architectural design that turned away from the skybound towers and retreated instead into the protective embrace of the earth. In 1584, on the quiet island of Hven, Danish astronomer Tycho Brahe constructed St. Jørneborg, an underground observatory with subterranean study rooms sunk deep into the soil to protect his delicate instruments from the ocean breeze. Named St. Jørneborg, or the Castle of the Stars, this subterranean facility consisted of 5 distinct observation crypts sunk deep into the grassy hilltop, connected beneath the surface by central study rooms, heated work chambers, and stone-paved corridors. From the outside, only the low, rounded wooden domes of the instrument crypts protruded above the lush lawn, looking like humble, sod-covered mounds resting gently against the island landscape. Beneath the ground, however, lay a masterpiece of scientific architecture Massive stone pillars were planted firmly into the dense glacial bedrock below, providing completely isolated, vibration-free foundations for Tycho's grandest brass instruments. The thick layer of surrounding earth acted as a natural blanket, keeping the subterranean rooms at a wonderfully stable temperature throughout both the freezing Scandinavian winters and the mild summers, preventing the delicate metal arms of the quadrants from expanding or contracting due to sudden thermal shifts. Stone walls lined with warm fir paneling sheltered the astronomers from the damp sea air, while small tile stoves provided a gentle, comforting heat during long winter night watches. When observations were ready to begin, the assistants had only to turn wooden hand cranks to slide back the hemispherical roof covers, exposing small, targeted openings to the night sky, while the observers remained snug, dry, and completely shielded from the ocean winds blowing across the grassy plain above. To step down the curved stone steps into St. during the quiet hours of midnight was to enter a realm of profound peacefulness, where the earthly realm and the star-filled cosmos met in quiet, undisturbed communion. The air inside the subterranean chambers carried a soothing, restful aroma, a blend of moist earth, freshly carved pine, rich linseed oil used to preserve heavy wooden beams, and the sweet, subtle warmth of beeswax candles flickering in wall niches. Soft, golden candlelight danced across the burnished surfaces of copper rings, brass sight vanes, and finely calibrated scale arcs, casting long, gentle shadows that rested motionless against the curved masonry walls. Looking straight up through the open hatch of an instrument crypt, the night sky appeared as a pristine square of deep obsidian velvet, framed by the dark silhouette of the roof structure, through which bright stars and glowing planets drifted with silent, majestic grace. Seated comfortably in wooden armchairs built directly into the recessed stone walls, observers adjusted fine thumb screws with slow, deliberate care, aligning sighting vanes with the steady, unblinking light of distant stars. Within these sunken chambers rested Tycho's grandest creations, a magnificent wooden sextant spanning nearly 6 feet across, and an equatorial armillary sphere designed to track celestial coordinates with effortless fluidity. The silence within the underground observatory was deep and sacred, broken only by the low, measured voice of an assistant calling out timing marks, the steady, rhythmic tick of a water clock, the soft scratch of an iron gall ink quill recording numerical coordinates into thick rag paper logs, and the faint, comforting whisper of wind passing harmlessly over the sod roof above. Here, shielded from the cold drafts and darkness of the open air, the astronomers experienced an unbroken state of calm concentration, their minds floating serenely among the planetary spheres, while their bodies remained anchored securely within the warm, quiet depths of the island's soil. The quiet nights spent within the underground chambers of St. yielded what would become the greatest observational legacy of the pre-telescopic world, proving that true scientific insight often springs not from grand, noisy declarations, but from quiet, grounded patience. The thousands of meticulous planetary positions recorded within those damp, wood-lined vaults were kept with such extraordinary fidelity that years later they allowed Johannes Kepler to uncover the elliptical paths of the planets and revolutionize our understanding of the solar system. Yet beyond its momentous contributions to the story of astronomy, St. Journeyborg endures in the imagination as a testament to the soothing harmony that can exist when human curiosity nestles itself respectfully into the quiet contours of the natural world. Long after the last candles were snuffed out and the subterranean trapdoors were closed against the dawn, the underground observatory retained its gentle warmth and steady silence, guarding the memory of those peaceful hours spent watching the celestial clockwork turn above. The island of Hvin slowly returned to its nocturnal slumbers, cradled by the gentle tide of the Orsund, while overhead the timeless procession of stars illuminated the dark European sky. As the evening draws to close and the constellations continue their slow, ancient voyage across the dark dome of the night sky, the memory of Tycho Brahe's hidden star castle offers a soothing reminder of the comfort found in quiet places. Resting deeply like the sunken chambers of Hvin, sheltered from the restless winds of the world, we can release the busy thoughts of the day, feeling securely grounded in the silent stability of the earth, while the quiet beauty of the universe carries us gently off to rest. As the 16th century gently yielded to the 17th, the human relationship with the night sky rested in a quiet, contemplative pause. For generations, astronomers and skywatchers had stood beneath the clear, dark heavens, observing the unhurried arc of planets and constellations, with nothing more than their own patient eyes, simple sights, and wooden quadrant instruments in the stillness of late evening, when the sounds of daily life faded into soft silence across towns and countryside. These early cartographers sought to translate the boundless vault of the heavens into something tangible, orderly, and serene. The night sky was far more than an abstract expanse. It was a grand celestial clock and a source of profound solace, turning with dependable perfection above a sleeping world. Each season brought its familiar stars, rising silently over the eastern horizon, Orion's bright belt in the crisp winter air, the sweeping curve of the Swan floating along the summer Milky Way, and the steady, reassuring pivot of the Little Bear around the North Pole. To capture this cosmic harmony on paper required not only mathematical precision and careful observation gathered over decades by figures like Tycho Brahe, but also a deep artistic reverence for the quiet majesty of the firmament. Across the quiet study rooms of Europe, illuminated by the warm, flickering flame of beeswax candles, mapmakers laid out heavy sheets of rag paper, fine ink pots, and sharp metal tools. They worked slowly, tracing the positions of hundreds of ancient stars whose light had traveled across vast reaches of space to reach human eyes. This practice of celestial cartography became a soothing bridge between earth and sky, allowing the observer to hold the cosmos in their hands, tracing with a gentle finger the quiet paths of light that guided travelers, sailors, and dreamers through the dark. In this peaceful period, just prior to the birth of optical instruments, the sky was mapped with an intimacy and poetic beauty that transformed standard stellar coordinates into works of enduring art, inviting any who looked upon them to breathe deeply and rest beneath the calm, timeless order of the stars. It was within this tradition of quiet craft and devotion that a landmark work of sky mapping came to light in southern Germany. In 1603, in Augsburg, celestial cartographer Johannes Bayer published Uranometria, engraving 51 delicate copperplate star charts that first introduced Greek letters to classify stars by their gentle radiance. Bayer, a lawyer by profession, whose true passion belonged to the quiet studies of astronomy and geometry, named his atlas after Urania, the ancient muse of astronomy. The publication of Uranometria marked a moment of profound transformation in how humanity visualized and spoke of the night sky. Up until that time, stars were often identified through long, descriptive Latin or Arabic phrases that recounted their physical positions within classical figures, such as the bright star in the left shoulder of the giant, or the dim light at the tip of the tail. Bayer introduced an elegant, harmonious simplicity by assigning the letters of the Greek alphabet to the stars within each constellation, generally ordering them from the brightest and most prominent down to the faintest visible to the unaided eye. The brightest star in a constellation became Alpha, the next Beta, followed by Gamma, Delta, and onward down the line of gentle Greek script. To give physical form to this system, Bayer oversaw the meticulous engraving of 51 copper plates, a painstaking printmaking process that allowed for remarkably fine lines, soft shading, and pristine details. 48 of these plates were dedicated to the traditional constellations handed down from Ptolemy's ancient catalogue, while a 49th plate captured 12 new southern constellations recently reported by Dutch navigators who had sailed beneath unfamiliar skies. The final 2 plates provided comprehensive maps of the entire northern and southern celestial hemispheres. When printed, the star charts presented a breathtaking synthesis of art and science. Graceful, dotted outlines of mythical heroes, animals, and instruments overlaid upon precise grids of celestial coordinates, with stars depicted as radiant points of light of varying sizes according to their magnitude. The heavy paper pages of Uranometria felt substantial and soothing to hold, offering a quiet, structured way for astronomers across different lands to communicate with one another using a shared, serene astronomical language that remains in use to this day. The brilliance of Bayer's system lay not only in its mathematical utility, but in the restful aesthetic order it brought to the human experience of stargazing. By associating each star with a specific letter and constellation name, such as Alpha Centauri or Beta Tauri, he created a gentle vocabulary that allowed skywatchers to read the night sky almost like a book of quiet poetry. Looking up into the deep indigo night, an observer could trace the hierarchy of light within a constellation, noticing how Alpha shone with a clear, steady beam, while its neighboring Beta and Gamma gleamed with a slightly softer, more muted intensity. This systematic classification encouraged a deeper, more mindful engagement with the night air, inviting people to sit in stillness and observe the subtle variations in brightness and hue that had previously gone unnamed. The copperplate engravings themselves were designed with extraordinary care and aesthetic restraint, rather than crowding the pages with harsh lines or heavy figures. Bayer's charts featured delicate, translucent figures sketched in soft contours, allowing the star positions themselves to take center stage. The stars were plotted with unprecedented accuracy for the era, drawing upon Tycho Brahe's master catalogue of stellar positions, which were the most precise observations ever made before the invention of the telescope. Furthermore, Bayer took the innovative step of printing the constellation figures as seen from the perspective of an observer standing on Earth looking up, harmonizing ancient artistic tradition with the practical needs of night sky observers. As copies of Uranometria made their way into universities, observatories, and private libraries across Europe, they became prized treasures for anyone who sought peace in the study of the heavens. Scholars and dreamers alike could spend quiet evenings tracing the engraved lines of Pegasus, spreading his wings across the dark, or Cygnus gliding along the star-dusted lane of the Milky Way, finding in these serene pages a reflection of the deep, quiet rhythm that governs the cosmos. As the night deepens and the world below settles into restful slumber, the legacy of these early star maps continues to offer a sense of calm and timeless beauty. Bayer's Uranometria stood at a unique threshold in human history, the culmination of thousands of years of naked-eye astronomy, published just a few short years before the invention of the telescope would forever expand human vision into deeper reaches of space. Yet even as optics revealed millions of previously unseen worlds, the gentle Greek designations and beautiful constellation boundaries established in 1603 remained the foundational tapestry of celestial cartography. There is something profoundly soothing in the realization that when we look up at the night sky tonight, we are seeing the very same stars that Bayer catalogued with such care on his copper plates in Augsburg. The steady shine of Vega, the warm red glow of Aldebaran, and the faint, delicate points of light that compose the distant constellations still follow their ancient, unhurried paths across the darkness. The act of mapping the sky was ultimately an expression of human hope and quiet wonder, an effort to find structure, peace, and beauty in the immense silence of the universe. As we let go of the thoughts and activities of the day, we can draw comfort from this enduring celestial order. The stars do not hurry, they do not falter. They simply shine on, softly illuminating the deep night, guiding our thoughts toward stillness, quiet reflection, and a peaceful, restorative sleep under the watchful, eternal canopy of the heavens. As the early years of the 17th century unfolded quietly across Europe, the night sky remained an enduring sanctuary for those who spent their evening hours tracing the slow, deliberate movements of the celestial sphere. For generations, natural philosophers and astronomers had regarded the distant heavens as a realm of perfect, unalterable constancy, where the fixed stars shone with unwavering permanence far above the shifting, mortal cycles of the earth below. Yet, on crisp autumn evenings, in the heart of the continent, observant eyes, watching from quiet courtyards and high tower balconies, began to catch subtle glimpses of rare cosmic events that gently challenged these long-cherished beliefs. The atmosphere over the European countryside was remarkably dark and clear, unmarred by the bright artificial glare of modern times, allowing the faintest gradients of starlight to stand out against the deep indigo mantle of midnight. It was in this peaceful atmosphere of quiet inquiry that the German mathematician and astronomer Johannes Kepler pursued his study of planetary motion while serving as the imperial mathematician in the historic city of Prague. In October 1604, in Prague, mathematician Johannes Kepler stepped into the evening chill to observe a brilliant new star in the constellation Ophiuchus. Watching its soft luminescence quietly fade over 18 months, the sudden appearance of this new star, which shone with a steady, diamond-like brilliance, rivaling even the bright light of nearby Jupiter and Saturn, stirred a profound sense of wonder within Kepler's analytical mind. Night after night, wrapped in heavy woolens against the descending Bohemian frost, he returned to his open courtyard to measure the position of the intruder relative to the surrounding stellar backdrop, recording its location and gradual diminish in brightness with painstaking care. For many months, as the autumn gave way to the deep silence of winter, and winter slowly softened into the gentle warmth of spring and summer, the temporary beacon held its place without shifting a fraction of a degree, proving beyond doubt to Kepler that it belonged far beyond the realm of Earth's atmosphere, nestled high among the distant stars themselves. This silent cosmic visitor did not streak across the sky like a fleeting meteor, but lingered with a calm and dignified presence, slowly dimming month by month, until it eventually dissolved once again into the black velvet of the nighttime sky. Through this steady, peaceful observation, Kepler gained a renewed appreciation for a universe that was dynamic yet orderly, governed by vast geometric principles that could be understood through patient study and quiet contemplation. The memory of that slowly fading star remained with him as he continued his endless calculations, working to uncover the harmonious, elliptical paths that guided the planets on their eternal journeys around the sun. While Kepler was immersed in numerical tables and the geometry of planetary orbits in Central Europe, a complementary revolution in visual astronomy was quietly taking shape across the foggy, river-laced countryside of England. For thousands of years, human beings had gazed upon the pale disk of the moon with naked eyes, interpreting its silvery light and mottled surface as smooth, mystical patterns across a flawless, ethereal orb. The recent development of basic optical instruments in the Netherlands, where spectacle makers had discovered that combining convex and concave glass lenses could make distant objects appear nearer, had opened a quiet new doorway for human sight. It was not long before these early instruments, constructed from simple tubes of rolled paper, bound leather, and hand-polished glass lenses, were brought across the English Channel and turned upward into the peaceful stillness of the night. On July 26, 1609, 4 months before Galileo turned his telescope to the heavens, English mathematician Thomas Harriot used a 6-bower perspective tube at Sion House to sketch the moon's softly shadowed craters. Sitting quietly in the garden of Sion House, along the gentle, reflective waters of the River Thames near London, Harriot leaned toward the narrow aperture of his modest instrument as the summer twilight slowly faded into dusk. Looking through the pale glass, the familiar, uniform surface of the moon dissolved into a landscape of unexpected detail, revealing rolling topography, darkened hollows, and delicate, crescent-shaped shadows that shifted softly with the changing angle of sunlight. With a steady hand and fine quill, Harriot recorded these subtle lunar features upon paper, creating what would become the very first telescopic drawing of an extraterrestrial body. His sketches were not sensational claims, but quiet, intimate records of a peaceful evening spent exploring the fine texture of another world. Although his 6-bower perspective tube offered only a modest field of view and required great patience to steady against the evening breeze, it was sufficient to reveal that the moon was not a perfectly smooth crystal sphere, but an uneven physical body with mountains and plains that gathered sunlight and cast long, soft shadows across its quiet surface. In the seclusion of his estate, Harriot continued to refine his lunar maps over subsequent months, systematically tracing the gradual movement of light across the cratered terrain. As the moon progressed through its monthly phases, content to observe, reflect, and document without any urge to seek immediate public acclaim. These two historical moments, unfolding peacefully within a few short years of each other, marked a tranquil threshold in humanity's relationship with the cosmos, bridging the ancient tradition of naked-eye skywatching with the limitless possibilities of optical exploration, where earlier observers had been restricted to measuring only what the human eye could naturally perceive. Thinkers like Kepler and Harriot showed that combining careful mathematical record-keeping with simple optical tools could unlock profound truths about the universe. The discovery that the celestial realm could produce temporary stars that flared and faded over 18 months, paired with the revelation that the moon possessed a textured, Earth-like surface, gently softened the rigid boundary that ancient philosophy had placed between the heavens and the earth. Above all, these quiet discoveries brought a deep sense of calm, inviting human beings to look up at the midnight sky, not with apprehension, but with a restful and open-minded curiosity. As the night air settled over the slumbering fields of 17th century Europe, the stars continued their slow, silent rotation across the dome of space, shining with the same steady, comforting radiance that had watched over humanity for uncounted generations. The early perspective tube had lifted a veil on the cosmos, showing that even the quietest corners of the sky were filled with subtle detail and timeless harmony waiting to be discovered. Gazing back across the centuries, one can almost feel the cool evening air of that Prague courtyard and hear the gentle murmur of the Thames at Sion House, finding rest in the knowledge that the universe remains a serene, orderly, and beautiful home for human wonder. As the long midsummer afternoon faded softly into dusk across the English countryside in the summer of 1609, a deep and restorative quiet settled over the historic grounds of Sion House. Situated along the serene, curving banks of the River Thames, just west of London, the estate offered a peaceful sanctuary of lush green lawns, ancient branching trees, and gentle, slow-moving waters that reflected the soft pastel colors of the lingering twilight sky. For generations, those who looked up at the heavens had done so through the lens of ancient philosophy, viewing the night sky as a realm of timeless perfection and unchangeable harmony. The moon, hanging like a pale silver disk in the evening air, was imagined to be entirely smooth and unblemished, a pristine orb of ethereal substance, suspended far above the imperfect, changing nature of the earth below. Yet, far across the narrow waters of the sea in the Netherlands, skilled spectacle makers had recently discovered that by placing convex and concave lenses of ground glass together inside a light parchment or leather tube, distant objects could be brought astonishingly close to the human eye. News of these curious perspective glasses began to travel quietly along established trade routes and within the thoughtful correspondence of scholars, reaching inquisitive minds who spent their lives contemplating the subtle structures of the natural world. Among them was Thomas Harriot, a scholar of quiet brilliance and profound intellectual curiosity, whose steady devotion to mathematics, optics, and natural philosophy had long flourished under the generous patronage of the Earl of Northumberland. Harriot was a patient and methodical observer, accustomed to spending long, contemplative hours in the quiet stillness when the rest of the world was fast asleep, measuring the subtle refraction of light rays through triangular prisms, charting the mathematical paths of light through water, and contemplating the fundamental order of the universe in his peaceful, book-lined study at Sion House, surrounded by handwritten manuscripts, delicate brass drawing instruments, and sheets of heavy rag paper. He held one of these newly arrived optical tubes, preparing to turn its magnifying lenses away from the familiar horizon of the Earth and upward into the vast, calm expanse of the summer night. On the evening of July 26th, 1609, as the dusk deepened into a soft, indigo twilight, Harriot stepped out from his study into the quiet gardens of Sion House. The air was comfortably cool and still, carrying only the soft, rustling sound of evening breezes moving through the leaves, and the slow, rhythmic lapping of the river against the grassy shore. Above the dark, silhouetted treetops, a thin crescent moon hung gracefully in the western sky, its gentle light casting soft, subtle shadows across the dew-kissed lawn. Carefully bracing his arms to steady his view, Harriot pointed a 6-bower Dutch perspective glass toward the evening sky, sketching the earliest surviving telescopic map of the moon's quiet craters. Through the narrow field of view provided by the small, hand-polished lenses, the smooth and featureless sphere of ancient tradition gently dissolved into a detailed and tranquil physical landscape. Harriot observed with quiet wonder that the boundary between the illuminated portion of the crescent and the dark side of the lunar disk was not a crisp or perfect mathematical curve, but rather a delicate, ragged line where sunlight played softly across uneven ground. Small, bright points of light appeared just beyond the edge of daylight, catching the sun like distant mountain peaks rising above deep valleys that remained shrouded in nocturnal shadow. As he brought his ink quill to paper, he rendered these subtle observations with soft, deliberate strokes, tracing the irregular oval boundaries of craters, the broad dark plains, and the gentle contours of lunar topography. In that single, tranquil act of observation and drawing, performed without fanfare or dramatic declaration, Harriot became the first human being in recorded history to document the physical surface of another celestial body as seen through an optical instrument. His drawing captured the moon not as an abstract or untouchable concept, but as a real physical place, possessing gentle highlands, quiet depressions, and vast, silent basins that echoed the varied textures of our own Earth. The resulting drawing was both modest and elegant, capturing the essence of Harriot's disciplined approach to natural inquiry. Upon a single sheet of cream-colored paper, he inscribed a clean circle to represent the lunar disk, carefully shading the darker regions that we now know as the lunar maria, and marking the subtle indentations that broke the smoothness of the crescent's edge. He noted how the shadows within the craters shifted almost imperceptibly as the night deepened, providing clear visual evidence that the lunar surface was subject to the very same interplay of light and shadow that shapes landscapes on Earth during the quiet hours of dawn and dusk. Holding a 6-bower perspective glass steady required immense physical patience as the small tube had to be held firmly by hand or balanced upon a simple wooden rest, while its narrow field of view meant that only a tiny fraction of the moon could be examined at any one moment. Yet, within these physical limits, Harriot found a deep and restful sense of discovery. The craters he so carefully mapped were not jagged or harsh, but appeared as peaceful basins carved into the ancient crust of the moon, filled with soft, velvety shadows that lengthened and shortened in harmony with the lunar cycle. His delicate map served as a quiet testament to the rewards of patient skywatching, demonstrating how a simple arrangement of glass lenses could expand the boundaries of human vision without disrupting the silent serenity of the night. Over the following months, Harriot returned to his garden night after night, continuing to observe the moon as it grew full and receded again, producing a series of increasingly detailed maps that recorded the complex topography of craters, mountain ridges, and glowing ray systems across the lunar surface. This peaceful milestone at Sion House marked the quiet beginning of a major shift in human understanding, gently opening a new door through which we would come to view our place in the universe. Long before larger telescopes were pointed toward the banded atmosphere of Jupiter or the intricate rings of Saturn, Harriot's early drawing quietly demonstrated that the celestial realm was continuous with the natural world, composed of physical landscapes that invited thoughtful study and quiet reflection. The River Thames continued its slow, eternal journey past the gardens, carrying the shimmering reflections of the summer stars down toward the sea, while high above, the moon drifted through the clear indigo sky, its ancient craters resting in perpetual silence. There was no urgent pressure to publish his findings or seek public acclaim. Harriot simply placed his lunar sketch alongside his extensive mathematical and scientific notes, content to have spent a peaceful evening in quiet communion with the night sky. The calm, unhurried pace of his work reminds us of the serene quality of true exploration, which so often takes place in moments of solitary stillness, far removed from the noise and distraction of daily life. As the night deepens and the world draws quiet, the same moon that Harriot observed over 4 centuries ago continues to glide serenely through the heavens, casting its gentle, silver light down upon the sleeping earth, offering a comforting sense of continuity and inviting us to drift into a deep, restful sleep under the very same timeless canopy of stars. In the quiet darkness of the night sky, long before human eyes had ever gazed through glass lenses to magnify the distant heavens, people looked up at the stars with a deep sense of reverent stillness and quiet wonder. For centuries, across ancient civilizations and scholars of antiquity, the overarching framework of astronomy rested upon a profound philosophical conviction that the universe was constructed of absolute geometric perfection. The great thinkers of Greece, from Pythagoras and Plato to Aristotle and Ptolemy, believed that because the celestial realm was unblemished and eternal, every planet, moon, and star must move along paths of flawless, uniform circles. In their minds, the circle was the only shape worthy of the divine, a form without beginning or end, embodying eternal balance, unbroken symmetry, and timeless majesty. To explain why the planets sometimes seem to slow down, pause, or temporarily wander backward across the backdrop of fixed stars in what we now call retrograde motion. Ancient astronomers devised intricate systems of nested circles called deferents and epicycles. These mathematical constructions allowed them to preserve the sacred ideal of circular motion, while attempting to fit the actual observations seen from Earth. When Nicolaus Copernicus introduced his breathtaking heliocentric model in the 16th century, placing the Sun near the center of the planetary system, he kept this ancient commitment to circular paths intact, continuing to use small epicycles to match the observed positions of the wandering lights. Yet, beneath the serene surface of these traditional models, tiny discrepancies remained between theoretical calculations and the actual positions of the planets as they moved through the constellations. Resolving these subtle differences would require an extraordinary combination of observational precision and mathematical devotion. In the final years of the 16th century, the Danish nobleman Tycho Brahe spent decades at his island observatory of Uraniborg, meticulously recording the positions of the stars and planets with unprecedented accuracy, using massive brass quadrants, sextants, and armillary spheres. Upon Tycho's passing, his vast collection of observational logbooks passed into the hands of his brilliant assistant, Johannes Kepler. Settling in Prague, a city of quiet stone bridges, soaring spires, and mist-wrapped rivers flowing beneath the night sky, Kepler inherited a treasure trove of cosmic data. He understood that these handwritten numbers were not merely ink on parchment, but the quiet transcript of the heavens themselves, waiting for someone to discern the true geometry hidden within their quiet rhythm. Among all the planetary observations inherited from Tycho Brahe, none proved more enigmatic or persistently challenging than those belonging to the planet Mars. Moving across the zodiac with a distinct, warm reddish tint, Mars had long puzzled skywatchers with its unusually variable speed, changing brightness, and noticeably uneven paths. Kepler set out to solve the mystery of Mars first, believing that if he could unlock the true orbit of this single planet, the secret of all planetary motion would naturally follow. The task, however, required immense mental endurance, as every single calculation had to be performed entirely by hand, using complex trigonometric formulas and endless columns of arithmetic. To map the true position of Mars, Kepler first had to determine the precise orbit of the Earth itself, since human observers were measuring Mars from a moving platform that shifted position continuously throughout the year. For month after month, Kepler worked in total quiet, testing dozens of geometric arrangements of circles, eccentric centers, and equant points. Again and again, his proposed circular models came remarkably close to matching Tycho's observations, missing the true positions of Mars by only 8 arc-minutes, an angle so small that it is less than a quarter of the width of the full moon as seen by the human eye. Many earlier scholars might have considered such a microscopic difference acceptable, attributing it to minor observational error. Yet Kepler held Tycho's meticulous work in such high regard that he knew those 8 arc-minutes could not be dismissed. They contained the quiet truth of how the universe actually moved. Setting aside the ancient doctrine of circular perfection that had guided astronomy for over 2,000 years, Kepler courageously began exploring non-circular shapes, experimenting first with egg-like ovals, and eventually turning his attention to the elegant properties of the ellipse. Working late by candlelight in Prague in 1609, Johannes Kepler calculated the orbit of Mars over 5 painstaking years, discovering that planets trace gentle ellipses around the sun rather than perfect circles. This landmark realization transformed the understanding of space into something profoundly natural and serene. An ellipse is a smooth, continuous curve formed around 2 internal points known as foci. In Kepler's new vision of the solar system, the sun occupied one focus, while the other remained empty, allowing the planet to glide around its star in a wide, balanced, and perfectly predictable oval loop. Kepler's discovery of the elliptical path of Mars, which he published in his masterwork Astronomia, Nova Asterisk, or New Astronomy, did not merely replace one geometric shape with another. It revealed a deep, breathing harmony inherent to the physical laws of the universe. Along with the elliptical shape of planetary orbits, Kepler recognized that a planet does not move at a constant, rigid speed as it travels through space. Instead, as a planet glides along its elliptical path, it speeds up slightly as it approaches perihelion, the point of its orbit closest to the gentle warmth of the sun, and then gradually slows down as it sails toward aphelion, its farthest point in the cool, quiet depths of space. Kepler expressed this phenomenon through a second elegant principle. An imaginary line connecting the sun to planet sweeps out equal areas of space in equal intervals of time. This meant that the motion of a planet was not an artificial mechanical rotation, but a fluid and organic cadence, accelerating and decelerating in a natural rhythm that mirrored the gentle ebb and flow of life on Earth. The universe was no longer seen as a set of rigid, crystalline gears, but as a vast, quiet sanctuary governed by simple, unified mathematical principles that harmonized distance, time, and speed. Decades later, Sir Isaac Newton would build upon Kepler's foundational work to demonstrate how the invisible pull of gravity naturally produces these very elliptical paths, binding the moons planets and distant stars together in an eternal, self-sustaining embrace. Yet, even before the physical cause of gravity was fully understood, Kepler's elliptical orbits brought an overwhelming sense of peace and order to the study of the skies. The heavens were shown to be neither chaotic nor artificially constrained, but gracefully balanced, carrying each world along a smooth, endless trail through the calm darkness of space. As we settle into the quiet of the night, surrounded by the soft shadows of the evening, we can reflect on the quiet dedication of those ancient skywatchers who sat beneath the stars, patiently unraveling the secrets of the cosmos. Above us, far beyond the reach of human noise, the planets continue their silent journey, tracing their gentle ellipses in the vast, peaceful dark, holding the world in a quiet and steady embrace while all of nature rests. As the 17th century quietly dawned across the peaceful towns and rolling countryside of Europe, a subtle transformation began to fold itself into the long-standing tradition of stargazing. For thousands of years, skywatchers had stood beneath the stillness of night, relying entirely upon the unassisted human eye to measure the movements of wandering planets and trace the ancient patterns of constellations across the dark vault above. Yet, as glassmakers in quiet workshops refined their craft and philosophers began to align polished convex and concave lenses within slender tubes, a new manner of seeing emerged, one that did not shatter the peaceful quietude of the night, but rather deepened humanity's quiet relationship with the heavens. The earliest refractor telescopes were modest instruments, constructed from simple tubes of wood, brass, or rolled cardboard, carrying small glass lenses that gathered faint glimmers of light and expanded them into clear, intimate fields of view. To step into an astronomer's study during this delicate era was to enter a sanctuary of patience, quiet reflection, and stillness, where long hours were spent waiting for evening clouds to part, for shadows to lengthen across wooden desks, or for the bright arc of the sun to reach a comfortable angle across a shuttered room. The practice of astronomy in these early decades was not a hurried pursuit of rapid discovery, but rather a slow, meditative observation of the natural world in its grandest, most serene dimension. Scholars worked in dark-paneled rooms where dust motes drifted lazily through thin beams of sunlight, or stood wrapped against the midnight chill on high observatory turrets, while the rest of the world slept peacefully below in silent villages. Through these simple tubes of glass, the sky ceased to be a flat canvas of static points and revealed itself as a living, vast depth filled with subtle gradations of shade, movement, and form. The universe, which had once seemed so distant, mysterious, and unyielding, began to offer gentle secrets to those willing to sit quietly in the dark, watching without expectation, and recording what they saw with steady, careful hands. In the early spring of 1611, as the crisp winter air began to give way to the softer breezes of March. A mathematician and Jesuit astronomer named Christoph Scheiner was working quietly in his study in the Bavarian town of Ingolstadt. Curious about the true nature of the sun's brilliant face, which ancient philosophy had long held to be a flawless sphere of pure ethereal perfection, Scheiner sought a safe and reliable way to study the daytime sky without straining or damaging his vision. Rather than gazing directly through his optical tube at the overwhelming glare of the midday sun, he devised a peaceful and elegant technique of camera obscura projection. In March 1611, in Ingolstadt, astronomer Christoph Scheiner projected the sun's light through a refractor telescope onto a clean sheet of paper, recording dark sunspots as they drifted steadily across the glowing solar surface. In the quiet dusk of his shuttered room, the bright disk of the sun appeared illuminated upon the white page like a soft, living parchment miniature. There, held within the quiet stillness of paper and shade, Scheiner watched as small, shadowy markings, dark, irregular sunspots, moved with slow, deliberate grace across the glowing circle. Day after day, as the sun climbed its familiar, peaceful path above the rooftops of Ingolstadt, he carefully traced these delicate smudges with pen and ink, noting how their shapes gradually shifted and how their positions moved in unison from one edge of the solar disk toward the other. This gentle rotation of the sun was not a chaotic disruption of the cosmos, but a serene demonstration of cosmic rhythm, revealing that even the central star of our solar system possessed its own quiet breath, rotating slowly on its axis over the course of weeks. The paper projections allowed for a restful, deeply reflective form of study, where the sun's vast power was softened into a quiet image that could be examined without strain, casting a warm and gentle light across the wooden desk where the astronomer sat in quiet contemplation. As the seasons turned toward the deep dark of winter a year later, another quiet observer raised his telescope toward the cold, clear evening skies over Franconia. In December 1612, German astronomer Simon Marius looked through an early refractor telescope in Ansbach to observe the Andromeda Nebula, comparing its gentle radiance to a candle flame glowing through a thin sheet of horn. Standing beneath the wide, frosty expanse of the December night, where stars sparkled like distant ice in the clear air, Marius focused his slender tube upon a faint, misty patch of light in the constellation of Andromeda, a spot long known to ancient Persian astronomers as a small cloud, yet never before seen through the magnifying power of glass lenses. In the quiet stillness of Ansbach, as the winter wind whispered softly outside his window, the early telescope gathered the faint, milky glow and focused it into a soft oval of light that seemed to hover without weight among the background stars. The comparison Marius chose, that of a small flame seen through a translucent sheet of horn, such as those used in traditional quiet lanterns of the era, captured precisely the soft, diffused quality of deep space illumination. It was not a sharp or jarring brightness, but a gentle, ethereal haze that seemed to breathe softly in the dark field of view. To look upon the Andromeda Nebula in those early winter nights was to catch a glimpse of deep cosmic distance, a place where light traveled across unthinkable gulfs of space, only to fall softly upon a piece of polished glass and enter a human eye. Marius made his notes by the dim light of a desk lamp, recording the peaceful appearance of this distant cloud, without fully knowing that he was gazing upon an entire island universe of billions of stars, situated millions of light years away across the silent expanse. These early telescopic observations marked a profound, yet deeply comforting shift in how humanity understood its place within the vastness of space. The discoveries made by early astronomers were not loud or violent disruptions, but quiet invitations to wonder, softening the rigid boundaries of ancient cosmology into a deeper, more nuanced appreciation of nature's quiet grandeur, where older views had insisted upon a rigid, unblemished celestial sphere. The telescopes of the early 17th century revealed a universe of movement, light, and soft shadow, a world where suns turned gracefully in place, and distant clouds of starglow rested in the dark like quiet lanterns. The simple acts of projecting sunlight onto paper or gazing through a glass tube at a faint nebula demonstrated that the cosmos was filled with gentle processes unfolding on scales both immense and serene. For the observer standing in the quiet of the night, wrapped in heavy wool while the stars drifted overhead, the telescope became a bridge between the intimate quiet of human thought and the vast, silent depths of the night sky. As the hours passed and the constellations made their slow, steady march toward the dawn, those early skywatchers retired to their rest with a renewed sense of peace, knowing that the universe above was not cold and indifferent, but a vast and beautiful home filled with quiet light waiting to be discovered. And so, under the watchful gaze of ancient stars and the soft promise of new instruments, the world drifted into a restful sleep, lulled by the eternal, quiet rhythms of the heavens. As autumn settled over northern Europe in the early decades of the 17th century, a quiet revolution was unfolding within the dimly lit study rooms of natural philosophers and skywatchers. For uncounted centuries, observing the heavens had required astronomers to turn their bare eyes directly upward into the vast expanse of the night, scanning the dark canvas for the faint glimmer of stars and the slow, wandering paths of planets. Yet, as glass lenses and optical theory began to refine the art of observation, scholars discovered gentler, more delicate methods for studying the brightest lamp of all, our sun. Direct inspection of the solar disk was dangerous and painful, but by drawing heavy curtains across tall windows and allowing only a narrow beam of sunlight to pass through a small aperture, often aided by a modest telescope, or lens system. Astronomers could project a wide, shimmering image of the sun onto a flat white card or sheet of paper. Inside these peaceful, darkened chambers, known as camera obscuras, the dazzling intensity of sunlight was softened into a serene, glowing circle of illumination. Here, in calm isolation from the bustling world outside, one could trace the subtle evolution of sunspots or note the delicate curve of the solar rim without straining the eye or rushing the spirit. At the same time, the mathematical tables of Johannes Kepler, published in his monumental Rudolphine tables, had begun to predict rare celestial alignments with unprecedented accuracy. Kepler had calculated that in late 1631, the innermost planet, Mercury, would pass directly between the Earth and the Sun, casting its shadow across the bright solar disk in an event known as a planetary transit. No human eye had ever consciously witnessed such an occurrence, and as November approached, a few dedicated observers prepared their quiet study rooms across Europe, waiting patiently for the clouds to part and reveal this fleeting, beautiful harmony of planetary motion. In Paris, the morning of November 7 arrived with cool, damp air and an uncertain sky. But inside a secluded study, the atmosphere was one of patient, undisturbed focus. On November 7, 1631, in a quiet room in Paris, scholar Pierre Gassendi projected the sun's image onto a white sheet of paper, recording the tiny, dark dot of Mercury as it drifted silently across the solar face for the first observed planetary transit. At first, Gassendi was profoundly surprised by how minuscule the silhouetted planet appeared upon the glowing paper disk. Prevailing theories of the era had led many astronomers to expect a much larger shadow, comparable to a sizable sunspot or a noticeable fraction of the solar diameter. But the dot that crept across the white sheet was extraordinarily minute, crisp, and perfectly spherical. With meticulous care, using a fine pencil to mark its gentle progress at regular intervals, Gassendi tracked the silent journey of this distant world as it crossed the solar surface over several quiet, reflective hours. Each small mark on the paper was a quiet testament to the accuracy of Keplerian orbits, proving that the planets moved along smooth, predictable ellipses around the sun rather than complex geometric epicycles. More than that, the tiny scale of Mercury's shadow offered astronomers their first real, empirical glimpse into the true, immense scale of interplanetary space. The inner planet was not a large, imposing body hovering near the sun, but a humble, distant sphere sailing through an enormous void, its tiny silhouette revealing just how vast, open, and quietly spacious the solar system truly was. The stillness of the room, punctuated only by the soft tick of a timepiece and the gentle movement of paper, mirrored the profound, eternal silence of the cosmos outside. The successful tracking of Mercury's transit marked a gentle turning point in how humanity perceived both the architecture of the cosmos and the peaceful practice of scientific discovery. by transforming the blinding light of the sun into a restful, indirect projection on paper. Gassendi had demonstrated that subtle cosmic events could be recorded with deep precision and effortless calm. The observation provided crucial empirical support for the heliocentric model of the solar system, confirming that the inner planets orbited inside Earth's own path around the sun, while also showing how simple optical instruments could extend human senses into realms previously invisible. Beyond its scientific importance, there was a quiet, poetic beauty in the event that resonated deeply with the natural philosophers of the age. It revealed a universe operating like a vast, serene clockwork, moving according to elegant mathematical principles that unfolded in absolute silence across millions of miles of open space. As the years went on, the practice of solar projection became a staple of astronomical study, allowing generations of stargazers to watch the slow dance of planetary shadows, eclipse edges, and solar features from the comforting shade of their quiet studies. The memory of that November day in Paris remained a gentle reminder of the power of patient observation, how a simple piece of paper, a darkened room, and a beam of sunlight could open a clear window onto the majestic, quiet expanse of the cosmos. As night fell once more over the rooftops of Paris, the bright projection faded back into the soft, velvet shadows of the evening, leaving behind only the carefully inked diagram of Mercury's historical passage across the solar disk. Skywatchers of the era could rest with a newfound sense of clarity and peace, knowing that the great mechanical rhythms of the heavens were slowly being understood, step by quiet step. The cosmos was no longer an enigmatic realm of unpredictable wanderers, but a grand and peaceful house governed by order, balance, and silent harmony, to sit in the quiet of a darkened room and watch the universe reveal its secrets at its own unhurried pace was a reminder of the deep tranquility that attends all true discovery. Today, as we look back across the centuries at those early astronomers who sat in silent rooms tracing light upon paper, we are invited to share in their peaceful wonder. The same silent celestial clockwork continues its steady, timeless turn above us tonight, guiding distant worlds along their eternal paths, and surrounding our world in a vast, soothing hush that gently beckons the mind to rest. As the 17th century advanced, the night skies over Europe began to open up in ways that previous generations could only have dreamed of through poetry and legend. The early telescopes, crafted from simple pairs of convex and concave glass lenses, had lifted the veil from the moon's rugged craters, revealed the shimmering dance of Jupiter's moons, and turned the smooth glow of the Milky Way into vast oceans of individual, glittering stars. Yet, for all their wonder, these pioneering instruments were primarily tools of qualitative observation. They allowed curious minds to gaze upon celestial landscapes, but they lacked the delicate precision needed to measure the precise geometry of the night sky. quiet observatories and rural homes of early astronomers, a new challenge quietly took shape: how to transform the telescope from a viewing glass into a tool of exact physical measurement, to track the slow wanderings of planets across the sky, or to map the subtle shifts of distant star fields with mathematical rigor. Observers needed a way to measure tiny angles directly through the optical path itself. Without a reference grid or a fine scale suspended within the field of view, calculating the distance between two adjacent stars remained a matter of rough estimation, dependent on the visual judgment of the astronomer straining against the faint light of a flickering lamp. The night air outside these early workrooms remained cool, dark, and tranquil, carrying the soft sense of damp soil and rustling leaves, while inside, natural philosophers pondered how to bring absolute clarity and exactitude to the vast darkness above. The sky remained an unfathomable ocean of space, peaceful and silent, waiting for the human mind to devise instruments capable of capturing its most delicate dimensions without disturbing the calm serenity of the night. It was in this atmosphere of quiet curiosity that a remarkable breakthrough occurred among the rolling hills and quiet fields of northern England. In 1638, in Yorkshire, astronomer William Gascoigne placed a fine strand of spider silk inside his telescope eyepiece, inventing the reticle micrometer to precisely measure minute angular distances between distant stars. Gascoigne, a thoughtful young scholar devoted to the study of optics and mathematics, recognized that by placing an extremely fine, well-defined line at the precise focal plane of a telescope's eyepiece, where the image formed by the primary objective lens came into sharp focus, the viewer could see both the magnified stars and the reference mark with perfect, crisp clarity at the very same time. Looking for a material that was thin enough to avoid obscuring faint, light yet strong, and uniform enough to remain perfectly straight under tension, he turned to the subtle artistry of nature, choosing the gossamer thread of a garden spider. When mounted onto small, adjustable brass frames controlled by delicately threaded screws, these microscopic strands of silk allowed Gascoigne to move the lines with extraordinary accuracy across the field of view. By aligning one strand with a bright reference star and gently turning the screw until a second parallel strand touched a neighboring celestial body, he could read the fractional turns of the mechanism to calculate angular separations far smaller than anything measurable with the naked eye or traditional open-sight sextants. The dark tube of the telescope, once a simple window into the heavens, had now become a laboratory of exquisite measurement, held steady in the still night air, while the gentle click of brass teeth and the smooth turning of fine threads echoed softly in the quiet room. This quiet union of biological delicacy and mechanical craft marked a profound turning point in the practice of observational astronomy, bringing an unprecedented sense of order and tranquil harmony to the mapping of the universe. With the reticle micrometer, the vast and intimidating expanse of the night sky could be divided into minute, manageable fractions of a degree, allowing astronomers to record the subtle movements of celestial bodies with peaceful, methodical care. No longer were observers forced to guess the apparent diameter of the sun or moon, nor were they limited to vague descriptions of double stars floating near one another in the dark. Instead, every point of light could be tied to a precise coordinate system defined by the whisper-thin threads of spider silk crossing the field of view. As news of Gascoigne's invention gradually spread through the scientific community in the decades that followed, telescope makers across Europe adopted and refined the technique, integrating fine crosshairs and micrometer screws into standard astronomical instruments. The simple act of looking through an eyepiece became a serene ritual of patience and stillness, where an observer might sit for hours in the deep quiet of midnight, watching a distant planet drift slowly along the dark, razor-thin line of silk, while carefully noting down measurements in a leather notebook by the warm glow of a shaded lantern. The universe, once so wild and unmeasurable in its infinite depth, seemed to fold itself gently into the clean, graceful geometry of the telescope, offering a reassuring sense of harmony to those who watched over it from the shadowed earth below. As the night deepened and the stars continued their timeless, silent march across the dark vault of heaven, the micrometer stood as a testament to the power of subtle human ingenuity, resting gently within the quiet rhythms of nature. The fine spider silk, gathered from quiet corners of dew-covered hedgerows and meadow grass, held its place inside the dark brass tubes, completely unaffected by the vast cosmic distances it was tasked with measuring. In the cool stillness of late night, as the breeze softened to a whisper outside the window and the world fell into deep slumber, astronomers could take comfort in the steady, unchanging precision of their instruments. Every measurement taken through those fine reticles drew humanity one step closer to understanding the true scale of the solar system and the quiet mechanics of the stars. The sky remained as peaceful and vast as it had always been since ancient times. Yet now it was viewed through an optical window that paired the infinite grandeur of the cosmos with the delicate lightness of a single silk thread. Beneath this canopy of quiet light, surrounded by the restful silence of the sleeping countryside, the astronomer could finally rest their eyes, confident that the night had revealed a little more of its silent truth, leaving the mind at peace to wander into gentle, dreamless sleep. As the 17th century unfolded, the study of the night sky began to transition from open-air observations under the biting cold air into quiet, sheltered interiors where light could be measured with tender precision and unhurried patience. In an era before grand observatories were established on high mountain peaks, early skywatchers sought solace in simple, quiet spaces, turning humble rooms into peaceful optical sanctuaries in the damp, gentle countryside of northwestern England. Late autumn moved quietly into winter, wrapping the rolling fields in low mist and soft gray skies. It was here, far from the noise of crowded cities, that natural philosophers learned that the immense radiance of the sun could be tamed and understood without gazing directly into its blinding fire. By closing the heavy wooden shutters of a small window and allowing only a tiny beam of sunlight to pass through a modest telescope lens, the bright expanse of the heavens was brought softly indoors, projected onto clean paper cards. This simple technique allowed observers to examine the solar surface in complete comfort, watching for the delicate drift of sunspots and the rare, silent passage of neighboring worlds. On December 4, 1639, in Much Hoole, Lancashire, astronomer Jeremiah Horrocks projected the sun's reflection onto a paper card in a darkened room, recording the silent transit of Venus across the solar disk. In the deep stillness of that cold afternoon, between his modest clerical duties and the gathering winter dusk, Horrocks watched as a tiny, perfectly round ink-black silhouette glided slowly across the luminous golden circle of sunlight. The moment was one of profound quiet, a rare alignment that had never before been witnessed by human eyes, foretold only through long hours of painstaking mathematical calculations carried out by the warm glow of candlelight. The observation carried out by Horrocks in that quiet Lancashire room represented far more than a fleeting visual wonder. It was a peaceful breakthrough in human understanding of planetary mechanics and cosmic scale. Before this quiet afternoon, the exact distances separating the Sun, Venus, and the Earth remained uncertain, constrained by ancient estimates that placed the celestial bodies much closer together than they truly were. As Horrocks carefully marked the position of the dark spot at regular intervals across the paper card, he was able to calculate the true physical size of Venus and refine our understanding of the vast, breathing scale of the solar system. The sheer silence of the event added to its deep majesty. For while the motion of planets through the vacuum of space involves unimaginable speeds and immense gravitational forces, to the watcher in the darkened room, it appeared as nothing more than a slow, gentle shadow creeping across a pool of warm golden light. This gentle method of projection protected the observer's eyes while revealing fine details of the cosmos that had remained hidden since the dawn of humanity. The patience required for such work was extraordinary, requiring the observer to wait through long hours of cloud cover and uncertain winter weather, maintaining a calm, unhurried focus. When the heavy clouds finally parted to reveal the projected sun, the reward was a profound sense of cosmic harmony, proving that the planets moved along precise, predictable paths designed by natural laws. As the winter sun set lower on the horizon and the transit drew to its peaceful end, the room returned to soft shadow, leaving behind a precious record of light and geometry that would help guide future generations of skywatchers. Across the continent of Europe, This delicate art of channeling sunlight into darkened spaces found an even grander expression inside the quiet, soaring interiors of great stone cathedrals. During the mid-17th century, long before electronic sensors or modern observatories were conceived, natural philosophers recognized that the vast, stable architecture of stone churches offered an ideal environment for high-precision astronomical research. Within these high-vaulted sanctuaries, the air remained remarkably still and temperate, protected from the thermal currents and shifting winds that often disturbed outdoor observations. By placing a small, precise aperture high in the roof or wall of a cathedral, an opening known as an oculus, the majestic building itself was transformed into a monumental camera obscura. A single, focused ray of noon sunlight would pierce the cool, shadow-filled nave, casting a glowing image of the solar disk onto the smooth stone floor below. As the seasons shifted from the warm, golden days of summer toward the quiet chill of winter, the path of this midday sunbeam moved steadily across the floor, tracking the changing altitude of the sun with astonishing accuracy. These cathedral observatories allowed astronomers to measure the precise length of the solar year, refine the calendar, and study the subtle variations in Earth's orbit with a degree of precision that smaller instruments could never achieve. Standing in the cool, silent air of these sacred spaces, surrounded by soaring stone arches and soft echoes, observers experienced a unique union of art, architecture, and celestial science, where the daily passage of sunlight became a serene ritual of quiet discovery. This harmonious blending of monumental architecture and celestial measurement reached its most brilliant fulfillment in the historic Italian city of Bologna. In 1655, inside the quiet nave of San Petronio Basilica in Bologna, astronomer Giovanni Domenico Cassini set a 67-meter marble meridian line into the floor, watching a warm beam of sunlight drift across calibrated brass plates to calculate the Earth's changing distance from the sun. High above, set into the lofty southern vault of the basilica, a tiny aperture cast a brilliant oval of sunlight onto the cathedral floor each day precisely at solar noon. Cassini laid a perfectly straight line of white marble across the wide floor of the church, inlaying it with calibrated brass strips marked with the days of the year, the signs of the zodiac, and fine gradations of angular measurement. As the spot of sunlight crossed this meridian line day after day, Cassini observed something profound. The projected image of the sun was not always the same size. During the cold months of winter, when the Earth was closest to the sun in its elliptical orbit, the solar image appeared slightly larger and moved more rapidly across the line, whereas in the heat of summer, when Earth was farther away, the image was slightly smaller and moved more slowly. By measuring these minute variations in the size and speed of the light beam, Cassini provided clear, empirical proof that the Earth moved along an elliptical path rather than a perfect circle, confirming the revolutionary planetary laws of Johannes Kepler. Within the cool, peaceful sanctuary of San Petronio, the gentle movement of sunlight across marble and brass turned complex mathematics into a visible, soothing reality. As the afternoon shadows lengthened across the nave, bringing a serene quiet to the basilica, the steady mechanics of the universe continued their silent clockwork, inviting the mind to rest in the timeless beauty of a cosmos governed by order, balance, and eternal peace. In the mid-17th century, as night descended gently over the damp meadows and tiled rooftops of The Hague, the world of observational astronomy was entering an era of quiet refinement and patient optical craft. The Netherlands in those years was a place where glassmakers, scholars, and natural philosophers gathered in quiet study, fascinated by the precise behavior of light as it passed through curved pieces of silica. Among them was Christian Huygens, a thoughtful young man whose mind gravitated naturally toward the measurement of time, the geometry of motion, and the faint illumination of the night sky. The Dutch landscape offered long, still evenings where the air settled into a cool dampness, creating moments of remarkable clarity for those willing to wait beside an open window or in a darkened courtyard. In this peaceful domestic setting, astronomy was not a hurried endeavor marked by dramatic announcements, but rather a slow, meditative practice carried out in the stillness of midnight. Hours were spent in low light, adjusting fine screws, smoothing glass with tiny particles of abrasive powder, and waiting for atmospheric turbulence to subside so that a distant planet might hold still for a single breathtaking second. The sky above the Low Countries, though often brushed by sea fogs and drifting clouds, would occasionally clear into a deep, transparent navy, revealing the full tapestry of stars with astonishing sharpness. It was during these tranquil nocturnal hours that the early telescopists learned the art of deep watching, tuning their senses to the subtle gradations of light and shadow that lingered upon the disk of the moon, or marked the faint, wandering points of light that moved among the fixed constellations. For Huygens, the night was a silent laboratory where the mechanics of the cosmos could be carefully disentangled from the illusions of human sight, provided one possessed the patience to grind lenses of exceptional smoothness and assemble instruments capable of reaching out into the quiet depths of space. The art of early telescope construction demanded an extraordinary degree of tactile patience, as every curvature of glass had to be brought to perfection entirely by hand. Christian, often working alongside his brother Constantine, spent countless quiet hours in their workshop, moving glass blanks in slow, rhythmic circles against iron tools coated with pitch and fine emery powder. The sound of wet grinding was a soft, steady whisper that filled the room, measuring out the passing time much like the pendulum clocks Huygens would later invent and perfect. To view the planets without the frustrating color fringing that plagued early optical instruments telescope makers were forced to increase the focal lengths of their lenses, creating instruments of astounding length that required great care to steady against the night breeze. A longer focal length meant a shallower curve on the glass, which in turn minimized optical distortion and produced an image of breathtaking purity, provided the long tube could be kept from swaying. These instruments were suspended from wooden poles, supported by ropes and pulleys, or extended through high windows, forming long, slender bridges between the observer on Earth and the silent realms above. Grinding such lenses required not only physical endurance, but an intuitive feel for the glass itself, sensing through the fingertips when a curve was uniform to within a tiny fraction of an inch. As the surfaces grew smoother, finer polishing compounds like putty powder were introduced, transforming the dull, milky surfaces into crystal clear portals capable of capturing the most delicate beams of antique light when held up to a candle flame in the darkened studio. A finished lens would reveal no scratches, no bubbles, and no uneven ripples, ready at last to collect the pale, ancient glow of distant worlds that had traveled across millions of miles of empty ether to reach the quiet shores of Holland. In March 1655, in The Hague, Dutch scientist Christian Huygens pointed a 12-foot homemade telescope with hand-ground lenses toward Saturn, discovering its bright moon Titan drifting beyond the planet's pale rings. The ringed planet had long puzzled earlier astronomers, including Galileo, who had seen only strange, ear-like appendages on either side of the central globe that appeared and disappeared over the years in a baffling display. But through Huygens's superior, hand-polished objective lens, suspended within its long wooden framework, the image of Saturn resolved with unprecedented clarity in the crisp March night air. Beyond the main disk of the planet, which shone with a soft, buttery yellow hue, Huygens noticed a tiny, distinct point of light situated along the plane of the planet's mysterious appendages. Night after night, with infinite patience, he returned to his telescope, recording the exact position of this tiny star-like companion relative to Saturn's body. Over the course of 16 days, he watched with quiet wonder as the faint speck moved in a regular, elegant orbit around the giant planet, completing a full circle before returning to its starting position. It became clear that this was not a background star passing behind the planet by chance, but a true satellite, a major moon tethered to Saturn by the invisible thread of gravity, orbiting far out in the dark abyss of space. This revelation provided the first conclusive proof that Earth was not the only planet in the solar system accompanied by a secondary celestial body other than Jupiter, broadening human perspective on the vast complexity of planetary systems. The discovery of Titan was a triumph of optical refinement and quiet persistence, proving that the secrets of the cosmos yielded not to force or grand speculation, but to clarity clarity of vision and the steady, contemplative observation of the midnight sky. As news of the discovery quieted down into the enduring record of astronomical science, the identification of Titan opened a new era in how humanity perceived the architecture of the outer solar system. The knowledge that a distant world possessed its own moons, drifting in silent majesty through the cold dark, invited observers across Europe to gaze upward with renewed wonder and humility. The universe was revealing itself to be far larger, more intricate, and more beautifully ordered than previous generations had ever dared to dream. In the quiet solitude of his study in The Hague, Huygens continued to refine his optical theories and improve his instruments, eventually solving the long-standing mystery of Saturn's shape by demonstrating that the planet was surrounded by a thin, flat ring that nowhere touched the globe itself. Yet, it was that first serene sighting of Titan, a solitary spark of light gliding through the deep velvet background of space, that marked a turning point in the history of the telescope. It showed that beyond the limits of unassisted human vision lay whole worlds awaiting discovery, moving in timeless harmony according to natural laws that could be comprehended through patient study. As the stars turned overhead and Saturn drifted slowly across the meridian, the early telescope ceased to be merely a novel glass toy and took its place as a profound window into the infinite. The cool Dutch night settled back into silence. The long telescope was brought indoors, and the peaceful study of the heavens continued its slow, steady journey into the light of a new age. As twilight drifted softly across the ancient stone quadrangle of Trinity College in the autumn of 1668, a profound stillness settled over the town of Cambridge. The gentle waters of the River Cam flowed quietly beneath the stone bridges, mirroring the fading amber hues of sunset and the gradual appearance of the first evening stars. For decades, natural philosophers across Europe had turned their eyes toward the heavens using long glass lenses, seeking to unravel the mysteries of the solar system and the distant firmament. Yet these early refracting telescopes, while revolutionary in the hands of pioneers like Galileo and Kepler, carried an inherent optical imperfection that blurred the boundaries of celestial beauty. As light passed through traditional glass lenses, it bent unevenly, separating white starlight into unwanted halos of color, frustrating fringes of purple, red, and blue that encircled planets and distant stars like phantom rings of mist. In his quiet rooms at Cambridge, a young Isaac Newton spent long, contemplative evenings pondering this fundamental puzzle of optics. Through delicate experiments with glass prisms, he had discovered that white light was not a simple, uniform entity, but rather a rich spectrum woven from all the colors of the rainbow, each color refracting at a slightly different angle when passing through glass. Realizing that no single glass lens could ever completely overcome this chromatic dispersion without growing impossibly long, and cumbersome. Newton turned his mind toward an entirely different principle of optics. Instead of attempting to bend starlight through glass, he reasoned that light could be gathered and focused using the reflective curve of a polished mirror. In a mirror, every wavelength of light, regardless of its color or frequency, obeys the exact same law of reflection, striking the surface and bouncing off at precisely identical angles. This elegant concept held the promise of an image untroubled by color distortion, a view of the cosmos as clear and pristine as the night air itself. As the evening hours deepened and the shadows lengthened across his study, Newton set about translating this theoretical insight into a tangible instrument, combining the patience of an artisan with the deep mathematical intuition of a philosopher. To bring this vision to life, Newton turned to the practical arts of metallurgy and precision grinding, transforming his solitary workspace into a sanctuary of silent, methodical creation. Rather than relying on commercial glassmakers or instrument builders, he chose to craft every component of the instrument with his own hands, working in the quiet hours when the gentle cadence of the night provided unbroken focus. For the primary mirror, glass coated with mercury silvering was inadequate for the precise optical curvature he required. So he turned to a dense alloy known as speculum metal, a carefully measured combination of tin and copper. He melted the metals together, poured the molten liquid into a small mold, and allowed it to cool into a solid disc. Once hardened, the disc presented a dark, rough surface that required endless hours of painstaking labor to shape into a smooth concave parabola. Sitting at his workbench, illuminated by the soft glow of candlelight, Newton rubbed the metal disc against shaped wooden forms using fine abrasives, gradually refining its contour. The process demanded incredible patience. Even the slightest uneven pressure or thermal variation from his hands could distort the precise curvature needed to bring light to a crisp focus. With gentle, rhythmic motions, he moved to the final stage of polishing, using a layer of pitch smeared over a tool and lubricated with fine putty powder. Slowly, over many quiet evenings of meticulous effort, the dull metal surface transformed into a brilliant mirror that gleamed like liquid silver in the dim light. In 1668, at Cambridge, Isaac Newton hand-polished a tiny 2-inch mirror cast from tin and copper to construct the first working reflecting telescope, gathering crisp starlight without the chromatic color fringes produced by glass lenses. The completed instrument was astonishingly compact, measuring barely 6 inches in length, small enough to sit comfortably in the palm of a hand, yet capable of magnifying distant objects with remarkable fidelity. To observe the image formed by the mirror, Newton devised a secondary optical element, a small, flat diagonal mirror positioned at a 45-degree angle inside the main barrel of the telescope. This secondary mirror intercepted the converging rays of light just before they reached their focal point, reflected them sideways through an opening in the side of the tube, where a simple magnifying lens served as an eyepiece. This ingenious layout, which would forever after be known as the Newtonian reflector, allowed the observer to look comfortably into the side of the telescope near the top, avoiding the awkward angles required by long refractor tubes pointed high into the zenith. When Newton first pointed his small reflecting telescope toward the night sky, the view through the eyepiece marked a serene triumph in the history of observational astronomy. Looking through the modest wooden tube, he observed the bright disk of Jupiter hanging in the velvet darkness, accompanied by its 4 Galilean moons resting like tiny beads of light against the void. Where earlier refractors would have painted the gas giant with distracting halos of magenta and violet, Newton's reflecting mirror presented the planet with exquisite visual purity, a sharp, clean sphere floating silently in the dark. He turned the instrument toward the moon, tracing the craggy rims of ancient craters, the sweeping dark plains of lunar Maria, and the delicate shadows cast across the terminator line, all rendered with crisp definition and untinted clarity. The success of this tiny device demonstrated that the path forward for astronomical observation did not lie solely in building ever longer glass refracting tubes that stretched dozens or hundreds of feet into the air, suspended from unwieldy scaffolding and swaying in the night wind. Instead, the reflective property of polished metal offered a way to gather immense amounts of light within a compact, stable framework. The tiny 2-inch mirror cast and polished in a Cambridge laboratory held the secret to opening up the deep universe to human eyes. Free from the blurring color fringes of chromatic aberration, starlight arrived at the observer's eye in its truest, most pristine state, carrying information across trillions of miles of empty space without distortion. The serene beauty of this achievement lay not merely in its technical elegance, but in the quiet harmony between nature's laws and human ingenuity. By understanding how light behaves when reflecting off a curved boundary, Newton had created a window into the cosmos that respected the subtle integrity of light itself, allowing astronomers to see distant worlds not through a veil of prismatic color, but as pure, uncluttered radiance. As news of Newton's invention spread to the Royal Society in London, the tiny reflecting telescope was met with widespread admiration, earning its creator election to the prestigious scientific body and cementing a pivotal milestone in the evolution of optical tools. Yet beyond its immediate acclaim, the small instrument laid the quiet groundwork for centuries of astronomical exploration that would follow. The principles embodied in that modest 2-inch disc of copper and tin would eventually scale upward across the generations, inspiring great skywatchers to forge larger and larger mirrors of speculum metal, glass, and quartz. From the massive wooden reflectors crafted by William Herschel in the English countryside to the giant glass mirrors atop mountain peaks in the 20th century, and ultimately to the segmented gold-coated mirrors, floating silently in the deep freeze of outer space. The lineage of every modern reflecting telescope traces its origin back to that peaceful workbench in Cambridge in 1668. Today, as night descends across the world and millions of stars emerge in the silent dome of heaven, the story of Newton's mirror offers a comforting reminder of the power of gentle patience and quiet curiosity. The night sky remains an ancient, peaceful expanse, welcoming all who pause to look upward with wonder. The faint, steady starlight that travels across light years to reach our eyes arrives unchanged, carrying the quiet history of the cosmos into our present moment. Resting in the quiet dark, we can imagine the calm atmosphere of that Cambridge room long ago. The rhythmic sound of hand polishing, the soft reflection of candlelight on metal, and the peaceful satisfaction of gazing through a small tube to see the universe brought into serene, perfectly focused clarity. As the gentle evening shadows lengthened across late 17th century London, a profound calm descended over the winding cobblestone lanes, softening the daytime hum of trade and craftsmanship into a restful, velvet silence. Along the quiet curves of the River Thames, where dark waters reflected the soft, pale embers of dusk, the ancient city seemed to sigh softly and relax under the vast, darkening vault of the night sky. In the wake of the great rebuilding efforts of the late 1660s, stone and brick structures stood firm and silent against the cool night air, and among them, Gresham College served as a tranquil sanctuary of learning and quiet reflection. Here, within sturdy walls insulated from the restless bustle of urban life, scholars of the early Royal Society gathered to study the subtle laws of nature and contemplate the silent order of the heavens. Astronomy, which had long relied on broad visual observations and sweeping star charts, was entering a period of extraordinary refinement, turning its focus toward measurements of breathtaking, delicate precision. Scientists were beginning to realize that the true nature of the cosmos, its vast dimensions, its subtle movements, and its hidden geometries, might not reveal itself through sudden, dramatic discoveries, but rather through the patient, quiet observation of the smallest imaginable details. Outside, the night air grew crisp and still, carrying the gentle scent of wood smoke from slumbering hearths and the damp mist drifting off the river waters. Within the quiet rooms of the college, where candle flames flickered softly before burning low, the evening hours invited a deep and meditative focus, encouraging the inquiring mind to set aside the cares of the terrestrial world and harmonize its thoughts with the slow, tranquil wheeling of the stars above. In this peaceful haven, time itself seemed to slow down, offering a quiet pause from the demands of daily life and allowing the spirit to rest in the comforting presence of the night. At the heart of this intellectual pursuit was a desire to solve one of the most fundamental mysteries remaining from the Copernican revolution: the definitive proof of the Earth's motion around the Sun through the detection of stellar parallax. Copernicus had proposed that as our planet completes its vast, yearly journey through space, nearby stars ought to appear to shift ever so slightly against the background of more distant suns. Yet this subtle displacement had eluded detection for generations, because the stars lay at unimaginable distances. To measure a movement so imperceptibly small, astronomers faced immense practical difficulties. For the long, unwieldy telescopes of the era were prone to swaying in the wind, vibrating with the lightest footstep, and warping under changing temperatures. Recognizing that true accuracy required an instrument anchored in total stability and darkness, the brilliant polymath Robert Hooke conceived a design of unmatched architectural ingenuity. In 1669, at Gresham College in London, scientist Robert Hooke built a 36-foot vertical telescope inside a chimney structure. Peering straight up through a quiet aperture in the roof to measure the faint, subtle shifts of the star Gamma Draconis across the seasons. By housing the 36-foot optical column entirely within the thick masonry of an unused vertical chimney shaft, Hooke created a protected sanctuary of thermal equilibrium, completely shielded from urban drafts, ambient city light, and mechanical tremors. The brick structure of the college itself became the rigid body of the telescope, holding the objective lens at the top and the observing eyepiece at the bottom in perfect, unyielding alignment, providing a tranquil well of darkness through which the sky could be studied in absolute rest. Every brick of the chimney wall helped to damp external sound and thermal movement, surrounding the long optical path with an insulating shroud of calm that protected the delicate rays of starlight on their journey downward. Hooke's selection of the star Gamma Draconis, a warm orange giant glowing brightly in the constellation of the Dragon, was a triumph of thoughtful scientific strategy. Because Gamma Draconis passed almost directly through the zenith, the point of the sky located precisely overhead in the latitude of London. Its light entered the vertical chimney telescope perpendicularly, passing through the shortest and thinnest column of Earth's atmosphere. This eliminated the heavy atmospheric refraction that bends starlight near the horizon, allowing the star's faint rays to travel downward through the darkness with exceptional clarity and minimal distortion. At the base of the chimney, in a small, windowless chamber draped in dark fabric, Hooke created a peaceful, meditative observatory where he could lie back comfortably on a cushioned couch, aligning his eye with the brass eyepiece mounted near the floor. Looking up through 36 feet of cool, shadowed chimney space, the open aperture in the roof appeared as a small, serene square of deep indigo sky, across which Gamma Draconis drifted with majestic slowness during its nightly transit. Equipped with fine micrometer screws and delicate crosshairs made of fine silk thread, Hooke waited in the soothing darkness, listening to the soft, rhythmic ticking of a pendulum clock as he noted the precise moment and position of the stars crossing. The complete quiet of the chimney shaft isolated the observer from all external sensory distraction, turning each observation into an exercise of deep stillness, where human consciousness rested in quiet attunement with the steady, silent drift of celestial light. In that darkened sanctuary, the boundary between the observer and the vast universe seemed to dissolve into a gentle, harmonious quiet, filling the room with an undeniable sense of peace. The soft, amber starlight, having traveled across light years of peaceful void, settled gently upon the eyepiece, connecting the observer below directly to the ancient heart of the dragon constellation above. Month after month, as the wheel of the year turned gently from the crisp nights of autumn into the silent frosts of winter, and onward through the gentle budding of spring into warm summer evenings, Hooke returned to his quiet vertical chamber to measure the stars' position across the seasons. Each observation recorded a single point in the Earth's orbit, contributing to a patient, long-term study that sought to map the subtle geometry of our solar system with unprecedented care. Although the definitive numerical measurement of stellar parallax would ultimately require the even more advanced optical tools of 19th century astronomers, Hooke's chimney telescope represented a revolutionary leap forward, demonstrating that pushing the frontiers of human knowledge required not noise or haste, but an unwavering commitment to stillness, precision, and harmony with natural laws. Indeed, his work with Gamma Draconis laid the crucial groundwork for future astronomers like James Bradley, who in the following century would discover the aberration of light using similar zenith observations. As one contemplates that silent chimney shaft in Gresham College, there is a profound, soothing peace in imagining the astronomer resting in the dark, watching the timeless glow of a distant star pass overhead, while the surrounding city slept in deep tranquility. The long cylinder of the chimney served not merely as a tool of measurement, but as a bridge connecting human stillness to the eternal calm of the cosmos. The stars move across the night sky with unhurried grace, reminding us that the grandest truths of the universe unfold in deep quietude, inviting the weary mind to lay down its burdens, breathe slowly, and drift into a restful and restorative sleep under the quiet watch of the universe. With every passing hour, the heavens continue their silent rotation, wrapping the world in a blanket of darkness and serene stillness that lulls the body and mind into deep, undisturbed rest. As the mid-17th century unfolded across Europe, the telescope evolved from a surprising novelty into an instrument of quiet precision, opening an era of careful measurement, patient cataloging, and reflective wonder. Astronomers no longer sought merely to capture fleeting glimpses of celestial novelties. Instead, they turned their long wooden lenses toward the sky night after night, carefully mapping the contours of nearby worlds with a steady and meticulous hand. The moon, which had once appeared to ancient skywatchers as a smooth, pearlescent disk suspended in the night, was now revealed in all its intricate, quiet topography. Through the improving glass of mid-century telescopes, observers could trace the soft shadows cast by jagged crater walls across the lunar terminator, the delicate dividing line between lunar day and night. They watched as sunlight slowly crested over lofty mountain ranges and illuminated vast, dark lowlands that stretched across the lunar face like silent, dried ocean beds. In the quiet university city of Bologna, two Jesuit scholars spent years peering through long refractors, comparing drawings, and carefully measuring the positions of hundreds of lunar features. In 1651, in Bologna, astronomers Giovanni Battista Riccioli and Francesco Maria Grimaldi published a detailed lunar map, introducing calm Latin names like Mare Tranquillitatis, the Sea of Tranquility, for the dark plains of the moon. This comprehensive map, published within Riccioli's grand astronomical treatise, replaced the chaotic and conflicting names of earlier observers with a thoughtful, poetic system of nomenclature that remains in use today. Where others had named lunar features after terrestrial kings, philosophers, or national figures, Riccioli and Grimaldi chose to bestow upon the moon's geography a sense of calm, atmospheric beauty, and emotional resonance. They designated the smooth, dark expanses of basaltic lava, which they recognized as low-lying plains rather than bodies of actual water, with peaceful Latin terms drawn from weather, moods, and tranquil states of mind. Beside the Sea of Tranquility lay Mare Serenitatis, the Sea of Serenity, and Mare Fecunditatis, the Sea of Fertility, while nearby stretched the vast expanse of Oceanus Procellarum, the ocean of storms. They also honored astronomers of the past by placing their names upon the circular crater rims, placing ancient thinkers like Ptolemy and Copernicus side by side across the lunar highlands. This thoughtful act of cartography bestowed upon the night sky a gentle human order, transforming the moon from an alien stone into a familiar landscape of quiet meditation. When stargazers gazed up through their eyepiece lenses, they were no longer looking at an unknowable void, but at named, peaceful places whose very titles invited rest, quiet thought, and gentle contemplation under the velvet dark. As the decade turned into the late 17th century, the spirit of patient measurement shifted its focus from the nearby moon to the outer reaches of the solar system, where distant planets orbited in slow, grand arcs. At the newly established Paris Observatory, constructed under royal patronage as a sanctuary for science, astronomers gathered under high stone ceilings, equipped with the finest instruments of the age. Long aerial telescopes, suspended from tall wooden scaffolds without tubes to reduce weight, were pointed toward the glowing disk of Jupiter and its 4 bright satellites. Night after night, skywatchers recorded the precise moments when these moons slipped behind Jupiter's shadow or emerged from its dark limb into the sunlight, using newly invented pendulum clocks to keep time with unprecedented accuracy. Among these celestial clockworks, The innermost moon Io moved with a remarkably swift and regular rhythm, completing an orbit every 42.5 hours. Yet over years of observations, astronomers noticed a strange, subtle drift in the schedule of Io's eclipses. Sometimes the moon disappeared behind Jupiter several minutes ahead of predicted time, while at other seasons of the year, it lagged quietly behind. In 1676, at the Paris Observatory, Danish astronomer Ole Romer carefully timed the silent disappearance of Jupiter's moon Io into planetary shadow, discovering that light travels at a finite speed after noticing a systematic 16-minute delay when Earth drifted farther away in its orbit. Before Romer's breakthrough, even the greatest natural philosophers had assumed that light was instantaneous, traveling across any distance in a single, timeless moment. Romer realized that the apparent irregularity in Io's orbital schedule was not a flaw in the celestial machinery, but a reflection of Earth's own movement around the Sun. When Earth was on the same side of the Sun as Jupiter, the distance between the two planets was shorter, allowing the light carrying the image of Io's eclipse to reach terrestrial observers sooner. As Earth drifted to the far side of its orbit, millions of leagues farther away, the light had to traverse that additional expanse of space, creating a cumulative 16-minute delay. This elegant revelation fundamentally reshaped humanity's understanding of the physical cosmos, establishing that light is not an instantaneous flash, but a traveler moving through space at a finite, measurable pace. To look out into the night sky was to look back into time itself, receiving whispers of starlight and planetary reflections that had departed their sources moments or years before. As the quiet hours of the night slipped away over the observatories of Europe, this realization offered a comforting perspective on the vastness of space. The universe was revealed to be a grand, harmonious clockwork governed by universal laws, where light moves gently across the dark, where lunar planes rest in perpetual quiet, and where the sky continuously invites the human mind into a state of peaceful, restful wonder. As the soft darkness of evening settles gently across the landscape, and the earth cools beneath a vast, shadowy sky, we arrive at the tranquil culmination of our long journey through the history of astronomy. Across uncounted centuries, human eyes have turned upward in quiet wonder, tracing the slow and majestic drift of the heavens from ancient observers who stood upon quiet hillsides noting the rising of seasonal constellations, to early scholars who carved alignments into stone and charted the subtle wanderings of the planets. The sky has always offered a deep, soothing rhythm to those who pause to look. With the coming of the 17th century, a profound transformation took place as polished glass lenses transformed our vision, opening hidden realms within the cosmic dark. The early telescopes of Galileo, Kepler, and Huygens revealed moons circling distant spheres, cratered highlands bathed in soft sunbeams, and millions of stars previously hidden from view. Yet, as astronomers sought even greater clarity and magnification, without the distorting color fringes of early thick lenses, they constructed instruments of astonishing length and delicate design, high above the quiet streets and resting harbor of Danzig. The cool night air carried the whisper of the Baltic Sea across roofs resting in shadow. Upon one such high platform, a remarkable structure rose into the midnight air, an extraordinary open-frame aerial telescope constructed of long wooden struts, fine cords, and balanced pulleys that allowed it to sway gently against the dark sky like the mast of a silent ship. Suspended high above the sleeping city, this immense instrument represented both the physical limit of early optical engineering and a quiet monument to human patience. Beneath its long, floating silhouette, the night was calm and serene, creating a sanctuary of stillness where the secrets of the cosmos could be quietly observed, measured, and cherished in total peace. It was within this high, starlit sanctuary that astronomer Elisabetha Hevelius worked side by side with her husband Johannes, sharing a deep devotion to the stars and the slow, rhythmic labor of celestial mapping. In 1679, atop a quiet rooftop observatory in Danzig, astronomer Elisabetha Hevelius worked alongside her husband Johannes, operating an open-frame aerial telescope 45 meters long to painstakingly catalog 1,564 night stars. This extraordinary accomplishment was born not from haste or dramatic discovery, but from a shared, tranquil persistence that matched the slow, silent turn of the firmament above. Operating such a vast instrument required immense physical coordination, patience, and visual skill, as the long wooden frame had to be adjusted with ropes and suspended pulleys to align perfectly with faint stellar coordinates. Elisabetha's mastery as an observer and her meticulous care in recording data made her one of the most accomplished female astronomers in history, working in seamless harmony with her husband to produce a stellar atlas of unprecedented accuracy and beauty. In the quiet darkness, illuminated only by the soft, warm glow of a shaded oil lamp, they noted the brightness, position, and delicate relationships of each point of light. Each star written into their ledgers was an act of quiet preservation, binding the vast infinity of space to the gentle page. The great wooden aerial telescope, extending 45 meters into the dark, acted as a peaceful bridge between the ancient tradition of naked-eye stargazing and the emerging era of high-precision optical astronomy. As the hours passed toward dawn, the couple worked in easy, unspoken understanding, their movements synchronized with the silent rotation of the earth, finding in their shared nocturnal labor a profound sense of calm, order, and quiet fulfillment. The star catalog, crafted atop that Danzig roof, remains a lasting monument to what can be achieved when human curiosity is guided by patience, stillness, quiet reverence for the night. Looking back across the long path we have traveled together, from the prehistoric Skywatchers, who first noticed the repeating phases of the moon, through the ancient Babylonian, Egyptian, and Greek scholars who calculated celestial paths, to the Islamic astronomers who preserved, refined, and named the stars, and finally to the early telescope makers who revealed the true depths of space. We see a single, unbroken thread of human wonder. Every generation has looked up into the same dark sky, seeking to understand our place among the stars and finding comfort in the steady, unchanging order of the universe. The invention of the telescope did not lessen the mystery of the cosmos. Rather, it deepened its peace, showing us that even in the unimaginable vastness of space, order and harmony prevail. The long aerial tubes of the 17th century have now given way to modern observatories and space-based mirrors. Yet the feeling of standing under a quiet, starry night remains entirely unchanged across the centuries. As the historic observatory in Danzig fades gently into the soft mist of history, the stars Elisabetha and Johannes catalogued continue to shine down upon us with the same calm, silver light. They move through their ancient, unhurried paths, indifferent to the busyness of the world below, inviting us to set aside our daily cares and rest beneath their silent, eternal watch. Now, as our journey through the history of early astronomy reaches its final, restful conclusion, the night deepens and surrounds us in complete, soothing calm. The long wooden telescopes are stowed away, the brass dials grow still, and the handwritten star maps rest safely in quiet archives. There are no more coordinates to calculate tonight, no more lenses to align, and no more distant worlds to search for in the dark. The sky above is vast, soft, and endless, holding the earth in a gentle, protective embrace. As you listen to the rhythmic cadence of the night, allow your thoughts to drift like the stars themselves, slowly moving across the peaceful expanse of space. Feel the quiet stillness that rests upon the rooftops of history, a stillness that flows down through the centuries to touch this very moment. The universe is ancient, beautiful, and at peace, moving in perfect, quiet harmony. Breathe slowly and deeply, letting go of all the thoughts of the day, and let yourself sink effortlessly into the soft warmth of rest, cradled by the timeless light of 1,000 quiet stars, as sleep comes gently, naturally, and completely.